Hey, this is Juan Tutors, and today we are working on the June 2024 Physics Regents. For me, the Regents that just happened a couple of weeks ago. For you, you may be taking on August Regents or January Regents or June Regents, and we are going to jump right into number one, numero uno. But before that, I just want to say good luck on the test. And I fully believe in your ability to do as well as you can possibly do on the test. One of the ways that you're trying to get the best grade possible is by watching this video, and I want to congratulate you for that. My goal is to make this the best, absolute best video possible, and because of that, I want to explain how to do each problem, but I also want to go actually over some test taking strategy that you could use to maximize your score, even in situations where you maybe don't know how to do the problem. What I advise you to do with this video, right before we jump into number one or numero uno, is that what you should be doing, yes, you can just watch all the way through the video if that is, and I know from my viewership numbers that's what some people do. The test is in a couple of hours, and some students just play the video as fast as possible. And if that's what you want to do, that's great. What I actually advise you, even in that situation, is actually to pause the video and always choose an answer before you see me choose an answer and how I get the answer myself. And when I say choose an answer, I don't say I think it's this one and then watch, because you could easily fool yourself into thinking you were right. Because like if I give you a different answer, you're like, oh, I knew it was that one. I've seen students do that all the time. I knew it was that one is the same thing as I was wrong on both the one I chose and the one that I thought it was. Really, it is, because what you did at that point is convince yourself that one of two possible ideas is right, and then you kind of went with one of the two ideas without really actually choosing which one made most sense. And I will also say this: I know a lot of students like say, "Oh, I think the answer is this one, but I'm going to choose that one." That's not good thinking. So definitely always go with the one that you think is the most right. And actually, I advise you to the complement of that question in this case is which ones are the most incorrect. And actually, I strongly advise you to eliminate the one that you think is the most incorrect, because often in a physics problem, there's maybe, and without exaggeration, between 1 and 50 ways of doing the problem, sometimes even more. And that's without exaggeration. But then there are thousands, without exaggeration again, thousands of different ways of confirming which answers are incorrect. So you, just as a living human being living in the universe that you live in, are actually way more conscious about the way that the world and the universe actually works than you think you are. And I don't mean that in a pseudo-scientific or any other that kind of way. I mean, literally, you live in the world and you've had almost 2 decades of experience with it, and you actually know how things function. That's literally what I mean. And so you actually have a lot of good intuition about what doesn't make sense, even if you don't know the answer in terms of what does make sense. So focus on what is incorrect way more than focusing on what is correct will maximize your grade. So, on that note, I want to be clear that the school is required to provide you a scientific or graphing calculator, a centimeter ruler, a protractor, and a copy of the reference tables. That you'll get a copy of the reference tables, but sometimes the school does try to play funny business with the calculators and the centimeter rulers. Make sure that they provide those for you. They are required to do that. That said, we're going to jump right into numero uno, number one. Which quantity is a vector? Electric field, electric potential difference, electric charge, or electric power? And I'll be honest, this is probably, they will always ask you this, by the way, which quantity is a vector? So it does help you to know a few different quantities that are vectors. This is honest, and I'm being honest, this is probably one of the more difficult which one is a vector questions that I've seen, because there's like some directionality to some of these numbers which don't actually have direction. So some students are fooled into thinking certain ones are vectors and some aren't. So again, electric field, electric potential difference, or electric charge, or electric power. Let me first cross out though which one I know. If I'm so when you hear me talk about fake student me, I'm simulating myself as a student for the purposes of teaching you how I would go about eliminating an answer or something like that. Okay, so the one that I will eliminate as a fake student is this one, electric charge. Why is electric charge not a vector? This is a number. It's a number and it's also just a physical property, okay? There's nothing, well, property. There's nothing wrong with a physical property being a vector or a scalar. A scalar is a number. But the thing is that you have to know what a vector is to be able to answer this question. So why not go and actually answer that question? What is a vector? It's a property that has uh, size and direction. At a single point. Okay. Okay. At a single point. Size and direction at a single point. And I added the at a single point because that actually is the piece that helps you tease out which one of these four answers maybe makes the least amount of sense. For some students, I've seen a lot of students choose electric potential difference, for example, as because they think it's a vector because there is some directionality feeling to it, or electric power because they're like force has a direction, so power should have a direction, or they imagine other scenarios in which they see power occurring. And there's some directionality to it. I do agree. There's some directionality to it, but that's a difference from the value of the thing having a direction at a single point. So we are not comparing two different points for a vector. We are looking at a single point and determining whether there is a directionality to it. So what about this electric potential difference? Electric potential difference measures the potential the potential at 2 points, okay? And what do we do after we measure those two potential differences? Then we subtract. So it's literally a potential difference. You literally measure the potential at 2 points and then you subtract. But notice there's 2 points required to measure the potential difference. So that's why the electric potential difference is actually incorrect. Now, what about this electric power? The power, one way to measure power is equal to force times a velocity. But another way to measure power is energy divided by time. And now the thing is, if you see the force and velocity, you're like, well, force has a direction and velocity has a direction. Um, and I'm going to put an arrow here dotted with velocity for those of you who are comfortable with vectors. And a better way to write it is FV without arrows times the cosine of theta between these two. Okay? Notice in the second equation, I don't have arrows on top because we actually don't use the vector. We actually use the magnitude of those two vectors and then the angle between the force and velocity vector. And another explanation why electric power is not a vector, well, energy is not a vector itself. Energy is a value. Energy is a number, and time is also not a vector. Um, yes, we'll say it that way. Time is not a vector because it only has one time dimension, right? So that one's not it. So what about electric field? Well, electric field at every single point, the electric field has a direction. So like if this is a proton, you have an electric field pointing out of the vector, okay, out of the particle. So at any given point there, you might have an electric field that is out of the particle, which is a certain size. And at this point, it's out of the particle, but smaller, really close to the particle, out of the particle, but bigger. So electric, these arrows here represent the electric field with magnitude and direction. Okay, and a good way to think about what a vector is like if a vector always has a magnitude because all basically all things have magnitude. But if you have to say like that way, or that way, or that way, or that way, then you can identify that thing as a vector. So a force always is has a direction. You're pushing in that direction. An electric field also pushes a particle in one direction, and therefore an electric field is a vector. Okay? I know this one had a lot of like directionality to the answers, whereas a lot of other problems in other regions didn't, which made that problem, in my opinion, one of the harder, which one is the vector questions. That said, since you know that every regent is going to have which one is a vector or which one is a scalar question, do get accustomed to which ones are vectors. So anything with that direction is a vector. So force, electric field, electric force, gravitational force, every force, so friction. Let's see. We don't deal with air resistance in this class, but air resistance, if we ever had to deal with it, if it ever came up, is a force. Let's see. Tension. The string pulls in the direction of the string itself. Springs push or pull in the direction of the spring extending or contracting. Forces. So forces are all vectors. And there's more. Any that have a direction is a vector. And then, of course, things that are not vectors, energy, time, and any situation in which you multiply two vectors. So speed and anytime you take a magnitude of a vector. So the magnitude of the vector is not a vector because you have to attach the direction to it to make it a vector. So speed is not a vector, but velocity is. The magnitude of acceleration is not a vector, but the acceleration is. Okay? The displacement, as an arrow, is a vector. The magnitude of the displacement is not. Okay? That would be distance. Distance is not a vector. Okay? Because distance is a combination of all the displacements at every unit time. So if you run around the track 4 times, your displacement is 0 vector, but your distance is about a mile, a 1,600-meter run. Okay, so numero dos, number 2. What is the magnitude of the eastward component of the velocity of an airplane flying 612 kilometers per hour in a direction north of east? So I want to be clear about this test. This test is an extremely formula sheet, reference sheet centric test, more than literally any other regions. More than any other regions. In fact, if you call the formula sheet for the math regions reference sheet, because technically it is, isn't it? Even those, you literally need the formula sheet, the reference table, way more in this test than any other test. It's like way more than 50% of the problems. So we're going to do that in a second. But first, I want to talk about a passing problem. We're going to talk about a passing problem right with this problem. So what is the magnitude of the eastward component of the velocity of an airplane flying 612 kilometers per hour in a direction 40.0 degrees north of east, 393 kilometers per hour, or 469 kilometers per hour, or 799 kilometers per hour, or 952 kilometers per hour? Look at this. So this is the velocity of the plane, and look at it having a direction. Now we know that velocity is a vector, but also, so it has a magnitude and direction, but also, if its total velocity is 612 kilometers, no single component of that velocity can be more than 612, which actually eliminates choice 3 and choice 4. Choice 3 and choice 4 get eliminated because they're bigger than 612. You can't have a component of a velocity be bigger than the velocity itself. Okay, which now we actually have what's called a passing problem. Passing problem. And you'll see me shorten this as PP. Passing problem. So what is a passing problem? We have to address that right now. So if you go to the reference table, I'm going to bring that over here. Okay. Ooh, why is that doing it? Stop it. Stop it. Okay. If you go to the reference tables, no, not the reference table, rather the conversion chart for this test. If you look at how many points you need to pass, now some of the tests, some of the science tests you need exactly half to pass, sometimes a little more than half, sometimes a little less than half. And in this case, half of 85 is 42 and a half. So I will acknowledge that you need a slight bit less than half, a slight bit more than half of the points on this test to pass. 48 versus 42 and a half. All right. But for argument's sake, let's say it's half. It's basically half because, of course, 3/4 is way farther than that. It's all the way at 63 raw score. And while guessing on the entire test, which is not all multiple choice, but if it were all multiple choice, you would be at 21. So 40 raw score of 48 is so close to half. We're gonna keep it as that, especially since we can actually eke out a lot of points on the parts that require a written answer. So what is it? Why do I call it a passing problem? Because you basically need 50% of the problems to pass this test. Yes, 50% plus 5.5 more points. Sure, out of 85 questions, right? So half. So you need 50% of the points to pass the test, which means that if you get to a problem and you've eliminated 2 answers, now you have a 50% chance of getting it right. And if you do that for a certain fraction of those questions, that certain fraction of those questions neither leads you towards a passing grade nor a failing grade if at that point you make a wild guess. And the beauty of it is that if you turn a problem into a passing problem, you could actually use test taking strategies to get even closer to passing the test, because you could use test taking strategies to increase the probability of getting the question right beyond 50%. Like, for example, in this case, I see that 612 kilometers is the magnitude of the velocity, and they want to know the eastward component if the velocity is 40 degrees north of east. It's north of east, not east of north, north of east. So I have to go from east. Now I lost a little bit of my color coding here, but for the purpose of not recording forever, let's fix that. Okay, so this is a 40-degree angle. So why do I mention test taking strategy? Well, here I remember from either my math class or my physics class, because I've been doing 30, 45, 60 degrees and trig for an extremely long time. I remember that cos 45 is radical 2 over 2, which is around 0.707. So the answer here, since I'm looking for the eastward component has to be bigger than 612 cos 45, or in other words, bigger than 612 times 0.707. 612 times 0.707. So now this is what I'm doing, is I'm making an estimate for the answer, and I get 432. The answer has to be bigger than 432, making this one the correct answer and this one the incorrect answer. And now, even if I don't know how to do this problem, I know the answer by making an estimate with a lower bound. So now, how do I actually go about this question? Is there an answer that is there something in the reference table that I could use? Yes. And by the way, I'm going to be doing a lot of scrolling, okay? And I'm going to do my best to not overly scroll, okay? But here is on the reference table the formulas that you need to do this question, okay? So if you see on the reference table, and I know that this might be small on your screen, but if you see on the reference table, I have the right triangle trigonometry here, c squared equals a squared plus b squared, and I have sine of theta equals a over c, cos of theta equals b over c, and tan of theta equals a over b. The one that I'm a fan of is that b for physics class. For physics class, I don't do this so much in trig class and algebra 2 class, but for physics class, I like b is equal to c times cos theta, and I like a is equal to c times sine theta. I like it that way better because that helps me to remember it. In physics class, it's so much more useful. And so that this side is 612 cosine 40, and this side is 612 sine 40. And they wanted the eastward component. This is the one that I care about. Now, I can't get this any other way other than the calculator. So I make sure that I go to my mode and I make sure that I'm in degree mode, okay? And I get 612 cosine 40, okay? and I get 468.8. Now, 468.8. Um, so V, so this is equal to, now this is a test taking strategy thing that I actually recommend. So I'm going to mention it now. Putting all the decimals now, uh, 468.8191992, and then rounding afterwards, which is 469. Okay. The reason I recommend that way, the reason I recommend putting all the decimals first and then rounding after the fact is uh, because you only get to see me do this once, as opposed to me teaching you in the classroom, right? If I teach you in the classroom, we could go over it over and over and over. But if you're watching this once, I need to give you a way that fixes muscle memory. And if you round incorrectly, I need to tell you one time how to round correctly. And the way I recommend is a muscle memory fixing method is putting all the decimals in first and then looking in the problem and see how many decimals it used. And it used 3 significant digits, so we use 3 significant digits. All right, numero tres, number 3. A car initially traveling at 25 meters per second is uniformly brought to rest as the brakes are applied over a distance of 40 meters. The magnitude of the average acceleration of the car while braking is, okay? Is it 0.31 meters per second squared or 0.63 meters per second squared or 7.8 meters per second squared or 16 meters per second squared? Now, 16 meters per second squared is more than 1 g. That's a big acceleration. But it might be. I mean, brought to rest, a car is brought to rest. In theory, it might be. But now, you know, if I were to remember my coefficients of static friction, not very many of them are above 1. In fact, on the table, on the reference table, none of them are above 1. So I strongly suspect that four is a little bit too big. Now, if you want to use my notation, I actually recommend using my notation. Let's talk about my notation for when I'm taking a test. I put an X next to an answer that I think might be wrong, as opposed to crossing it out right there. You see the I don't know that 4 is incorrect. I suspect that it's incorrect because I think that the acceleration due to friction is probably not going to be more than 1 g, or in other words, not bigger than 10 or 9.81. But that I'm making guesses right there. Now, I also see 25 meters per second. If the acceleration is less than 1 meter per second squared, then I am losing less than 1 meter per second of velocity every second, which means that this car is going to be going towards rest with using these accelerations. So these two are going to be losing less than 1 meter per second of velocity every second, which means it takes longer than 25 seconds to rest. Takes longer than 25 seconds to rest. Where did I get to 25 seconds? From the 25 meters per second. Okay, which means it travels, starting at a velocity of 25 meters per second, it travels way with, turns out 5 y's, way farther than 40 meters, making these, just by a quick estimate, incorrect. Now, notice again with borrowing my notation, I highly recommend borrowing my notation. I know some people have different notations. This one notation is just so quick that it's a one that I recommend. I'm going to show you what I do when I think an answer is right versus when I know an answer is right. You should know when an answer is right, circle it. But when I know an answer is wrong, 1 and 2 are definitely wrong. I cross it out at the number. Whereas choice 4, I suspect that it's wrong, and I put an X next to it. I want to point something out here though. I crossed out 1 and 2, meaning I 100% know that they're wrong, which means that I now have a passing problem. I have a passing problem. So that's a phenomenal thing. This is leading me towards a passing grade. And I know for those of you who are just aiming for the passing grade, this will get you closer to the passing grade, as you can see. And I know that some of you are actually more like aiming closer to an 80. Some of you already are at an 80, want to get a 90, and some of you are already at a 90 and are trying to get to the 95 or the 98 or the 95 or even the perfect 100 grade. And I want to wish you good luck for that. Work really hard at it. This kind of strategy is great for students who are trying to pass. Now, is it great for students who are trying to get that 100 or anyone in between? Actually, yes. Actually, yes. Because I know this is true. I know all the physics on this test. I mean, not surprisingly, I'm making a video on it. I know all the physics on this test. How many do you think I got wrong while I was prepping for it, right? Everyone makes mistakes. I didn't get any wrong on this test because I didn't know how to do it. I mean, I am a full-time teacher, and so I was working, and then I was prepping, and then I was driving, and then, of course, meaning I'm tired, just like you guys are prepping for tests. You're tired too. You're going to be tired when and or feeling a certain way when you're taking the test. So you might just get some questions wrong on a oopsie. So make a booba. So you don't want to make a booba. So actually, this strategy is phenomenal for you if you're trying to get 100 on the test. Phenomenal. But what do you do to actually get the question right? So, and I want to point out though, I just got a passing problem, but I also think the choice four is wrong. So even if I don't know how to do it, which I'm going to show you how to do it, but even if I didn't know how to do it, now I'm gravitating towards answer three because I know one and two are wrong, and I suspect for really good reasons that four is wrong. And so I'm gravitating towards three, which maybe is the right answer. That's a hint. So how do we do this? So now I'm gonna actually from now on, I'm gonna start marking the test how I normally take the test. So I need to say initially traveling at 25 meters per second, I mark this as a VI. Brought to rest. This is a keyword that y'all have to know. To rest. To rest. Rest implies that the velocity is equal to zero. Notice I didn't say VI or VF. Rest means that the velocity is zero. To rest, final velocity is zero. From rest, initial velocity is zero. But rest means the velocity is zero. So to rest, this means VF equals zero. Okay? As the brakes are applied over a distance of 40 meters, D equals 40 meters. So D equals 40 meters. Okay? Now, I'm marking it this way for now, but I'm going to show you a better way of marking it later. The magnitude of the average acceleration, now they're looking for A with a question mark of the car while braking is. Okay, so I want to notice I have VI, VF, and I'm looking for A, and I have D. So I have VI, I have VF, I have D, and I'm looking for A. Now this is where I go to the reference table, and this is the thing that I want to say. I'm not. I like the way physics looked when I took it in high school. I'm not as much of a fan of it the way it looks now. That said, it's because they took a lot of the actual physics out of it, and it's so formula centric. I'm not a fan of that part, but it's an advantage for you. So if, despite it not being something that I'm a fan of, it is an advantage for you. What we're looking for is now a formula that has everything you have or need, VI, VF, D, and A. And there is a formula basically for every problem that has exactly what you have or need. Have or need. Make if you can make it one word, have or need, have or need. That's the way to solve problems. In fact, that's the way to solve problems in math class too. VF squared equals VI squared plus 2AD. Now, I'm not saying that this is the only way to do it. There's actually many ways of doing the problem. And in fact, if you can't find the one formula that has everything you have or need, literally find any other formula because that's one great thing about physics. Physics problems allow for many avenues towards a solution. So I'm going to put these numbers into the equation. VF squared, I got 25 squared is equal to, nope, that's a lie. VF squared is 0 squared. So I got 0 squared is equal to VI squared, 25 squared, plus 2. A is an unknown, and D is 40. Okay, so now I go into my calculator, and I put these numbers in whenever I'm ready. 0 equals 25 squared. Yes, I do use my calculator obsessively. I'm going to simulate that right now, but I'm not going to simulate it for every single problem. I'll be honest, because it's just a little bit too much for you to do, for you to watch. And this video can easily turn into a 1,000 hours long. So I got 0 squared. Yes, if you don't know that what 0 squared is, fine, put that in the calculator. But if you know 25 squared, good for you. I happen to know it, but a lot of people don't. 625. 625 plus 2 times 8 times 40 is 80. 2 times 40, I'm doing this just to simulate it. 2 times 40 is 80. Okay, so 80A. And now I subtract 625. Subtract 625. Don't be ashamed of not knowing 0 minus 625. This is a physics test, not an arithmetic test. I'm doing this only to simulate it. 0 minus 625 is negative 625. Negative 625 is equal to 80A. And if you don't know what negative 625 divided by 80 is, you're normal at that point, because no, neither do I. I can easily estimate it. I could actually calculate it because they're nice enough numbers, but divide that by 80, and I get that A is equal to negative 7.8125. A equals negative 7.8125. And notice I put all the numbers in the paper before I went and rounded to the thing that they wanted me to round to. I got that 7.8. Turned out that my suspicion that 4 was incorrect was a correct suspicion. Okay. Now, there's a lot to say about the crazy numbers that can appear on a test. For example, why are the numbers so crazy? Why not give you answers that are really close to the possible answer? Well, it happens to be that when I took the Regents back in the day, they would purposely give answers that were close to the answer to eliminate students' abilities to make estimates and guess from there. And believe it or not, that was a good thing, because the opposite of that is where the answers are only able to be arrived at through common but faulty errors. So those answers are there because students literally make the mistakes that will arrive at those answers. So what does that mean? It does mean that if an answer is there, the probability of it being very far from the correct answer is higher, which is an advantage, which means that it actually ups the benefits of making estimates. So definitely do make estimates when you're doing these problems. On that note, numero cuatro, number 4, a brick starts from rest and falls freely from the top of a building to the ground. As the brick falls, its acceleration increases and its speed increases, or increases and its speed is constant, or is constant and its speed increases, or is constant and its speed is constant. Brick from rest falls freely. Brick from rest falls freely. I should be very comfortable with free fall at this point. You know, we know the acceleration due to gravity. Due to gravity, which is equal to negative, well, actually, G is the magnitude of, I should say, magnitude of the acceleration due to gravity. And that's why it's positive 9.81 meters per second squared. Positive 9.81, I ran out of space there, equals 9.81 meters per second squared. There we go. Okay. I don't know why it's not, my pen is being weird, but hopefully it doesn't bother us too much while we're doing this. So 9.81 meters per second squared. I know some of you use 9.8 in class, which is totally fine. I know for quick estimates, some of you use 10. Phenomenal choice. Acceleration due to gravity, just a quick 10, and you get a quick estimate, and you can often move on from there. Now, what does that mean? If we know, why did I mention this here? Because we do need to know, based on basic physics, we need to know that the acceleration due to gravity on average on the surface of the Earth is 9.81 meters per second squared, which means that we know that the acceleration is constant. Now, this is a 2x2 problem. So I'm going to quickly, well, no, let me just address this, and then I'll go to another 2x2 problem when I get to it. And I'll tell you what a 2x2 problem is later. So increases, the acceleration does not increase, so I cross those out. but it is constant. So one of these two choices is correct. And now look at this. We have a passing problem. Passing problem. So now, if the acceleration is constant, we also need to know what an acceleration is. Acceleration is equal to change in velocity over change in time, which means since the acceleration is constant and time goes on, that implies, so if A is not equal to 0, delta V is not equal to 0. Because, 0 on the left, 0 on the right. Not 0 on the left, not 0 on the right. That's an arithmetic property. So the speed has to change. So that means that the speed can't be constant, which is great. The speed has to increase. Okay? Notice, by the way, from rest, that's VI is equal to 0. Okay? So the speed increases. Let's move to numero 5, number 5. Which object has the greatest inertia? A 0.10 kilogram baseball traveling at 30 meters per second, a 70 kilogram sprinter traveling at 10 meters per second, a 1,000 kilogram car traveling at 50 meters per second, or a 2,000 kilogram truck traveling at 20 meters per second. Inertia is an interesting concept. Why we address it in physics class, I think it's an important concept. It does cause a little bit of confusion, but inertia, but I want to define inertia here, but I also want to give you the number. And these are both important things. Okay, so the inertia is equal to resistance. Okay, resistance to a change in velocity. That's inertia. Inertia is equal to the resistance to a change in velocity. Now, I'm a big dude. You might not be able to tell. This bookshelf is 6 feet tall, so I am 6 feet tall. And I'm actually about 217 pounds. Wish I was a little lighter, like a lot of people. But point is, I have a whole lot of resistance to a change in velocity. So if my nephew comes to push me, I might not fall. I might not move much. But if my niece, who's about 5'8" and 12 years old, comes to push me, I might tumble a little bit, right? So what makes it different? Not their heights necessarily, but their own masses, and actually my own masses relative to them depend. But the thing that affects that is how hard they can push. Well, what is proportional to my change in velocity over time? Actually, my mass. So inertia has to be proportional to mass in theory, right? Actually, though, here's the point. This is the big point. You need a number for what inertia is. Inertia is equal to, without exaggeration, inertia is equal to mass. Period. Inertia is equal to mass. I am not talking about a rotational situation where you have a moment of inertia, which is not inertia. A moment of inertia in rotation is one thing. Inertia is a different thing. Inertia is equal to mass. Your resistance to change in velocity is literally your mass. This bottle of Fairlife, which I'm going to talk about in about 30 minutes or so, has a certain mass. That's its inertia. And this pure protein bar, which has a certain mass, which I'm going to talk about in about 30 minutes too, has a certain inertia. And I, being a big 6 foot tall, 270 pound dude, I have a certain amount of inertia. How much inertia do I have? Well, in kilograms, my mass is about 100 kilograms. It's actually really very close. About 98 kilograms, 97 kilograms. That's my inertia, my mass, my mass. So which object has the greatest inertia? Actually, the velocities don't matter. The thing with the greatest mass has the greatest inertia. So it is that one. There is no eliminating there's no process of elimination. You literally just have to know what inertia is. Now, what if I didn't know what inertia is? How could I have eliminated any of the choices before we go to number 6? If you don't want to hear the explanation, strongly advise you to listen to the explanation, because that's the important thing, isn't it? Well, I would say that the things in between have likely less inertia. So the 70 kilogram sprinter traveling at 10 meters per second, I would immediately eliminate that one, because even if I didn't know what inertia is, this one has a smaller mass and a smaller velocity, like if I thought velocity might matter, uh, I I see 1,000 kilogram car traveling at 50 meters per second, and I see a much lighter object traveling at 30. I think this one, and least to greatest, number two would never be on the list. So I would have a 1 in 3 chance now of getting it right. That's how I would eliminate a choice here. But that said, numero seis, number six, an unbalanced force is always necessary to keep a body at rest, keep a body moving with constant velocity, change the speed of a body, or change the position of a body. Okay, so now I know that a lot of students would say this this problem has perhaps uh, two answers, um, but it doesn't. Okay, um, and it's important. It's important to know that. How we eliminate some answers though. First off, unbalanced force is not required to keep a body at rest. I would personally eliminate that from process of elimination. This a body at rest, the F net is equal to zero. Okay, for sure, F net is equal to zero for a body at rest. I know that. So I do need to know for this problem though what an unbalanced force is. So, but by the way, by eliminating choice one, I now have a 1 in 3 chance of getting it right. So the reason I eliminated choice one is a process of elimination strategy. But now, what is an unbalanced force? Unbalanced force uh, is F net is not equal to zero. That's what an unbalanced force means. So you might have a pushing force, a pulling force, and a gravitational force, an electric force. You might have um, a spring and a string acting on it, while I don't know, a rocket is flying off of the thing. All of those forces together might literally add up to zero, and then the forces are balanced, and then the thing is um, then what happens in that situation if the forces are balanced? Well, actually, if the forces are balanced, then the acceleration is equal to zero. Notice that if F net equals zero, that means that mass times acceleration is equal to zero, which means that, and since the mass in principle wouldn't be zero because you're acting on an object, that means the acceleration is equal to zero. So notice that if you have an unbalanced force, if F net not equal to zero, that implies by Newton's second law that ma is not equal to zero. And if assuming, well, now m can't be zero at all, which this implies that a is not equal to zero. So notice that unbalanced force implies that there is an acceleration, which implies now that we know that keeping an object moving at a constant velocity, this implies that a is equal to zero, a equals zero, which implies that F net is equal to zero, which implies that you have a balanced force. Okay? So it's not this one. So what about choice three or choice four? Change the speed of a body or change the position of a body? Well, some students might feel, and I've heard arguments about why like choice four might be correct, because if you change the position of the body, you need something, and one of the things that could change the position of a body is an unbalanced force, but that's just one of the things. In fact, if just v is not equal to zero, then the position changes. Right? If v is not equal to zero, then the position changes. V can be zero not zero while the net force is equal to zero. This has no effect. This doesn't speak about a. Therefore, and a can be zero even if v is zero. Think about a car coasting at a constant speed. Put your cruise control on at the speed limit, of course, or 5 miles above the speed limit, which is technically well, I won't talk about philosophies about driving, but there's things to be said about what technically is the safer speed. That said, if you put on your cruise control, you're going at a constant speed, you're a constant velocity on a straight road, then your acceleration is zero, even though your speed is not zero, but the forces are balanced in that situation. So that's not the answer. Therefore, changing the speed of the body is the answer, and this implies that delta v is not equal to zero, which implies that delta v over t is not equal to zero, which implies that a is not equal to zero, which implies that f net is not equal to zero. And that's why choice 3 is the answer. If you feel so far that this video is helping you, I do appreciate the subscribe. Again, this video may have ads on it. I don't get a single penny of it until my subscriber count, and this is my YouTube channel, Juan Tutors, and of course my website, JuanTutors.com, if you need tutoring. I currently have 850 subscribers. Last time I made a video, I had 844, so that subscriber count's going up. I need that to be 1,000, and that's how many views I've had: 128,150 and 128,150 views. And none of those have gotten me any money because all of the money goes to YouTube. I can't get the ad revenue until I get to 1,000 subscribers and 4,000 hours of views in a single year. So I do appreciate the subscribe. All that will do for me is get the ad revenue, at least some of it, in my pocket. And I do this for a lot of reasons. This teaching and tutoring and the videos. One is that I've always wanted to have a component of my videos be accessible to people who grew up like me, very poor, and can't afford tutoring. I've literally never in my life had a tutor. So despite that fact, I happen to be very highly sought after, and I appreciate that. But what that means is that I tend to price out a lot of people who grew up like I did. So if you do appreciate the quality of this video so far, please do hit the subscribe button. It does help me a lot, and it does help a lot of people a lot because it actually provides me some income so that this piece of free content can remain free forever, and it will remain free forever. On that point, number 7, space probes launched from Earth send information back to Earth from space in the form of mechanical waves, sound waves, longitudinal waves, or electromagnetic waves. So definitely, this is one problem that I highly recommend trying on your own before you hear how I do it, because some of these just don't quite make sense based on the fact that it's a space probe in space sending information back to Earth through empty space. That said, I'm not going to pause on any other problems because it's YouTube. You literally have a pause button. So I'm going to move on to the answers. I know that they can't be traveling through any medium because the space probe is in space, where there's so little air that you can't even transmit really almost anything, sound even, for example. So mechanical waves can't be it, and sound waves can't be it. And now I have a passing problem because I've eliminated 2 choices, even not knowing how to do it necessarily. And then I have to say to myself, longitudinal waves or electromagnetic waves. And then the question is, wait, are electromagnetic waves longitudinal waves or not? And I can't remember, But the thing is that that space probes shoot to Earth, the only waves that you have ever dealt with that travel through space, gravitational waves, which you've heard a lot about in the news, but still hasn't appeared in a Regents. Maybe it will way in the future, but it still hasn't in the Regents. Gravitational waves pass through empty space, and electromagnetic waves pass through space. So the only one that really makes sense for passing through space, so gravitational waves and electromagnetic waves travel through space, travel through empty space. Leaving electromagnetic waves as the only answer that really makes sense. However, electromagnetic waves, are they longitudinal waves? No, these are actually transverse waves. Transverse waves go up and down relative to the direction of motion. up and down relative to the direction of motion. You could say, wait, how do electromagnetic waves travel up and down relative to the direction of motion if they're going in one direction and there's nothing that's traveling? The thing that goes up and down relative to the direction of motion is the magnitude of an electric field and the magnitude of a magnetic field. So that's what that's what you could see going up and down. So longitudinal waves includes sound waves. So it's not longitudinal waves. So electromagnetic waves is the only one that actually makes sense for the problem. On that note, numero ocho, number 8. A ball is thrown from level ground at an angle of 55 degrees above the horizontal and lands on level ground. Neglecting friction. So from neglecting friction, if the ball is thrown again at the same angle, but with a larger initial speed, the ball will travel higher and the same distance horizontally, or to the same maximum height and farther horizontally, or both higher and farther horizontally, or to the same maximum height and the same distance horizontally. This is a 2x2 problem, so I will address what a 2x2 problem is. I highly recommend not drawing this, but do understand what I'm drawing here. So I'm going to draw a box here. And so I draw this box, and what's in this box? So I notice that there's really, in the choices, there's not one of 4 choices being asked. There's actually two questions being asked. And the questions here are higher and the same distance horizontally. So higher dy. So I'm going to call this, I'm going to call if dy goes up or dy is constant. And here, the same distance horizontally or the same or farther horizontally. I'm going to say dx goes up or dx is equal to constant. Now I notice that choice 1 says higher, dy higher, and the same distance horizontally. So this is choice 1 right here. And then choice 2, the same maximum height. So dx is dy is constant, and farther horizontally, so dx up, this is choice 2, or choice 3, it goes both higher and farther horizontally, that's choice 3, or choice 4, the same maximum height, dy is constant, and the same distance horizontally, so choice 4. So again, you don't have to draw this box every single time. What I want you to recognize is that there were actually 2 questions separately being asked, which means that you could address both questions separately. If you try to address both questions simultaneously, you might actually get lost in the mud. But if you actually answer both questions separately, then you can get the answer right. So the question is, did the ball go higher up or the same distance up? And also, did the ball go farther horizontally or the same distance horizontally? Answer those separately. Did the ball go higher up or the same distance up? And did the ball go farther horizontally or the same distance horizontally? Answer those separately and you get this answer. Now, what I noticed is that what didn't change, the angle didn't change. Okay, so what only changed, and then dy, the displacement in the y direction is equal to 0. And neglecting friction, so this is a non-frictional thing. If the ball is thrown again at the same height but a higher initial speed, the ball will travel what? So why did I put this water feature picture into the problem? Now, this water feature is slightly above the ground, but if I put this point here as the same level of the water feature, then I notice I put this one because it actually draws out the parabolic path that the water molecules take on their way out of the faucet and into this pond. No, so notice that that is a parabolic path. What happens if I take the water, if I turn the water rate down, I mean, I kind of know what happens. This is the part where I talk to you about knowing what happens in real life. If I turn the water rate down, then you just kind of get this little dinky water feature that sucks. That's not too fun. It doesn't go as high, it doesn't go as far. And if I turn the water up a tremendous amount, then I get this crazy water feature that goes out of the picture and goes really far. All right, before getting to the before getting into the pool. So this is one of those things where I said, if you don't know how to do this problem in a real life situation, then you can answer the question using numbers and algebra and physics. Then you can answer the question using your own personal intuition. Notice that if turning up the faucet isn't intuitive for you, turning down the faucet might be the one that gives you the intuition. If you turn down the faucet, then you get this pretty dinky water feature, don't you? It doesn't go quite as high, it doesn't go quite as far. Nobody would travel to see your amazing water fountain, but they would travel if you had a really strong water feature in the middle of your area. So definitely, if the ball is thrown again at the same angle but with a initial speed, larger initial speed, both of these are going to go up. So first off, the when I said 2x2 problem, is the water going to go higher or lower? This is where, or the same. This is where I say, oh, if I turn up the water feature up, it's going to shoot the water way higher into the air. So I know in my intuition that the dy is going to go up. So this one makes sense and this one makes sense so far, but these don't make sense because the vertical distance that the water travels can't be constant, or the vertical distance that the ball travels can't be constant. Now, what about this? I might be breaking my intuition on the horizontal distance, but then I think about this water feature again, and I see if I turn the water feature up, it doesn't give me the intuition that I want it to have on the horizontal distance. But then I think about what happens if I turn the water down, and I realize, oh, but if I turn the water down, the horizontal distance definitely goes down. So if I turn the water feature speed up, then the distance has to go up, and that's what increases my intuition on that one. And so this one, I the horizontal distance has to go up. Um, so that one these make sense, and then this one, the horizontal distance staying constant doesn't make sense. And the only one that has two check boxes is 3. I initially crossed out 2 and 4, but now I crossed out choice 1, and the only one remaining as making sense is 3. That's what a 2x2 problem is. And I highly recommend recognizing a 2x2 problem for what it is, because a lot of problems can be split up that way. And trying to analyze the 2x2 problem as a 1x1x1x1 problem, meaning 4 different choices, then you have to sit there and try to analyze 2 things simultaneously, and that doesn't really work. 2, in fact, we actually teach you to not do that, because we teach you to do the vertical direction and the horizontal direction separately. So if you're trying to analyze both simultaneously, well, you're actually doing the opposite of what was recommended in physics class. On that note, numero 9, number 9, a photon collides with an electron as represented in the diagram below. Incident photon, electron, an arrow, and a scattered photon. I look at the diagram and then I let that process how it processes in my brain, and then I move on, and then I come back to the diagram later. After the collision, the electron recoils and the photon is scattered in another direction, excuse me, with a longer wavelength than the incident photon. The increase in photon wavelength results because during the collision, the photon loses energy to the electron, or gains momentum from the electron, or loses some speed, or generates a magnetic field. Now, there are some physics things that you need to know to be able to answer this question, but they didn't talk about a medium. There's no change in medium. You do need to know the speed of light is a constant. You need to know that c equals the speed of light is a constant, okay? You do just 100% need to know that, okay? There is no avoiding that fact, okay? So because of that, the photon, this is what's happening. Now, another place where students lose points is that they don't realize that they're asking about. Are they asking about the incident photon, the scattered photon, the electron? They don't answer the question about the thing that they asked about. They asked about the photon, the scattered the photon. Did the photon lose speed? This is going to be crossed out, insta crossed out. In fact, I'm going to put another X next to it because, and another one. Oh, look at that. Oh, look at all those X's because this is impossible. C is equal to a constant, right? So many crosses out because no, that can't be it. If you didn't know that, now you know it, and you have to obsessively know it. The speed of light is a constant in a given medium. Okay. Are you in a vacuum? Speed of light is 3 times 10 to the 8th. Are you in uh, glass? Well, the speed of light might be a different number than outside of the glass, but it's a still constant within the glass. Are you in a diamond? Are you in water? All of those different media have a different speed of light, but they're all constant in that given medium. Okay? So speed of light is a constant. So now the next one, does the photon, um, the increase in photon wavelength, does it happen because it loses energy to the electron, or does it gain momentum from the electron, or it generates a magnetic field? Excuse me, let me take a sip of this coffee. Ooh, that's fun. Now I'm not deleting any coughs, any sneezes, because I realized um, well, first off, a lot of people appreciate my videos, and they always ask me, "Are you doing a video in this? Are you doing a video in that?" And then the thing that ends up happening is um, I end up spending so much time editing videos that I lose time to do more videos, and I end up like sometimes I'm recording like 2/3 of a second video, time runs out, and I don't finish the video. Whereas instead, if I just upload the video unedited, then I can make more of them. Now, that said, if you look over here, the energy of a photon is actually proportional to its frequency, and it's inversely proportional to its wavelength. Okay, so if a wavelength has increased in wavelength, then it has less energy. Okay. I just want to do a quick scroll to see if there's anything that I want to mention here, like momentum. I don't see anything about the actual momentum of a photon in formulas. Okay. Just wanted to check and be sure. I didn't recall some from before either. Okay. Now that we've crossed out number 3, so does it lose energy to the electron? We do need to know the energy is equal to, according to the formula sheet. Let's go to the formula sheet. Let's go to the modern physics section. Modern physics section. So there is a formula that relates the energy and the wavelength. Okay. So, ooh, that's huge. Okay. I don't know why the letters got small there in the writing, but hey, okay. So there is an equation relating the energy and the momentum right here. Okay. So if you notice, the energy of the photon is equal to hf and is equal to hc over lambda. So energy of a photon is inversely proportional to the wavelength right here. Which means that if the wavelength goes up, that implies that the energy goes down. Okay? And so this one is looking very good. Now, what about gains momentum? Does the photon gain momentum from the electron? Well, the electron, according to the problem, is there, and then it recoils. Okay, the electron gained. The electron gained momentum. Okay. Well, how can the electron gain momentum and then the photon also gains momentum? The photon, which is here, it has to lose momentum. Okay, the photon actually gains momentum if its frequency increases and its wavelength decreases. So it doesn't gain momentum; actually loses momentum. Do you need to know the formula of a momentum of a photon from this? Um, no, you actually don't, because you just need to know the law of conservation of momentum. If the electron gained momentum, then the photon had to lose momentum. Okay, and so that one doesn't work. So that's by the law of conservation of momentum. By the law of conservation of momentum, which says that pi is equal to pf. Okay. Now the fourth one generates a magnetic field. The photon does not do that. It doesn't like generate a magnetic field all of a sudden. In fact, a photon is a traveling, oscillating electric and magnetic field. So uh, that's the wave part of a photon, the traveling and perpendicular electric and magnetic field. So it does not generate a magnetic field. It already has one associated with it that fluctuates. But now the electron happens to generate a magnetic field if it's moving. That's fun, but that's not what the photon did. Okay, so therefore the only one that makes sense is that it loses energy to the electron. On that note, numero 10, number 10. What is the weight of a 60.0 kilogram student on the surface of the Earth? The weight of a 60.0 kilogram student. This is where I would gladly make a quick estimate. The weight is equal to mg. Uh, you know, or Fg equals mg, negative mg, whatever you wanted to use. If you did a quick 10 for g, remember g is a 9.81 meters per second squared, or about 9.8 meters per second squared. And those of you who are taking AP physics actually know and are comfortable with changing that 9.81 to a 10. Of course, the 9.81 is the more accurate answer on average. But if you do the quick 10, 60 times 10 is equal to 600. And so the answer's got to be close to 600. Eliminating the answers, and you're done. Any answers that's not even remotely close to 600. But now, how do we actually do this? Again, Fg is equal to negative mg is equal to negative 60.0 kilograms times 9.81 meters per second squared. And now I said I just got to be clear about this. I'm not going to go. Am I going to go to this formula sheet for every single formula? I am going to try, but I think there was already a problem where I didn't. So I just do want to address again that that this is a very formula centric test. And when I say it's more formula centric than other regents, I mean that to an extreme. Why did that not paste? Okay. I mean that to an extreme. Like, yes, it's more formula centric than uh the like algebra 1, geometry, the algebra 2, chem regents, physics regents, um but also by like more than 100%. Like it's more than double the number of the formula centricity than any other test that you take as a Regents. So you have F equals ma. Sorry, this is the centripetal acceleration, but let's see. F net equals ma. Where's F? There it is. I'm used to writing F net equals ma, but for some reason the formula sheet prefers A equals F net over M. Sure. But now we have the formulas. If you use this formula here, if you want to use it that way, sure. 9.81 is equal to, now notice that mine has a negative because I treated FG as a vector. When you're doing vector problems, that negative really super duper matters. Okay, so 9.81 though equals FG over 60.0 kilograms. And then so if you multiply both sides by 60.0 kilograms by 60.0 kilograms, meters per second squared. I missed the units there. Why do I put the units? Because later on when you do problems that require you to show work, you got to put the units. Okay, so FG is equal to what this calculator is going to say, which is going to say 581 times 9.81. 588.6. 588.6 newtons, which is around 5, 8. The 6 causes us to round the next 8 up to a 9 newtons. And there's where that answer is. Okay? Notice a quick 10 got us the answer right away. Numero 11, number 11. A 120 Newton box is pulled by a 48 Newton horizontal force across a horizontal surface at a constant velocity. The coefficient of kinetic friction between the box and the horizontal surface is 0.041 or 0.40 or 0.67 or 2.5. Now, I'm going to use my process of elimination skills here. I see that the force pulling the box this is Fg. So now I said that I was going to put another way of making my numbers written. I write it here on the side. Fg is equal to 120 newtons. I have the pull force, F pull, is equal to 48 newtons. And then across a horizontal surface at a constant velocity, F net is equal to 0. Okay? I have that Fn. Since it's going a horizontal surface, force normal is equal to 120 newtons. Up, down. And now I'm going to say let's say to the right. Okay? Because it didn't address that. So that makes that F friction is equal to 48 newtons left. And do I draw a diagram? Absolutely. 120 newtons. I got a F pull 48 newtons. I got this is F pull. So I got a force of friction 48 newtons. And I got the force of gravity negative 120 newtons. And I got the force normal. I got 120 newtons. Okay. So now the coefficient of kinetic friction, where do I use my estimates? 0.041 is an extremely small coefficient of friction. This would require a very small force to pull. So I'm going to cross that one out. And then 2.5, this would require a pull force greater than Fg. Okay? Which causes me to cross that one out. So now I have a passing problem. So now if I didn't know how to do this problem, I would maybe take a guess from that. But as you know, what do I tell you about this test? It's a very formula sheet centric test, and this is a friction problem. I'm gonna zoom out a little bit so I could see the formulas a little better. There's a friction force formula right here. every formula that you need is on the formula sheet. I think I want to say that that's 100% true. It might. I think there was one problem one time that for some reason I just didn't see how to do it on using the formula sheet, and because of time, I kind of ran out of time and didn't successfully discover a way of doing it without the formula sheet. Sorry if you couldn't see my drawing there. I just scrolled to make it more visible. But anyway, so I think though every single problem, every formula is there on the formula sheet. Not only that, every problem technically can be done with just like one formula. Um, and in fact, the ones that require like two formulas tend to be separated as two problems. So do know that. So does that mean that you should always look for the one formula method? No, I think that the better way to think about it is to find any way that you could do the problem and get your answer that way. So force of friction is equal to mu times the force normal. So I got that the force of friction was 48, and that's equal to mu times the force normal, 120, divide by 120, divide by 120, and I get that mu is equal to 48 over 120. And I need two digits of accuracy. 48 over 120, 0.40, 0.4. Another thing I could have done for an estimate is that 48 is less than half of 120, making that one the right answer, making this one incorrect. So there are ways of doing the problem, even if you don't remember. Numero dos, number 12. Box A has a mass of 10 kilograms and is at rest on a shelf that is 1.5 meters above the floor, right about there. Box B has a mass of 20 kilograms, double the mass, and is at rest on a shelf that is 3 meters above, well, actually way above my head of the floor. Compared to box A, box B has a gravitational potential energy relative to the floor that is 1/4 as great, the same, twice as great, or 4 times as great. I would think about this problem a little bit. How mass affects gravitational force, gravitational potential energy, and how height affects gravitational potential energy. So, but that said, mass B is equal to twice mass A, which doubles the gravitational potential energy. And then also the height of B is equal to double the height of A, which doubles the gravitational potential energy. So this one is looking very good to me. This one is not looking good to me. This one is definitely not looking good to me at all. Uh, now, uh, but I'll cross this one out here, and I'll cross this one out here. And let me tell you why I would cross this one out here. The height has a doubling or halving effect because it's a multiplication by 2. And also the mass has a halving or multiplying or halving or doubling effect because it's again another multiplication or division by 2. So the answers, depending on what order they put the numbers in, could be a quarter, the same, 2 times 2, which is double 4 times, or 2 divided by 2, which is the same, or divide by 2 divided by 2, which is a quarter. So I strongly suspect though that based on just what I wrote here, that the answer is going to be 4 times as great. Now, is this a formula sheet problem? Actually, yes. I like the ones that force you to do the math without having numbers, but this one does, by luck, it has the numbers. So, gravitational potential energy, where's the gravitational potential energy formula? Let's see, here it is on the formula sheet. Okay, so here's the gravitational potential energy formula. So PE1 is equal to 10 PEA, I should say, because it's mass A, 10 kilograms times G. I'm going to use 10 for ease because I can. I could use 9.81 times H, 1.5 meters. And I could put that in my calculator. Now, I know that might scare you for those of you who are so used to using 9.81 over and over and over, or who are used to using 9.8 over and over and over because your teacher never let you deviate from that. Whatever it is that you want to do, take my 10 and replace it with a 9.81, or take my 10 and replace it by a 9.8, put it in your calculator that way. So 10, but I just need the quick estimate, 10 times 10 times 1.5, and I get a 150. And this is a joules, okay? And then PEB is equal to 20 kilograms times G, 10 meters per second squared, and times H is 3.0 meters. And then if I put this in my calculator, I get 600 joules. Again, I'm not going to simulate every plugging in. You know how to plug into a calculator. Use your calculator, though, obsessively. This is not an arithmetic test. This is a physics test. I know students who know how to do the problem and get it wrong because they didn't bother putting it in the calculator. But notice that 56, this is 4 times 150 joules. Okay? So it is 4 times as great. Now, another place where students get this one wrong, before anything, they look at the comparison, but they answer the question about the wrong object. They answered about, the question is about box B. The answer is about box B. So we might have to make sure that we answered about box B. It's not a trick question to ask about box A. They asked about box B though, so it is 4 times as great. Okay? So número 13, number 13, a 0.10 kilogram yo-yo is whirled at the end of a length of string in a horizontal circular path, okay, of radius 0.80 meters at a speed of 6.0 meters per second squared, meters per second, sorry. The magnitude of the centripetal acceleration of the yo-yo is 4.5 meters per second squared, or 7.5 meters per second squared, or 23 meters per second squared, or 45 meters per second squared. So now you may have a better intuition than I do about the magnitude of centripetal acceleration, but I don't have an answer, me personally, that I want to eliminate. I do see an acceleration of 45 meters per second squared, and 23 meters per second squared, and 7.5 meters per second squared, and 4.5 meters per second squared. And I feel like uh, I I have a feeling that that 4.5 is going to be a little bit small. But again, for some reason, when I have a small circle, my intuition starts to disappear. So, do I have one that I cross out immediately? No. I do. Do I have things that allow me to make some estimates? Well, you could think about the radius of the circle, okay, and double that, and then think about how long it takes to go around a circle, or the speed of the circle. Uh, there are ways to eliminate answers. So there are ways to eliminate some of these smaller answers. Uh, that said, though, I go for the formula sheet. So first off, I label some things M. Length of string, this is R, right? Um, this is a speed of V, okay? And then they're asking for the acceleration, centripetal acceleration, AC, okay? So let's look for a formula that has all of that data. And it turned out that the mass was not a necessary quantity for this one. Now, I want to talk about necessary and unnecessary quantities for a moment, if I may. Turns out that the mass was not necessary in this problem. Do I ever want you to get into the habit of crossing out unnecessary information? When I say no, I want you to pretend like I'm screaming it, like with an unreasonable amount of passion. Do not cross out unnecessary information. When you were in 5th grade and 4th grade and 3rd grade, we in the education system did you a disservice by teaching you to cross out irrelevant information. It turns out that almost after that happened, we created problems in which almost every test document product has every bit of information relevant. Now, what counts as irrelevant information? I mean, is it a yo-yo, or is it a pail of water, or is it a rock? That doesn't matter as much as the fact that it's a mass. Now, I pointed out here that it turned out that the mass was not a relevant thing. Why am I telling you don't cross that out? Well, the reason is it's not that that piece of information was irrelevant. A piece of information is not irrelevant just because we're not used to it, using it. A piece of information is not irrelevant just because we're not using it. A piece of information is irrelevant only if there's literally zero avenues towards solving the problem in which that number is being used. There is a way of doing this problem in which you use the mass. And what this mass did for a lot of students is it gave students a second avenue towards solving the problem. They get the centripetal force, and then from the centripetal force, they get the centripetal acceleration. Yeah, so there's a second avenue of doing this problem using the mass. We are not going to use the mass because we are just using a different formula that's on the formula sheet. Do not look for, don't look, especially don't look for irrelevant information, but don't cross it out either. Okay. In fact, go ahead and assume that all information is relevant. And if you ever get to a point where you didn't use a piece of information and you got an answer, start to question it. Question your answer. Don't assume that it's wrong, but question whether you did it right and check if you did it right. And if you didn't use a piece of information, then great, you found a way to do it without the irrelevant information, without that piece of information. But it's also useful to say, when you're stuck on a problem, to say, is there a piece of information in the problem that I didn't use? And then force yourself to use it somehow, using legal math, using legal physics. But that said, I have that AC. I'm looking for AC, but I have AC is equal to V squared over R, which is equal to 6.0 meters per second squared divided by R, 0.80 meters. Okay, so why did I have a feeling that 4.5 was going to be too small? Again, because I had a big velocity and a small radius that I was dividing by, a tiny radius that I was dividing by. So yeah, at this point, I already have enough information to eliminate 4.5 and 7.5 because I see the answer is going to be bigger than 6 squared. And actually, I can eliminate 23 because the answer is going to be, again, bigger than 6 squared. Because I happen to know that if I divide by 1, I get the numerator, which is 36. And so if I divide by a number bigger than 1, I get a smaller number. And if I divide by a number smaller than 1, I get a bigger number. So 6.0 squared is 36 divided by 0.8. And I know a lot of students lose intuition on the arithmetic. Wait, I'm dividing by 0.8 and I get a bigger number? Well, the good thing is you're not taking a math test. You're not taking an arithmetic test. You're taking a physics test. Yes, it is true if you divide by a number smaller than 1, the ending result is bigger than what the numerator was. And hopefully that gains you a little bit of intuition. So 45 meters per second squared. Okay? And that's my answer. Número 14, number 14. A 4.0 kilogram mass is initially at rest on a horizontal frictionless surface. A constant 2.0 Newton force to the east is applied to the mass for a 5-second interval. As a result of this action, the mass acquires a velocity of 10 meters per second east, or a velocity of 10 meters per second west, or a momentum of 10 kilogram meters per second east, or a momentum of 10 kilogram meters per second west. Yeah, I would highly suggest starting to eliminate some answers on your own. And I'm not going to say that for every single problem, again, but the problem really has a ton of information that you can use to eliminate some choices. 4 kilogram mass, and I'm going to draw my diagram, initially at rest on a horizontal frictionless surface, so 4 kilograms. So there's no friction. So Fk equals 0, equals Fs, S for static friction. A constant 2.0 Newton force to the east 2 newtons force to the east is applied to the mass for 5 seconds. T equals 5 seconds. What, as a result of this action, this mass acquires A. Now, here's the thing about process of elimination. If you don't eliminate the velocity gains to the west, then this may be a nice, and of course initially at rest, so vi is equal to 0. Then this is an important point that to note that a mass, a net force produces an acceleration in the direction of the net force, in the same direction of the net force. So momentum is not gained to the west, and that eliminates choice 1 or 3. Notice, by the way, this is a 2x2 problem, as I mentioned before. The question is the gain a velocity of 10 meters per second or a momentum gain of 10 kilogram meters per second? And then separately, is it east, choice 1 and 3, or west, choice 2 and 4? So notice that that is a 2x2 problem. Is it east or west, and is it a velocity or momentum gain? Okay, so what do we need to know? We need to know some formulas. Now, I said that each problem is a one formula problem, and each problem that is a 1 point problem is a one formula problem, and I'm not taking that back even on this problem. But the thing is that the answer choices are separate formulas. So this is this is one of the topics that a lot of schools don't address much, and the reason that a lot of schools don't address it much is that there's avenues to escape it. But what's J over here? And we go over here and we see J is equal to impulse. It turns out that when you're in space, and when you're shooting a rocket to outer space, and you have a satellite in outer space, and you want it to do certain things, the thing that matters more in space is impulse. It could be the tiniest, most minute force that you produce onto an object that's the size of a house. And actually, that's more satisfactory, often more satisfactory when you're already in space, more useful than, like, for example, having a rocket that's shooting a ton of energy out with a massive force. Because why? Well, unlike on Earth, where we care about arrival time, in space, the distances are so large that large forces or small forces have less of an effect on arrival time than the force relative to the amount of mass being used in fuel. But on Earth, time is the bigger factor. So it actually turns out that like if you look at a train and you look at its acceleration, um, you care about its velocities and its average velocity, really, when you're talking about arrival time. So you really care about how much time it spends at the station and what its maximum speed is. So even in actually not for, and you care about the acceleration in that case because train stations tend to be close to each other. That said, let's actually just start using formulas. Can you escape this formula here? Yes, because you could use you could use acceleration to get, well, you could use F net equals ma to get the acceleration. Then you could use the acceleration and the time to get the final velocity. But I want to point out here that the impulse is F net times delta t. Let's see if we change a momentum by the amount that they said. So F net is 2.0 newtons, and the delta t is 5 seconds, and this is equal to an impulse of 10 newtons times seconds. And if you notice, that's a change in momentum. We see that the momentum did change by 10 Newton seconds. Now, I know Newton seconds doesn't match the units that they gave, but delta P has units 10 kilogram meters per second. But if you notice, Newton has units 10 kilograms meter per second squared multiplied by second, and second cancels. One of the seconds cancels in the denominator, is that's 10 kilogram meters per second. And so the answer does match choice 3. Now, why is the answer not 10? Well, because this one didn't take into account the 4 kilogram mass. If it was, if you notice, a 4 kilogram mass being pushed by a 2 Newton force, why I'm not liking choice 1 as an answer choice. If I were to do more process of elimination, I would note that a 4 kilogram mass being pushed by a 2 Newton force, this would gain 1 meter per second every 2 seconds. 4 divided by 2 is 2, so it would gain 1 meter per second of velocity every 2 seconds, which means its final velocity is going to be 2.5 second final velocity. If I had to do a quick mental estimate. So but that's why I would have eliminated choice 1 in my quick estimating strategy. So the answer is choice 3. Number 15, número 15. A motor lifts a 1.2 times 10 to the 4th Newton elevator 9.0 meters in 15 seconds. The minimum power output of the motor is 8.0 times 10 to the 2nd watts, or 7.2 times 10 to the 3rd watt, or 1.0 times 10 to the 5th watt, or 1.6 times 10 to the 6th watts. Okay, so I would strongly advise you to look for a formula in your formula sheet. In fact, I'm going to give you another strategy for watching this video. If you are just really super insistent on not doing the problems, again, I am a highly sought after tutor, and I'm giving you advice not as a teacher who likes to give busy work, but as a tutor who wants you to get the best grade possible. If you want another strategy for getting the best grade, if you're watching this video and you insist on not doing the algebra, spend your time looking for the formula. Okay, so here's a force, and this is the distance, and this is a time, and they want the power, capital P. So the number that we're looking for is the power. So I'm going to look for a power formula, and I see this one. Here's a power formula. And by the way, if you don't know what these letters mean, again, you are in a physics class, so I do hope that you know what the letters mean. But the beauty of this formula sheet is that all the definitions of the letters are on the right. Look at the mechanics letters. If you scroll up slowly, look at the geometry letters, look at the modern physics letters, the waves letters. Like, they actually tell you what the letters are in the formulas. Here's the electricity letters. They tell you what the letters are, which is nice. So if you're looking for an equation and you're like, what's the letter for power? You could look for the word power here, and you find it, that's capital P. Then you look for capital P. Then you probably know that F is force, but then distance or displacement, T time, what's W? W, work, like et cetera, et cetera. Like, you could look for the letters here and then look for the equation here. So it is a nice reference table, so that if you've never taken physics, you're literally never taken physics, and you decide you just want to take the Regents, go to the reference table, okay? So power equation is right here, and I see force, distance, and time, and that's this part here. So I got power is equal to force times distance over time, and they're looking for the power. And I think if I had to just make an estimate, I would say the power of over 1,000,000 watts of power is probably too big for such a relatively small force on a slow moving thing. But let's see. 1.2. So I'm guessing that this is too big, but I'm also guessing that this one is too small, because this is a fair distance in a fair amount of time. I'm guessing that this is a somewhat powerful engine motor. So 1.2. But notice I put the x's next to it because I intuitively think that those aren't the right answers. So 1.2 times 10 to the 4th newtons times meters. Okay, let me scroll so you can see the full numbers. Meters, 9.0 meters, divided by the time, 15 seconds. Make a line here so let's get mixed up here. And now I go to my calculator and I see in my calculator 1.2 times 10 to the power of 4 times the 9 meters divided by the 15 seconds. I got 7,200 watts. So, and by the way, this W is for work. This W is the unit watts. This W is work, okay? It's a variable energy, where this W is the number of watts, named after a scientist named Watt. So, but we got that answer, 7,200. If we move the decimal place over 3 times, right, 7.2, we moved it over 3 times, making the number smaller. So we have to multiply by a 10 to a positive power. How many did we move over? 3 spaces. So the exponent is a 3. Okay. So the exponent on the 10 is the number of spaces that you move the decimal. You could remember that if you move the decimal to the left, then you have to multiply by a positive power, and if you move the decimal place to the right, then you multiply 10 by 10 to a negative power. Or you could think of it as a size argument. If you took the 7,200 and made it a smaller number, 7.2, then you have to multiply by 10 to a power that's a bigger number, so that's a positive power. Okay? So, número 16, number 16, a train blows its horn, which emits a uniform sound as the train approaches a stationary observer. The observer hears a sound that has a lower frequency than the emitted sound and is decreasing in amplitude, or a lower frequency that is emitted and is increasing in amplitude, or a higher frequency than emitted and is decreasing in amplitude, or a higher frequency than the emitted sound is increasing in amplitude. Okay, this is a 2x2 problem. So I don't want you to think of both like both things at the same time, because I think it'll cause confusion. Instead, I want you to think about those separately. Is the frequency lower or is the frequency higher? And is the emitted sound decreasing in amplitude or is the sound increasing in amplitude? First, the train is going towards the observer, okay? So the one that is more intuitive to me is the towards the observer, because maybe I'm thinking about a train that's somewhat close by and coming towards me. Don't put the train close by. Put the train really, really far away and then let it get closer to you. As the train is honking, is the sound getting louder or softer? So put the train far from you. Put the train far from you and getting closer. So that implies that the sound is getting louder. Definitely. Which implies that the amplitude is on its way up. Amplitude is a measure of the sound loudness, but the relation I'm not going to address right now. So it's definitely getting louder. So not decreasing in amplitude is increasing in amplitude. So we cross that one out. It's not decreasing in amplitude, but it is increasing in amplitude. So choice 2 and choice 4 have a checkbox. Now I get to address the thing that I said before, what my notation is. If I think an answer is wrong, I put an X next to it. If I know an answer is wrong, then I cross out the number I cross out the number. So if I think the answer is wrong, I put an X next to it. But if I know the answer is wrong, I cross out the number. I know that choice 1 and choice 3 are wrong because the train is coming towards the observer. I'm the observer. The train is coming towards me. The train's horn is definitely increasing in amplitude, getting louder. So now the question is the frequency decreasing or increasing? That's the next question. Is the frequency decreasing or increasing? And to answer that question, I'm going to say this. That's what I'm going to say. to answer this question, I'm going to say, right? What is that? If you've ever heard a car honk its horn as it's going by you, or if you've ever heard an ambulance go by you, sounding its siren as it's going by you, or a cop car going by you as it's going by you, what happens to the sound? Like as it's going by you, right? That's the sound. So what happens when it's going towards you? Then it's going as it's going by, and it's going away from you. And what happened? Higher frequency, lower frequency, moving away. So as it's going towards you, higher frequency. As it's moving away from you, lower frequency. So, and I bought for the nerds. Again, nerd is a compliment. And I really fully believe that. I should put that on a T-shirt and sell it. Nerd is a compliment. I did put the Doppler effect equation. Frequency is equal to the frequency of the emitted sound multiplied by the speed of sound minus the velocity of the receiver. So if the receiver is also moving, and then divided by the speed of sound plus the velocity of the source. Now, where does this plus or minus come from? The velocity sign is relative to a point between the source and the receiver. Because you can't do positive and negative, because now both of those things are moving relative to the air, but then the thing is that it matters if you're moving like away or towards it matters where you are relative to the actual source. So the direction, so in other words, train going this way to the right, if you want to call that positive, great, but then the train passes you, it's still moving to the right. You can't call that that sign, that velocity, still positive. So what matters is the velocity of your velocity relative to a point in between, and also the velocity of the source relative to velocity in between. And that should not be a zero. I realize that should be a source, the frequency at the source. Fun fact: one of the weird things when if you've ever been unlucky enough to ride in an ambulance, you realize that the siren doesn't change frequency when you're in the ambulance because of the fact that you're not moving relative to the ambulance. But if the ambulance is going towards you, you hear a higher frequency, and if the ambulance is moving away from you, you hear a lower frequency. In fact, that frequency change helps you to know, like, wait, do I have to pull over if you're driving? And you hear the frequency, and you're like, oh, that frequency is higher. There's definitely an ambulance behind me going towards me, and I got to move away. Okay, so that said, now, right, train's going towards you, higher frequency, higher frequency. You don't need to know this formula. You just need to know what happens if the object is going towards you, away from you, a higher frequency. So that's it. Número 17, number 17. A wood block is pulled at a constant velocity, which implies that F net equals 0. Now, I do this whenever I'm taking a test. Do I make my numbers immediate? Actually, I do. Sometimes I make the numbers and I turn out not to need them, and that's okay. Across a horizontal wood floor, which type of energy increases in this block floor system as the block floor I'm sorry. Let me read it again. A wood block is pulled at a constant velocity across a horizontal wood floor. Which type of energy increases in this block floor system as the block moves? Gravitational potential energy, kinetic energy, mechanical energy, or thermal energy? Now, horizontal implies that delta H is equal to 0. So that implies PE gravitational, delta PE gravitational is equal to 0. Okay? So let's cross that out. We want increases. Increases. Kinetic energy, velocity is constant, delta KE is the change in 1/2 mv squared, but m is constant, but also delta v is zero. This is equal to 0. So delta ke is actually also 0. Now, so I can eliminate those answers. Now, the question then is mechanical or thermal energy, the one that's increasing. Mechanical or thermal energy, are those the one that are increasing? So now I have to think about the situation. What is mechanical energy in this class? Mechanical energy um, is spring energy, but there's also kinetic energy. There's also all potential energies, etc. Um, so are those increasing? And they're not. They're not. What about this thermal energy? So are we saying that thermal energy is increasing? Well, this is where we have to remember what happens. And now I actually recommend doing this, rubbing your hands together, seeing what feeling you have in between your hands. However, there's an unfortunate thing. And I noticed this about myself, so I'm guessing that it's true about you. You have to think about when you've done this in the past. If your hands, if it's summer, if you're taking the Regents in August, and so it's summer, and your hands are actually a little bit hot and you do this, then you can actually feel the heat really well. Okay? So when you're rubbing your hands together, you do produce a lot of heat. Ironically, I know that when my hands are really, really, really cold and I do this, I don't feel the heat because the amount of heat relative to the amount of heat that my hands are just constantly losing seems to be so different that like I don't feel the heat change. But it is creating heat. It is creating heat. That's why when people are cold and they do this all of a sudden, this is something that people did even before they understood that this is producing heat. It's just a weird like automatic reaction that we have. This creates heat within our hands. In fact, if you're wearing gloves or if you're wearing gloves or mittens and your hands are still cold, you could rub your hands together and the mittens get warmer and that will warm up, or the gloves will get warmer and you'll warm up your hands. Fun fact, mittens are way better than gloves in terms of keeping your hands warm. But yeah, thermal energy of two rubbing things is increasing. So it is thermal energy. Número 18, number 18, a total energy of 5 joules is used to move an electron. So this is a work, 5 joules, to move an electron from position A to position B in a uniform electric field. What is the potential difference between position A and position B? 3.1 times 10 to the 19th volts, or 8.0 times 10 to the negative 19th volts, or 3.2 times 10 to the negative 20th volts, or 3.1 times 10 to the 18th volts. Now, this is one that I highly suggest um, taking your time to think about uh, how to do this question. Now, I know that an electron is a small charge, but the amount of the potential difference, though, is a measure of the amount of energy per unit charge needed. Uh, yeah, so it's the difference in energy per unit charge between two positions. Okay, so in volts, it's the amount of energy per coulomb in two positions. The amount of energy per coulomb in two positions. So, is there something that makes me eliminate some of these answers? Well, if the potential difference were if 5 joules of energy was used to move a charge of 1 coulomb, then the potential difference would be 5. Okay, but if I then that's per coulomb, but this charge is extremely small, and I still needed an immense amount of energy to move the charge. That means that the amount of the potential difference between 2 points has to be huge. Tons of energy to move a tiny charge, potential difference has to be huge, which means that this answer is exceedingly small and this answer is exceedingly small. Now, um, So again, potential difference is equal to the energy per unit charge. And now keep in mind, energy could be measured in joules or electron volts, and then charge could be measured in coulombs or electrons. And there is an equation. Let's look for that equation. Okay. Now, if you're wondering which one it is, then again, this is where the dictionary that's on the right helps. W is work, so you look for work, and Q is charge, and then you're like potential difference. What's that? Then you realize that potential difference in the exact words is there. So you have V equals W over Q. So the reference table does give you enough information to get this answer. Okay, let's expand that equation. V equals W over Q. Okay, so we have V is equal to the amount of work, W 5.0 joules. And now this is where, this is Q. This is Q, an electron. This is where you need the reference table again, because we're working in joules and volts, which means that we need the charge in coulombs. So we actually can go to the beginning of the reference table that tells us what one elementary charge is in coulombs. And it's right here. So I'm gonna put this over here. Oh, it's too big. Okay. Nope. Didn't do that. Okay. So volts is equal to 5.0 joules divided by the charge of an electron in coulombs, 1.60 times 10 to the negative 19th coulombs. And this is where a lot of students get this question wrong. Remember, you are not doing arithmetic, you're doing physics. So what do I recommend? I actually recommend putting the entire numerator in parentheses and the entire denominator in parentheses. And I'm just going to make that recommendation blanket because for every single problem, because you're not taking an arithmetic test, you're taking a physics test, but they will look for, did you use parentheses in the denominator or not? You might say, well, I don't need parentheses because the horizontal fraction bar doesn't need parentheses. Well, fun fact though, the diagonal fraction bar 100% does. And remember, PEMDAS, I'm an enemy of PEMDAS. I actually have a preferred acronym that's not PEMDAS, that works a lot better. But P does not stand for parentheses, it stands for grouping symbols. And the horizontal fraction bar is a grouping symbol, the diagonal fraction bar isn't. So you need parentheses around the denominator. So 5 divided by parentheses 1.6 times 10 to the power of negative 19 coulombs. And you get this enormous number, 3.125 times 10 to the 19th. To the 19th volts, which is enormous. And it rounds to choice 1. Okay, número 19, number 19. Before we talk about snacks, número 19, number 19. 0.14 kilogram lacrosse ball traveling west at 17 meters per second is brought to rest with a 0.21 kilogram lacrosse stick. If the force applied by the lacrosse stick on the ball is 220 newtons, which is enormous, east, then the force applied by the ball is to the stick is 150 newtons east, 150 newtons west, or 220 newtons east, or 220 newtons west. So again, this is the mass of the ball. This is VI. This is, and I'm noting these, but it turns out that they're not going to be used because, but are they necessary? Actually, yeah, because conceptually they have to be stated. To rest, VF is equal to 0. And then this is M lacrosse stick. And this is F net. Now, look at this though. This is saying that the force applied by the ball to the stick is, now what about all of these is not, why did I say these numbers turn out to not be necessary? But they have to be stated, therefore they are necessary. Well, what I mean is for the problem to be well defined, these numbers or something along these lines need to be stated. It turns out that you don't need them to do the calculation. Okay. Now, Newton's third law, I'm going to write it. I'm going to write Newton's third law, but I'm going to also reword Newton's third law in a way that is actually more useful. So Newton's third law states that every action has an equal and opposite reaction. Okay, but then what's an action? And a lot of students are like, what? They're like, I don't know, and then they get stuck because every single problem with Newton's third law, every action has an equal and opposite reaction, doesn't even involve an action. So there is a better way to state Newton's third law. So if mass A and mass B act on each other, okay? With a force, okay? Then this is what's happening. So object mass A, so if the force, I don't like the way I started this one. I'm going to erase it. Erase that, okay? If mass A pushes on mass B with a force F A to B, okay? Then mass B pushes on mass A, okay? With what force? With a force F from B to A, which is equal to exactly negative FAB. That's Newton's third law. So if I'm pushing on this bookshelf, the bookshelf's pushing right back on me. How hard am I pushing on this bookshelf? Maybe about I want to say about 50 newtons. I think right now that's a fair estimate. Not pushing very hard. Bookshelf is pushing on me right now with a force of 50 newtons. I'm pushing with 50 newtons that way. The bookshelf is pushing this way, 50 newtons this way. Are they exactly opposite? So exactly parallel and in opposite directions? Yes, 100% exactly opposite directions. I'm pushing on the bookshelf that way. The bookshelf is pushing on me this way. And it's 100% exactly opposites. And that's what Newton's second law is. Therefore, if the force applied on this from the stick on the ball is 220 newtons, 220 newtons. So F, I'm going to label this as F from the stick to the ball is equal to 220 newtons east. So equals 220 newtons. That's in the positive direction, which I've chosen east to be positive. That implies that the force applied by the ball on the stick, F ball to stick, is equal to 220 newtons west, which is equal to negative 220 newtons. Okay, so there's my answer. This was a Newton's third law question. That's all it was. Okay. On that note, and if you want to skip to numero 20, number 20, go ahead and skip to number 20, but I do want to address snacks. What do we do about snacks when we're taking the Regents? Well, first off, I want to talk about this. This is my coffee. I love my coffee. I'm going to take a sip of my coffee right now. Am I advocating for you to drink coffee? Hell no. Heck no. Sure, whatever you want to say. Um, I am not advocating for you to drink coffee. In fact, I will say this: if you're not a coffee drinker, then uh, suddenly deciding you're going to take a cup of fully caffeinated coffee to your Regents might be a very bad idea. Because I know a lot of adults say this. A lot of adults, and they're wrong, by the way. A lot of adults say this, that when they drink coffee, they feel less hungry. There's a weird effect that coffee has for professional coffee drinkers like me. It does take away your hunger a little bit, but in a weird way, and it's fake. If you actually follow like a regular coffee drinker and you follow what they ate after their coffee, even if they didn't eat when they were drinking the coffee, it almost always is the case that their body that they ate something much sweeter, much fattier, uh, much less healthy. Because what the coffee does about an hour after you've drank the coffee is it increases your cravings for fats and carbs, and it makes you, when I say crave them, I mean it makes you starve for them. So an adult might say, well, no, it doesn't do that to me. But what I'm saying is that if you actually follow the adult and find out what they ate on days that they drank coffee and find out what they ate on days that they didn't drink coffee, you would find that that it had a subconscious effect, because the conscious effect, they were not aware of the conscious part. That's it. So coffee will make you, and if you don't satisfy that craving in the middle of a Regents, you may find that an hour through the Regents, you are starving, but like to a level that you couldn't even comprehend. And that happens to a lot of students. They bring coffee to a Regents and they're starving halfway through. Now, what about uh, decaf? Could you drink decaf coffee? If you're not a professional coffee drinker, you know what? I mean, decaf coffee might not be the worst idea. Decaf coffee does have caffeine. Here's the thing, decaf coffee will have the same effect on you as like regular coffee has on me, because I'm a professional coffee drinker. So, yeah, I'm not going to advocate for drinking decaf coffee the day of the Regents. Definitely don't drink decaf coffee like 2 hours before the Regents. Take it with you and drink it during the test. Don't drink it like 2 hours before the test, because even that decaf coffee, you will find that you're starving halfway through the test. So, um, that's my recommendation. You could bring decaf with you. Highly recommend. Treat coffee as what it is. It is a drug, and treat it with the respect that it deserves that way. And also, of course, even if you're going to drink decaf coffee, talk to your parents about that, because there are decisions that need to be made. But don't drink the coffee hours before, because then the coffee will actually have a negative effect on your performance if you drink it even an hour before. Okay. That said, what about snacks? Snacks. Oh, and the other thing about milk, and I'm going to come back about milk in a second because this is going to be relevant. One liquid snack that I recommend for the test is Fairlife. Now, Fairlife doesn't sponsor me, although they can call me if they want to sponsor me. Uh, Fairlife, the good thing about it is it's very high in protein. It's liquid, so it hydrates you a little bit. Okay, and it doesn't have much fat and it doesn't have much carbs. What it'll do is it'll satisfy your craving for food in the middle of a Regents. It doesn't provide that much energy because it only has 2.5 grams of fats and 4 grams of carbs, but it is greater than zero. Okay, and so it does give you a little bit of energy. I do recommend something like this because what it also has, and on the bottom, I'm not going to show you, but I am pointing at where it says it's lactose free. Let's talk about lactose. Even if you're not lactose intolerant, being 42 years old, lactose intolerance finally caught up to me. Most Hispanic people are not lactose intolerant when they're young, although our genetic mixing with other people has brought lactose intolerant to the Latin American community. So there are many Latin American people who are lactose intolerant even at young ages. That said, even if you're not lactose intolerant. Having things with lactose may be a bad idea because your body might be like the tiniest bit lactose intolerant, like that much compared to like a fully lactose intolerant person, and then it can cause your belly to swell up with gases and actually make you want to go to the bathroom in the middle of a Regents, which is not the best thing. You want to have your 3 hours that you get, or 4.5 if you get extended time, or 6 hours if you get extended time. You want your full allotted time to work on this Regents. So I recommend something without lactose. And why I'm mentioning that and the coffee is because most people, when they drink coffee, they add milk to it. Drink add You can add lactose free milk to it. If you don't have lactose free milk, but you happen to have lactose powder, you can add lactose powder in it. If you don't have lactose powder, but you happen to have lactose pills, like lactate pills, for example, then you could actually take the lactate pills, break them up, and powder them up and throw that into here. And that lactase is not one lactase pill is not like a drug. So that's something I can absolutely recommend. Literally, lactase is literally just an enzyme that breaks down lactose sugar. So you could totally throw lactose powder or lactose pill broken up into here, and that'll break up the lactose into sugars that your body can process without giving you a gassy belly and making you have to go to the bathroom in the middle of a test. Okay. The last thing that I'm gonna recommend as a snack before we move on to numero 20, another company that doesn't sponsor these videos, but absolutely can if they want to contact me. This Pure Protein bar is a bar that I recommend because it is high in protein, so it takes away the hunger. But this one also happens to have 18 grams of carbs, which is not the worst for a protein bar. Often you want less carbs by a lot than the amount of protein, and it has 5 grams of fat. However, the thing is that the carbs and the fat, we're not talking about like a healthful snack on a random day in April. We're talking about in during the test, right? Having the 18 grams of carbs is actually not a bad thing because it actually gives you a little bit of energy. And the 5 grams of fat also gives you a little bit of energy. So actually, a pure protein bar is actually a really phenomenal bar to have in the middle of a test. And the good thing about it also, it doesn't flake like a lot of like candy bars might. So it doesn't, dirty up your test, doesn't dirty up your clothing, it doesn't cause any situations like that. And it also doesn't um what some other bars do, what you might call an energy bar, is they are so easily digested that for different reasons from lactose, they make you want to go to the bathroom. So you don't want to necessarily have something that causes you to digest the bar really quickly and makes you go to the bathroom. Now, if you don't have anything and that's all you have, one of those bars, one of those energy bars, then go ahead and have that. But I do recommend this pure protein bar, and I do recommend Fairlife milk. And again, for coffee, I actually recommend decaf if you're not a professional coffee drinker. And I also recommend lactose-free milk or lactase powder or lactase pill broken up into the coffee. And of course, the best way to score on this test is to click the subscribe button. It's actually been found that if you click on just my subscribe button, that your score goes up by 10 points. Proven. Don't sue me if it's false. Numero 20, number 20. 4 wires are tested for electrical conductivity. All 4 wires have the same length and the same cross-sectional area, but are made of different metals. Which wire has the highest conductivity at 20 degrees Celsius? Aluminum, copper, gold, or silver? To be honest, I do know the answer to this question because I've done this kind of question so often, but I don't, I don't have like a super phenomenal way of eliminating answers other than saying this. I remember that in terms of resistance, uh, copper is somewhere between aluminum and silver. Okay, so I remember that copper is somewhere between aluminum and silver. So even if I don't remember how to do this, or I don't know this, good thing is you don't need to know this. You could look it up. But I remember that copper is between aluminum and silver. And then I might say to myself, gold, where is gold relative to aluminum and silver? And I'm like, mentally, I'm like, I think gold is actually also between aluminum and silver. So I'm going to put an X next to that because I think it's wrong. So notice my notation. I'm simulating myself as a student. So even if I don't know how to do this problem, I might choose between aluminum and silver. So, but what do I do? Well, it turns out that this is on this test. So let's go look for the uh, conductivity question or the resistivity question. Where is it? Here it is. So you see which conductivity, the highest conductivity, which is the opposite of resistivity. So highest conductivity, we need the lowest resistivity. Okay? So I see the equation here for resistance. And you do need the equation. If you think you don't need the equation, you actually do. This is one of those situations where you sit there and say, how do you use the equation? Again, the same length, so the L is a constant, and the same cross-sectional area, A equals a constant. Okay? And the temperature is equal to a constant. Does resistance and resistivity change depending on temperature? Yes. But it means that these are, since they're constants, the only thing that we need to do is compare the resistivity and the resistance. Notice that, again, this is a constant. This is a constant. And notice that rho R equals rho L over A. This is the resistivity, which, since the material is changing, is not constant. And this is the resistance. So we need to compare the resistivities. And the resistance and the resistivity are actually proportional to each other. So we need the lowest resistivity. If we go to the table, aluminum has a resistivity of 2.82 times 10 to the 8, negative 8th, okay? This is ohms per meter. The copper, just to confirm that I'm doing this right, has a 1.72 times 10 to the negative 8th resistivity. Gold, which I thought might be wrong, has a resistivity of 2.44 times 10 to the negative 8th resistivity. And then silver has a resistivity of 1.59 times 10 to the negative 8th ohms per meter. So lowest resistivity, there's my lowest, 4. Turns out I was right about copper being between aluminum and silver, and when I wasn't sure, fake student me was unsure about whether gold was between aluminum and silver, but suspected it for guessing purposes. It turns out I was right. But notice that in the end, I did not guess. I looked up the answer. I looked up the answer and confirmed that the answer had to be silver. And on that note, we go to number 21, numero 21. The angle of incidence for a ray of light striking a plane mirror is 20 degrees Celsius. What is the angle between the incident ray and the reflected ray? Okay, so you do need to know what the incidence ray and the reflected ray means. That said, I will draw this out, but it's either 20, 40, or 70, or 90. The incident ray and the reflected ray. So if you have a mirror, okay, this is my mirror. Then if you have a incident ray, okay, so then ray that bounces back is going to be red also. This one didn't straighten out. Let's try again. There we go. The reflected ray. Good. Okay. I kind of want to like move this over the slightest bit. Nope, that's not what I wanted to do. Just wanted to move this over a little bit so that it's a little bit clearer. Okay. Let's delete that there. Okay, good. So now we need to know what the angle of incidence is. This is something that you do need to know. And I remember what I was taught. I was taught that the angle of incidence is equal to the angle of reflection. Okay? But then I need to know which one the angle of incidence is. So if I draw the perpendicular line from the mirror, then this is the angle of incidence. And then this is the angle of reflection. So this is equal to 20 degrees, and this is equal to 20 degrees. Okay? So the angle of, now I see 20, 40, 70, and 90 degrees as my possible answers. The one that, if I were to do a process of elimination, the angle between the incident ray and reflected ray, for that to be 90 degrees, there's no way for those angles to add up to 90. Okay? The angle between, in other words, the angle between those, for that to be 90, the angle would have to be 40, the angle of incidence would have to be 45 degrees. So it has to be, in other words, the answer has to be some sort of multiple of either 20 or a multiple of 70. So actually, basically all of these answers, for a lot of reasons, don't make sense. The angle between the incident ray and the perpendicular has to be 20 degrees. So this one is really testing, do you know how to name the angles? Okay. Luckily, 140 is not one of the answers because that would be the most common incorrect answer. So, but I wonder if the test has that as a formula, right? So if you go to, let's see, modern physics, let's actually check. Let's check together. Okay. It's definitely not going to be there. Mechanics, geometry, modern physics, waves, the angle of incidence equals the angle of reflection. And the answer, the equation is there. So as I told you, this is a very formula-centric test, and the angle of incidence formula is in fact there, okay? Angle of incidence is equal to the angle of reflection. So 20 plus 20 is 40. Luckily, this didn't require you to know that that was the 20 degrees and not this bottom one, right? Because if you label that one as 20, then you would label the top one as 70, but then 70 plus 70 is 140, and 140 is just not one of the answers. So we did get lucky there. 20 plus 20 is equal to 40 degrees. So that is the answer. Now, número 22, number 22. As shown in the diagram below, mass M slides across a level, frictionless surface with a speed VI. The mass strikes the spring at position A, causing the spring to compress. When the mass is at position B, it's moving at a slower speed, VF. So VF, I'm going to write this, VF is less than VI, okay? Which statement best describes the energy conversion as the mass moves from position A to position B? Some of the mass M's kinetic energy is converted to elastic potential energy, or all of mass M's kinetic energy is converted to elastic potential energy, or some of mass M's kinetic energy is converted to gravitational potential energy, or all of mass M's kinetic energy is converted to internal energy. Definitely think about this question because I think there's some of these that could be eliminated pretty easily. Like they could have made this a 2x2 problem, meaning and it is partially 2x2, it's some or all, but the other one is not 2x2 because it's elastic or gravitational or internal. So it's 2 by 1 by 1. So, well, here's what I do to eliminate some answers. I see that VI is less than VF. It said it's moving. It said it's moving at a slower speed. So VF is less than VI, but also it's 0 is less than VF, which means that KE is greater than 0. Kinetic energy is greater than 0 because 1/2 mv squared is greater than 0, right? Which means that only some of the kinetic energy is converted to something else. So not all. So we cross out all, we cross out all, cross out 2, we cross out 4. And so some of the mass's kinetic energy was converted to something else. And now the beautiful thing is that one of these is makes a little bit more sense than the other one. Was some of the kinetic energy converted to elastic potential energy, or was some of the kinetic energy converted to gravitational potential energy? The formula sheet again says PE sub G is equal to M delta PE is equal to mg delta H. That formula we did copy and paste it on an earlier screen, so I'm not going to look that one up, but I will look up the spring potential energy. Spring potential energy. Where is the spring potential energy? PES, there it is, potential energy stored in a spring. PES is 1/2 kx squared. PES is 1/2 ks squared, x squared. So here, mg delta H is equal to mg times, this thing is not moving up, this is horizontal, which is equal to 0. So the energy is not converted to gravitational potential energy at all. The energy has to have been converted to elastic potential energy. And in fact, the spring is compressed. The spring is compressed. Here's your delta x, or x, which is greater than 0. Okay? And I'm going to put x, and I'm going to put x in absolute value, because it depends on whether you want to make x positive or negative as a compression. Okay? So we have the elastic potential energy, and that one makes more sense. All right, número 23, number 23. The diagram below shows a magnetic compass placed between unlike magnetic poles. North and south, I see the compass, I see A, B, C, D. And then the north pole of the compass needle will point towards A, B, C, or D. You do have to, put a little bit of thought into this one, which direction the pole of the compass points. Is it going to point towards the north or the south? And this is an interesting one because this one does require you to know how a compass works. Well, no, that's not true because the wording of the question releases you from having to know that. It says the north pole of the compass needle will point towards the north pole or the south pole of these two magnets. Okay, the wording of the question releases you from having to know how a compass works, and the way a compass works is actually a little bit interesting. But you do need to know that opposite poles of magnets attract. Okay, and also that the like poles, like or same poles of magnets repel. So they release you from knowing how a compass works by saying the north pole of a compass needle. They didn't say the compass needle itself on the object, what does it point? It just says the north pole of a compass needle. Okay? Will it point towards A, B, C, or D? Well, because the compass needle has to point to one of the poles, it eliminates B and D. It's not going to point sideways. It's going to point either towards the north pole or the south pole. And so that eliminates choice 2 and eliminates choice 4, and we have a passing problem. Passing problem. Now, a fun fact, we know that if you go further north on the Earth, Well, you end up at the North Pole. We also happen, if you took Earth science, you happen to also know that what we call magnetic north, what we call magnetic north, is actually shifting around. It does move, and it actually does move a lot, believe it or not. Um, but at least in New York and most of the world, the magnetic north is sufficiently pointing towards the north that it gives us an accurate calculation of what direction true north is. True north would point towards the North Star or towards the North Pole. So why am I mentioning that though? Well, supposing even that the that magnetic north is close to the North Pole, because that is a fairly good estimate, especially in New York. Well, what can we say about that North Pole? It turns out that the North Pole, what we call the North Pole of the Earth, is actually closer to the magnetic south, is the South Pole of the dynamo magnet that is created by the Earth. So why do we call that the North Pole? And I'm not sure at this point. If you happen to know, you could post it in the comments. But it happens to be the North Pole of the magnet points north to geographic north. Again, the North Pole of the magnet points towards geographic north. But if the North Pole of the magnet points to geographic north, and like poles of magnets attract, well, that means that that North Pole of the magnet has to be pointing towards the compass magnet has to be pointing towards the South Pole of the magnet of the dynamo in the Earth, which means the South Pole of the Earth's magnet is north, and the North Pole of the magnet is south, and that actually is true. So the North Pole, magnetic north, is called magnetic north because of the compass needle, not because of the Earth's magnet. The Earth's magnet is South Pole is north on the north side, so that the magnetic north of the compass points north. Okay, fun fact. And why am I saying that? Because the South Pole of this magnet has to point towards the magnetic north of this magnet, and the North Pole of this magnet has to point towards the magnetic south of this magnet. So, which means that this compass, the North Pole of the compass needle, is going to point towards C. Now, the reason why I went through that conversation is that you do need to know that for this test, although the wording of this test freed you from knowing that. That's how a compass works. The compass north points towards the south dynamo of the Earth, which is towards the North Pole geographically. Fun fact. Número 24, number 24. Which circuit diagram contains a lamp that will not have a current passing through it until the switch is closed? Um, is it choice one, choice two, choice three, choice four? So I would strongly think about this, but I mean, I do have to, for time's sake, I do have to basically explain it. But how do I do this problem? So the way I do this problem, it's saying it will not have a current passing through until the switch is closed. So what I do is I actually try to follow the battery, and I do what I call the right hand turn. Right hand turns to the right, turn to the right always, unless the unless I can't. And then I see if I can make it around to the battery again. So here I go up. There's nowhere to turn except the way the wire goes. So I keep going. This is a current flowing, flowing, flowing. There's nowhere to turn except the way the current where the wire goes. So I go here and I arrive at a switch. No way to cross over. So this one, I look for any other way that I could have gone, and there is no other way that I could have gone. So the answer is almost definitely going to be this one. Almost definitely going to be that one. But then I go to the other questions, and I see what happens when I go to the other ones as well. It's got to be that the other ones must allow current to flow even when the switch is closed. And I do the right hand turn again. So I go up. nowhere to go but to the left, nowhere to go but down. Now, here I go to the right side. The right side, if I'm this way, is actually continuing down. So I'm continuing down before I go to the switch, and I keep going this way, and I go this way, and I stay to the right, so I keep going this way, and I'm right back at the battery. I found a path to the battery, so it's not this one. It's not choice 3. Choice 2, I do the right-hand turn again. I go this way. I have a fork in the road. I could go left or to the right. So I go to the right-hand turn. I keep going, keep going, keep going, keep going. Nowhere to go but down. And here at this vertex, I take the right-hand turn because that's what I said I always do. And it happens to be that I arrive right back at the battery. So I found a loop that flows, current will flow in choice 2. So it's not that one. Choice 1 is looking phenomenal. Then on this one, on choice 4, I go up, nowhere to go but to the right. So I keep going. Here, nowhere to go but down. Here, as I said, I follow the right-hand turn rule. So I turn to the right, and I arrive at a switch, so I can't keep going. But it doesn't mean that I'm done, because I have to check if there was any other choice that I made. I made a choice at this vertex. So now I make the other choice at this vertex. There's only one other choice, and if there were 2 other choices, I would make the rightmost decision. But there is no other choice. I go down here, and I keep going to the right here, and there's nowhere to go but up here. Now, again, I'm at a vertex, and I go to the right, and I'm right back at the switch, and I can't go, but I go back to this vertex where I made a decision, and I go up instead, and I'm right back at the battery. I made it to the battery. This choice 4 allows a current to flow, so it's not choice 4. Remember, I'm looking for not. This one allows current to flow. This one allows current to flow, but choice 1 does not allow current to flow. So it is choice 1. Número 25, number 25. The diagram below represents an electric circuit. Well, I do a quick look before I go back to it. I see a battery. I see a 9 ohm, 6 ohm, and 3 ohm resistor. And then I say it says the equivalent resistance of the circuit is 1.6 ohms, 2.0 ohms, 6.0 ohms, or 18 ohms. And I invite you to think about this answer. This one, I'm going to go into my formula sheet for sure to do it. But I do notice that all the resistors, you do need to know what it means to be connected in parallel. And these resistors are connected in parallel. So connected in parallel means that all resistors are connected by a wire, okay? By a single, but I can't, are connected. I'm gonna say can be connected. Can be connected by a single node. Now you might say, how could they be connected by a single node? But if you notice right here, that, let me see if I could actually, this collection of wires can be connected by a single dot, okay? Single dot. And single node, but the point is not just a single node where the current can split into or more. Okay? The current can split in 2 or more. Okay? So as opposed to parallel, as opposed to series, the current cannot split because it has only one path to take. So if you notice from this battery, the current would go to the right and then up, and then it splits into the 9 ohm resistor or up to go to the 6 ohm and 3 ohm resistor. So those are connected in parallel. The 9 ohm resistor is connected with the system 6 and 3 in parallel. Now the 6 and 3 also, if you go to this node, the current can split again between the 6 and 3 ohm resistors, so that those are connected in parallel. So the 9 is connected in parallel with 2 resistors that are connected also in parallel, so the whole system is connected in parallel. So these are in parallel, okay? And why does that matter? Because now I could actually eliminate some choices by intuition. Resistors in parallel have a combined reduced resistance. Now you could say, how could it be that the resistors combined have a reduced resistance? But the reason is that if they're in parallel, then the current has the option of going towards one resistor or the other resistor. So the current always takes the path of least resistance. And there is some math that can be done that addresses why the resistance, or why the path of least resistance, it's reduced, why the path of least resistance, even though the resistors vary in resistance, how it could be that the electrons might pass in two different directions. Because what truly ends up mattering is not the resistance of the individual resistor, but the amount of energy lost by the electrons, by the charges. If the amount of energy lost by the charges is what matters, then really what happens is that the electrons or the charges flow in the direction that reduces the energy that reduces the energy drop. And then you might say, well, doesn't the energy drop across the smaller resistor, isn't that one always going to be smaller? And actually in parallel, not necessarily. Not necessarily. Because if all of the charge is going to the, let's say the 3 ohm resistor, and none of the charge is going through the 9 ohm resistor, then a single electron with whatever energy can pass relatively freely through the 9 ohm resistor without losing any energy. But then more and more charges go through the bigger resistor until the energy drop across both resistors becomes equal. So that's the key. That's the key, and to understand. Now that said, we want to understand that this diagram is drawn in parallel. The reason, again, it's drawn in parallel is, as we said, that the current has to split to each resistor. So is there a formula in the formula sheet that allows us to do this question? Yes. And it turns out that resistors in parallel and resistors in series have different equations. And these equations might not be intuitive for you, but, and they are intuitive for me, but it took me a while to gain intuition on these. The ones that are intuitive for me are the current the current equation and the voltage equation, the voltage drop equations. Excuse me. If they're in series, I'm sorry, in parallel. If the resistors are in parallel, then the energy drop has to be equal to the energy provided by the battery, which means that the voltage drop across all the resistors has to be the same and has to be equal to all the energy given by the battery. So V equals V1 equals V2 equals V3 makes sense to me. And then the second one, I equals I1 plus I2 plus I3, that the fact that the current across all the resistors is a sum and adds up to the total current from the battery. That one made sense to me because that's the law of conservation of charge. Charge can't be created, charge can't be destroyed, charge doesn't leak out of the system. So the total current going to all the resistors has to be equal to the current coming from the battery. So again, the total sum of the current through all the resistors has to equal to the initial current from the battery. The one that broke my intuition when I first learned it was this resistance equation, which I don't know if there's a way to fix that intuition other than to say, remembering that V equals IR at each resistor and V equals IR at the battery, where where R at the battery is the effective resistance of the entire circuit. If you use that equation, this weird equation for the resistance kind of pops out. And I think it's weird. It does break my intuition to think it has to be exactly this. But I will say this, that um, it does imply that the total resistance should go down. Okay, so now, and I didn't address the guessing strategy yet, but here's where the guessing strategy is. The resistors are connected in parallel, therefore the total resistance has to go down. Implies that the total resistance is less than the individual resistances. So R effective is less than 3. It's also less than 6. It's also less than 9. It's also less than 6. And it's also less than 9. It's less than 3 and less than 6 and less than 9, which means that crosses out choice 3 and choice 4. So even if I mess up on the arithmetic when I'm doing this problem, I'm left with a 2x2 problem, and I could go about it that way. Now, from the 1.6 and the 2.0, is there one that I would eliminate now? I mean, the 3 and the 6, there's just arithmetic that I've done so many times with the 3 and the 6. Like, that's going to end up adding up to 2 just by themselves. Then you add another resistor in parallel, that's going to reduce the resistance more. So I tend to cross out this one. But that's my intuition on arithmetic, not yours. So how do I do this problem? I just literally put it into this equation. 1 over Req is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And so that's equal to 1 over 3 plus 1 over 6 plus 1 over 9. And if you don't like the order that I put these in, change the order. You get the same answer. This is an arithmetic question. Okay? 1 over 3 plus 1 over 6 plus 1 over 9. And you get 0.611. Okay? And then if you get the R resistance, so 0.611 repeating. So Req is equal to 1 over 0.611 repeating. And you might not know how to put that in the calculator, 0.611 repeating, but you don't have to. You could do 1 divided by second answer. 1 divided by the answer is 1.63 repeating. 1.63 repeating ohms. And to 2 decimal places, and that's choice 1. Número 26, number 26. An object is thrown vertically upward with an initial velocity of 9.81 meters per second. So that's VI. And vertically upward. So that means that G is equal to 9.81 meters per second squared. And what is the maximum height? This is H, maximum height reached by the object. Neglect friction. Is it going to be 1 meter, 4.91 meters, or 9.81 meters, or 19.6 meters? Okay, so there are some answers. My intuition is good enough that I can eliminate, believe it or not, all of the incorrect answers without even knowing why the correct answer is the wrong answer. So 9.8 meters per second, this is a pretty fast velocity. And then G happens to be the same exact magnitude of G. But this implies that VF is equal to 0, which implies that time G equals to 0. Now, just arithmetically speaking, I could see that the time flying is going to be 1 second, and that's why choice 1 might be there. But the thing is that 9.81 meters per second, the object travels a distance of 1 meter, which is only that far, really very quickly. If G was equal to 0, which it's not, but if G was equal to 0, an object traveling at 9.81 meters per second, or around 10 meters per second, would travel 1 meter in a tenth of a second. Or in this case, 9.81 meters per second, slightly more than a tenth of a second. That's not enough time for gravity to take it from 9.81 meters per second upward to 0 in a tenth of a second. It travels faster than it travels for more than a second. So this one is incorrect. It's too small. But also the average, so again, t is going to be equal to 1. The average, why? Because and then the acceleration downward, 9.81 meters per second squared, from 9.81 meters per second to a velocity of 0. That happens, the V average, which is V average, is less than 9.81. For 1 second, this one can't be right. And this one, it's also too big. So these two are too big. And now I have 3 wrong answers without knowing how to do it in quotation marks. But why did I do it this way? We want to maximize our grade on this test. Yes, this is a formula-centric test. Do I recommend circling the correct answer and moving on? Do I recommend circling the correct answer and moving on? Actually, I don't. Because if you are struggling with the test, you're probably not going to run out of time. You're going to do your best to do every single problem. But the truth is, you should go to the formula sheet and find the answer that is going to give you everything that you want. H is the displacement, right? VF is, so you have VI, you have VF, you have G, and they're asking about H. I said T is equal to 1, but I mentioned that because this problem allows for many different ways of doing the problem. The one equation that gives you gives you everything you have or need. Remember, have or need is my word. Have or need is one word. Have or need is one word for me, because in an equation you need an equation that has everything, not that you have, nor everything that you need. You want an equation that has everything you have or need. Okay? And this equation does have everything that you have or need. Let's see. VF squared is equal to 0 squared equals VI squared is 9.81 squared. If you were doing this on a part 2, you do need the units, okay? But we're not, so plus 2. G is negative 9.81 times D. Okay. I'm going to make a point here also about direction. Up, if I call up positive, I have to call down negative. Do I recommend just changing the sign if you get the wrong sign? I mean, in an extreme way, no. Okay? I'm going to subtract minus 9.81 squared, minus 9.81 squared. Why? Because often it's the case, yes, that if you just mess up a sign, then the other answer is it's the opposite. But actually, more often, getting the incorrect sign is a tool to let you know that you did the problem wrong. And often, it's the case that the problem is not just going to give you like the opposite sign, but if you fix the problem, it just gives you a totally different number. So I got negative 9.81 squared equals 2 times negative 9.81 times D. Divide by 2 times negative 9.81. Divide by 2 times negative 9.81. And I do need parentheses around the denominator. So I'm going to put that in parentheses and around the numerator for completeness sake. I'm going to try to remember to put parentheses around basically every numerator and every denominator for the rest of this video, because that's a arithmetic fixer. Arithmetic problem fixer. Divided by parentheses 2 parentheses negative 9.81. It's an arithmetic problem fixer, really. Because the horizontal fraction bar is a grouping symbol, the diagonal one is just strictly not, and you get 4.905. Which rounds to 4.91 meters. Número 27, number 27. Which type of photon has the least amount of energy? Ultraviolet, visible, infrared, radio. Okay, least amount of energy. Now, if I didn't know how to do this problem and I just refused to go to the reference table, let's talk about time usage. This is a really good time to talk about time usage. Is it worth it to spend time to get a question right versus not spend the time and have a chance of getting it right? I think a good way to interpret that question is to say this. You could take the amount of time it takes you divided by the probability of getting it right. And that gives you another number, like kind of an effective time. Like if it takes you 2 minutes, but it's still a wild guess, well, your effective time is 2 divided by 0.25, which is 8. Whereas if it takes you 3 minutes to get to 50% chance of getting it right, well, that's 3 divided by 0.5. Your effective time is 3 divided by 0.5, which is 6 effective minutes. In other words, eliminating 2 choices is worth it. And versus if it takes you 4 minutes, but you're guaranteed to get it right, now your effective time is the 4 minutes because you're guaranteed to get it right. So it is worth your time. Now, which type of photon has the least amount of energy? I am going to go ahead and do this and eliminate visible light, because I know that in terms of energy, visible light is between ultraviolet and infrared. And so that's not the answer. And I happen to remember that infrared is between visible and radio. So if visible is not the answer and infrared is between visible and radio in terms of energy, then infrared can't be the energy. Now I have a passing problem. And fun fact, if I have 24 questions, let's say I didn't know how to do half the multiple choice questions and I wild guessed on all of them. Now I have a 1 in 4 chance of getting it right. So I divide by the 4 choices that I have. The number of questions that I'm going to get right if I wild guess on 24 questions, this is now guessing strategy, is equal to 6 questions. Now you might say spending some time to eliminate a choice isn't worth it, but if you notice, 24, if I eliminate exactly 1 choice on 24 multiple choice questions, now I have to guess out of 3 choices. On average, I don't get 0 of the questions right. Actually, on average, I get 24 divided by 3, which is equal to 8 questions right, which is 2 full points. So is it worth your time to eliminate choices? Absolutely. But here's the beauty. What if you don't eliminate 1 choice? What if the thing that you do eliminates 2 choices like I did here? Infrared, in terms of energy, visible is between ultraviolet and infrared, so I eliminated visible light. And I remembered that infrared is between visible and radio, so that eliminates infrared too. So 24 divided by 2, if I eliminate 2 choices out of all those multiple choice questions, 24 divided by 2 is 12. That's a huge boost in your grade. As 6 versus 12, 8 versus 12, huge. So is it worth spending your time to eliminate choices? Absolutely. But now, suppose I don't remember which one has more energy, ultraviolet or radio. Now, I do remember which one has more energy versus ultraviolet versus radio. And ultraviolet, thank goodness, is not conducive to working radios, although sometimes, if the energy is not the thing that we care about, maybe, because ultraviolet rays are kind of harmful to us, right? But if we look on the reference table, there is a spot on the reference table that talks about energy. Now, you might say, well, this didn't talk about energy on the reference table. Excuse me. And if you said it that way, you'd be right, except that if you go now to the reference table and got the energy equation for electromagnetic waves, nope, I'm looking for modern physics. There we go. Remember I'm gonna bring the glossary here just so we could just mention the glossary maybe one more time. The energy formula. So remember, energy for a photon is equal to h, which is Planck's constant, which is on page 1. The number is there. And then frequency is there, or hc, or hc over lambda for wavelength. And luckily, the reference table gives us both the energy, the frequency, and the wavelength. So least amount of energy. So we have E equals H, which is a constant, F, and it equals to H, little h, hc over c is the speed of light over lambda. Notice that if we have the least amount of energy, right? Again, this is a photon. So we want the least amount of energy. So if I draw an arrow down here, then h is a constant. So, but f would have to go down to match the energy. But also lambda, being that we're dividing hc by lambda, dividing, that means that it's inversely proportional to the photon's energy, which means that this would have to go up to get a smaller number. Which means, so if we look at ultraviolet, which is right here, and we look at radio, which is right here, and we look at the frequency, 10 to the 18th versus 10 to the 6th, this is frequency down here, and this is frequency up, right? And here, they actually also do the wavelength, 10 to the negative 9th versus 10 to the 0, or actually negative 2 all the way to 10 to the 4th. So this is lambda. 10 to the negative 9th is 1 nanometer. Lambda is down over here, and lambda is up over here. So which one has the higher energy? And I'm sorry, the least amount of energy? We need energy down, which means the frequency has to go down, and the wavelength have to go up. This is E down. So it's radio waves. And luckily it is radio waves, because radio waves tend to be non-ionizing waves, although some research is being done. We'll see later on in the future whether, let's say, for example, our cell phones have an effect or not. But luckily our cell phones are not just constantly shooting insane UV rays. Although there's questions about that too. After all, they are warm, right? And so the black body radiation, well, there's questions, right? Número 28, number 28, a 7.5 kilogram object moving, so this is M, moving at 20 meters per second, strikes a second object. So I'm going to call this M1 and V1, and this is a 60 kilogram object, M2, initially at rest, V2I, and now we have an initial, so V1I. Let me make that a little bit neater. V1I on a frictionless surface. So there's no, on a horizontal frictionless surface. So there's no energy lost to friction, not going up a hill, anything like that. The two objects stick together. And so V1F is equal to V2F equals, let's say, VF. Let's call it VF. And move off at a speed of 0.33 meters per second, or 2.2 meters per second, or 2.5 meters per second, or 18 meters per second. So after reading and labeling, we could lose all the information that we just gained. So then we have to go back into the problem and read it a second time. And at this point, I will say this. A lot of students get to the problem and say, I don't know how to do it, and move on, thinking that they should be able to read the problem once and do it. That's not how it actually works. The nerds among you who are getting the higher grades actually know that you usually read the problem somewhere between 2 and 5 times. And it actually happens to be true that the average number of times that a problem gets read for higher effort students is 5. That's actually the average, 5 times. So it's actually better to read the problem more than once, far more than once, and don't expect to have to read the problem exactly once. Expect to read the problem at minimum twice. But if you read it twice and nothing happened, go read it again. Nothing happened the third time, go read it again. Yeah, you got to read the problem average 5 times. So now going back to the problem, because there was so much information, 7.5 kilogram object, 20 meters per second, strikes a 60 kilogram object initially at rest, and they stick together, and they move together at a speed of what? So this is a small object striking a big object and sticking to it. The small object and the big object are not going to move together at a very fast speed relative to the initial speed of the initial object, the initial small object, since the big object was at rest, which means that the final velocity is going to be small. So I'm going to eliminate the 18. This is too big. Okay. Now, I happen to also want to eliminate the 0.33. Now, let's address why I'm going to eliminate the 0.33. The 0.33 is 1/60th of 20. But the thing is that the 60 kilogram object and the 7.5 kilogram object, they're not their mass is not at a ratio, or their combined mass is not at a ratio of less than 5%. So this one's too small. So now we have two answers, 2.2 and 2.5. I don't know, in terms of my intuition, which one is going to be the answer. I do some weird arithmetic that does eliminate one of the answers for me versus the other, but that arithmetic is weird and not worth teaching. It has to do with factors and uh, prime numbers, weird things. I do know why the incorrect answer is there. Students who forget to stick the masses next to each other. But how do we do this question? How do we actually do this question, right? Even we got some intuition and we got a fair probability of getting it right. But here it is. This one technically, if you want to be technical, yes, you need two equations. But one equation is to understand the theory, and the second equation is to actually do the calculation. P equals mv, momentum is equal to mass times velocity, and momentum before equals momentum after, assuming that the objects don't interact with the outside of the system cannot lose momentum, and that's the general statement that a closed system does not lose momentum. So the initial momentum is equal to the final momentum, which means that m1 v1 plus I plus m, so this is pi equals pf. So m1 v1I plus m2 v2I is equal to, now they stick together, m1 v1f plus m2 v2f. But let's actually just acknowledge that they stick together. M1 plus m2, and then they stick together, vf. And now let's plug in some numbers. So M1, 7.5, times V1, 20, plus strikes a 60 kilogram object, 60, initially at rest, 0, equals M1 plus M2, 7.5 plus 60. And this is where students got things wrong. They forget to stick the masses together. And that's where one of the answers is, times missing VF. Okay, so then I go to my calculator. I see 7.5 times 20 is 150, is equal to 67.5 VF. And I divide by 67.5. I divide by 67.5. And I go to my calculator. Yes, I'm blocking that off because you guys need a big screen so you can see better. 150 divided by 67.5. And I get 2.2222 repeating. So VF is equal to 2.2 repeating meters per second. Okay? Which rounds to choice 2. Nice. Number 29, number 29. How is the electrostatic force between two positive charges affected as the charges are brought closer together? How is the electrostatic force between two positive charges affected as the charges are brought closer together? Does the force of attraction between them increase? Does the force of repulsion between them increase? Or does the force of attraction between them decrease? Or does the force of repulsion between them decrease? This is clearly a 2x2 problem. Electrostatic between two positive charges. How is that affected as the charges are brought closer together? Is that force, to begin with, a force of attraction or repulsion? And then second, does that force increase or decrease as you bring them closer together? Yeah, 2x2. You do want to know that if you like charges repel, like charges repel. And then also opposite charges attract. Okay, that is a big fundamental statement in physics class. Okay, I don't like the way they made that square. That was, should have just made the square myself and not let the computer fix it for me. There we go. That's a fundamental statement about the way physics works. Like charges do repel each other, and opposite charges do attract each other. So this is two positive charges, so they're like charges, which means that they repel. This is our force of repulsion. So cross out attraction, cross out attraction, cross out one, cross out attraction, cross out three. 2 by 2 problem. So now we know it's a force of repulsion. Now we do also need to know that, and this one you can use the formula sheet. It does help to know that charges, as they get closer together, the force increases. But we want to go to the electricity section where we have the force between two charges. There is a force between two charges, the electric force. Fe is the electrostatic force. Okay? Fe, sorry, again. Fe is equal to K Q1 Q2 over R squared. So if you increase R in the denominator, notice that R is in the denominator. If you increase R, then since Fe is in the numerator and R is in the denominator, that actually makes Fe and R, well, actually technically R squared, in this case, are inversely proportional. So if R goes up, Fe goes down, but in this case, they actually said R goes down, so I'm going to draw the arrow downward. So then, in other words, so since R squared and Fe are inversely proportional, if R squared goes down, Fe goes up. You do want to know that. Bring up charges close together, force goes up. Bring charges far apart, force goes down, right? If you have an electron and I have an electron, the force, and we're this far apart, wherever you are, in distance, the force definitely is going to be low. But you try to put the electrons really close together, and you get some interesting forces going on. So the force of repulsion between them increases as you bring them closer together. Okay? Número 30, number 30. What is one difference between magnetic forces and gravitational forces? All right, magnetic forces, gravitational forces. Let me think about gravitational forces. Let me think of magnetic forces while I go to this to these choices. Magnetic forces are always attractive, whereas gravitational forces are always repulsive. Or magnetic forces are always repulsive, whereas gravitational forces are always attractive. Or magnetic forces can be attractive or repulsive, whereas gravitational forces are always attractive. Or magnetic forces may be attractive or repulsive, whereas gravitational forces are always repulsive. Again, another 2 by 2 question. The question is, are magnetic forces, it's not even the difference between them. You actually don't even have to address the difference. You just address each one individually. So that's the benefit of a 2 by 2 question. They said the difference between these two, but you don't actually have to think about them together. Think about them individually. Gravity. Is gravity repulsive? Are we literally being nailed to the ground because gravity is just pulling us up into space? No, we are being pulled towards the Earth. That is definitely very much an attractive force. The Earth is pulling us towards itself. We are pulling the Earth towards us. Gravity is an attractive force. So that eliminates any one that says gravitational forces are repulsive. There we go. So choice 1 and choice 4 are eliminated. 2 by 2 question. And now we ask the second question about the magnetic force. Are the magnetic forces always repulsive? Or can magnetic forces be attractive or repulsive? Well, if you've ever put a magnet on a refrigerator, you actually can answer this question even without knowing it. I do hope that your school let you play with magnets at some point, but they didn't even necessarily have to. Because if you've put a refrigerator magnet on your refrigerator, you know that the magnetic forces between the refrigerator and your refrigerator magnet are attractive. Otherwise, the magnet would not stay there. Whereas there is no always attractive answer, but choice two says always repulsive. We just gave an example that is not repulsive. Think refrigerator magnets. Now, one thing I do recommend to you, if you want to check, wait, can they be attractive or repulsive? Go to your refrigerator. If you happen to have two magnets on it, you may not, but if you do happen to have two magnets on it, play with the magnets. See if you can get them to attract each other and see if you can get them to repel each other. Magnetic forces between magnets can be attractive or repulsive. So the answer is choice three. Número 31, a sound wave, or 31, a sound wave passes through an opening in a brick wall as represented in the diagram below. We see the sound wave, we see the wall, we see the opening, and we see this bowed looking sound coming out to the observer. An observer, let me shrink the size of this image so it fits on the screen. An observer standing behind the wall is able to hear the sound. This spreading out of the sound wave as it passes through the opening is an example of interference or reflection or refraction or diffraction. This part of the Regents actually is asking us a lot about a lot of these definitions. So we do need to know what these words mean. So what is interference? This is a combination of two sound waves. That's what interference is, a combination of two sound waves. And you might say, wait, but what if they combine and make a louder sound? Well, that's constructive interference. And if they combine and the sound waves combine, two sound waves combine and make a lower amplitude sound, that is destructive interference. So, but either way, interference is a combination of two sound waves. Reflection is a bouncing of a wave off of a surface or boundary. Okay, and then what is refraction? Refraction is a bending of light of the direction of light when transitioning between mediums, two different mediums. And as we've seen, I hope that we've seen that, but there's like an example of that. If you've ever been to a swimming pool and you see that a person deep in the swimming pool looks shorter, it's because the light bends or the water and air bend the light as the light transitions from the pool out. And also, if you take an actual stick, which you know doesn't bend when you put it in water, and you actually put that stick in the water, the stick looks like it like bends right in the middle, right where the stick touches the surface. So that's because the light bends the stick, the light bends the direction that the stick appears to go, because the water air boundary bends the light itself, not the stick. And then diffraction is the spreading of a wave through an opening. Okay. Now, how would I do this problem if I didn't know some of these words? I've seen students get this question wrong despite knowing what the word that they chose meant. In other words, I've literally seen students select an answer that they personally can verify is incorrect. What mistake did those students make? They actually didn't verify the definition of they didn't verify with themselves whether they knew what a certain word meant. Like, for example, if you don't know what this situation is describing, but you remember that to get interference, you can have a constructive interference or destructive interference. If you remember that, then you can eliminate interference, right? So that's the only suggestion that I could really make with these. Some of these you might actually know, like index, you might remember, oh, where is the word refraction used? Index of refraction. The index of refraction is used when like light is going from air to water, or from water to air, or from like plastic to glass, or from like diamond to glass, or diamond to water, or diamond to air. That's index of refraction. That's index of refraction. So in that situation, we have refraction, and that's not a curving of the light. It's just a quick bending of the light before it continues in a different straight direction. So now, if I just remembered what those two words meant, I'm at a 50-50 chance of getting it right, and I'm at a passing problem. Now, you may not be at a passing problem, but vice versa, you may also have remembered that reflection is the bouncing of a wave off a surface. That's the one that I personally remember every time. Reflection happens when you bounce a wave off of a surface. And this light wave is not bouncing off of a surface. It's not bouncing off the wall. It's going through the opening in the wall, which leaves only, again, the diffraction as the answer, the spreading of the wave through an opening. Well, look at that subliminal message to subscribe. If you gotten to look, I don't like begging for subscriptions because I don't believe in that. Now the number of subscribers might be going up, might be going down because this actually I bought this thing like a week ago or 2 weeks ago. I just wanted to display my the number of subscribers that I have. Um, it can go up or it can go down in the middle of a video because the way subscriptions work, you usually get like 10 subscribers and lose one, get 10 and lose one. Uh, Actually, I was at 850, I believe, at the beginning of this video, so I'm at 851. Now, this video is not recorded live, so when you click subscribe, it won't show up in the middle of my video, but because this is actually a physical object in front of me, as opposed to kind of being a fake display showing my number of subscribers, but from YouTube as you're watching it, but as I'm creating it. But on a future video that you watch, one of these subscribers that you see will be you. So if you've made it through this point, it means that this video has been helping you. I feel like I've earned your subscription, and if you agree and you feel like I've earned your subscription, please do click the subscribe button. I really do appreciate it. It is what allows me to actually fund the creation of these totally free videos, which clearly take many, many hours to make. How many hours am I in? Uh, I'm looking for the timer. Uh, well, you could see the timer right below, right? Uh, I forgot where the timer is and it's tiny letters, but wherever it is, for me it's 3 hours 24 minutes. So clearly it takes time, and I might have deleted something earlier. So if it's not 3 hours 24 minutes, oh well. But the point is, I also do the test beforehand so that I know what I want to say while I'm making the video. So easily this video is 20 hours in the making for free because YouTube gets the entirety of the ad revenue. So if you do subscribe, it helps me get closer to funding this channel through ad revenue. And for the 851, if you're one of the 851, I really do appreciate having subscribed. It really does help me a tremendous amount. Número 32, number 32, a sound wave is emitted by a vibrating tuning fork. What is transferred as the sound wave travels to a student's ear? Mass only, or energy only, or both mass and energy, or neither mass nor energy? I know for a fact that when I hear a tuning fork, I didn't just get heavier on the scale. And so I have a strong suspicion that mass is not going to be included. I have a strong suspicion. Um, and I fully know that neither mass nor energy can't be the answer. Something had to have been transmitted, right? I got something. Mass or energy had to be transmitted. So I think two of the answers are wrong, and I know one of the answers is wrong. I have a somewhere between a 1 in 3 and a 1 in 1, meaning 33% chance and a 100% chance of getting it right. But I want to address why the answer is not one or the other. After all, I could. What if mass gets transmitted, but it then leaves when the sound kind of goes away? Maybe that happens, but it doesn't, and that's really, really, really important to know. That's not how sound gets transmitted. That's not how waves work at all. I do want you to remember this. The way that waves work the way that waves work, energy is transmitted. Waves transmit energy. So how can a wave transmit energy from a tuning fork to my ear, but not transmit mass? Well, the reason is the thing that is traveling is a pressure wave. It is a pressure wave, but you don't feel it as a pressure wave. After all, if it had a low frequency, you'd literally feel that. You would literally feel that. If it was a low frequency but loud enough, there are sounds that are at that frequency going on around you all the time, and you don't feel them because the amplitude is so low. But if it was a frequency that loud that you'd feel it, it would also be damaging your ears and probably be injuring you to the point that you wouldn't be enjoying it for very long. Um, but that is actually what's happening. You literally are having pressure waves where the pressure is increasing and then decreasing and increasing and then decreasing and then increasing and then decreasing. And if that was what's happening at a super low frequency, but at super high amplitude, you would literally be being pushed like this, and you would literally be doing that. Thank goodness you're not experiencing that, because a wave of that magnitude that's able to push you that much would probably tear you apart. We're talking about like explosion, A bomb, for example. Um, that said, uh, that that analogy where something gets pushed and pulled and pushed and pulled is is what's happening at your eardrum. Your eardrum is literally being pushed and pulled and pushed and pulled. And now, if the tuning fork is 440 hertz, that's 440 hertz. That's equal to 440 pushes and pulls on your eardrums every second. Now, there are really rare people who can actually hear extremely low frequencies, and they actually can describe it often as a frequency that you feel, a push and a pull. Sometimes, depending on the situation, I sometimes detect those, but I'm not even 100% sure that I detect them in my eardrums. So I wonder if those people who can detect them uh, really detect them in their eardrums, or if it's something else, or if it's like their hairs in their bodies or something else. Um, but that is literally what is happening. Think earthquake, though. If you've ever been in an earthquake, which actually now New Yorkers can say that we've experienced, because we recently did have an earthquake in New Jersey that transmitted all the way to New York, and a lot of people in New York felt that earthquake that day. Or you may have felt an earthquake at a different time. Um, yeah, that's literally what's happening in your eardrum. Your eardrum is being pushed and pulled 440 times per second when you get a 440 hertz sound. And but the mass is not being transmitted. It's just a pressure wave. The air literally, like let's say somewhere between me and the microphone, if I go ooh, that sounds like a constant tone, but what's really happening is my vocal cords are vibrating at a constant rate, somewhere around 440. Although I don't know the frequencies, so which nor can I sing. So if I go ooh, the sound is literally doing, the air is literally going back and forth in front of me. Now I'm gonna go here because my microphone's right there in front of me, like that. So the air is not being transmitted; it's shaking back and forth, and it's arriving at the microphone. And the microphone has a little thing, and the little thing on the microphone is going back and forth, and it's detecting that vibration. Only energy is being transmitted when a sound is travels. Okay? Número 33, number 33. An electric current passing through a copper wire at a constant temperature would result in an increase in the resistivity of the wire, or a decrease in the resistivity of the wire, or the emission of protons from the wire, or a production of a magnetic field around the wire. Now, this is one where some students might struggle with it because it breaks their intuition. There's something new that they didn't know about in physics. And I hope that your teacher got to talk about it with you. But I happen to know the answer to this because my teacher got to talk about it with me. If electrons are flowing through a copper wire, and a current is flowing that way, then you actually get a magnetic field around the wire, going around the wire. So literally down on the other side. Let me see if I'm getting this right. Am I getting it right? Or down on one side. I think it actually is coming up on the back of the page towards me. So towards me, down in front of the page, and then into the page under. So I think that's right. Okay. Where if the current is positive current, which is how we usually treat current. That's intuition. So this is a magnetic field. Moving electric charges create a magnetic field. Moving electric fields create magnetic fields. So knowing that, immediately I know the answer to this question. But let's address what I would do if I didn't know that. I mean, again, your intuition might break so much on this one because you didn't know that at all. Well, I don't know what to say because if you didn't know that, but you might be able to eliminate 3 of the 4 choices, and that might get you to the right answer. Here, an electric current passing through a copper wire at a constant temperature. Constant temperature. I know that temperature changes resistivity. Okay, which changes resistance. But constant temperature doesn't change the resistivity, right? So the electric current doesn't change the resistivity. Now, also doesn't decrease the resistivity. So there's not a decrease in resistivity either, which eliminates choice 1 and choice 2. So even if I didn't know how to do this question, I eliminated choice 1 and choice 2. Now that I'm stuck with choice 3 and choice 4, and the thing is, if I didn't know that a magnetic field was produced by a wire, flowing electricity in a wire, then I look at choice 3 and it says the emission of protons from the wire. Oof. Wires might, in some interesting situations, might emit electrons. Like, for example, if you increase the voltage to a level that the wire itself can't handle, you might see some sparks. But those are electrons. The wire will not emit protons. This would literally require radioactive decay, which is a tremendous, tremendous amount of energy. So that actually gets eliminated too. And then the one answer that I think may be a little bit unintuitive for me, that the production of a magnetic field, if I didn't know that, that one's the correct answer. But the answer is that you do get a magnetic field going around a wire with a current. The reason you see me doing this thing is that if my thumb points in the direction of the current, and actually I see that the current for me, so I'm looking at the sheet, so I'm looking at the sheet my way. But now if I'm looking at the sheet your way, now that my thumb is pointing in that direction. Oh, but then actually what I should be doing is this. There we go. There we go. I should actually be facing. Does it matter? It doesn't matter. If the current is going this way, then the current goes that way in one direction, and then this way in the other direction. Now the problem is that I'm also on the page. So that I think is what's causing the intuition break from me explaining it to you versus you explaining it to yourself. So what you need to do is you take your thumb, your right thumb, and it has to be your right thumb because this is the right hand rule. Your right thumb, you point it in the direction of the current, then your fingers curl in the direction of the magnetic field. So it goes out of the page on top of the wire, down in front of the wire, into the page under the wire, and then up up on the other side of the page. And that it does happen that way. It is real life true, truly does happen. That's one of the ways that, in fact, people can create magnetic fields without having to have permanent magnets. An electromagnet is creates a magnetic field that way. Número 34, number 34. The velocity of an object in uniform circular motion has a, so again, uniform circular motion, so V equals constant, and this is a circular motion. That's important. So the velocity of an object in uniform circular motion has a constant magnitude. This is the velocity, constant magnitude in changing direction, or constant magnitude in constant direction, or changing magnitude in constant direction, or changing magnitude in changing direction. Uniform, a circle, it's moving in uniform circular motion. I mean, this is going around a circle. Let's say it's going counterclockwise. I know that this does make a nice circle for me, so let's make a nice circle. Nice. Going around a circle, uniform circular motion. I mean, does the direction change if you're going around a circle? Does the direction change? Is my direction changing as I'm going around the circle? Did my direction change? Absolutely. Direction is changing. Direction changes for a fact, even if I didn't know what uniform circular motion is. But you do need to know what uniform circular motion is, yes. So does the direction change? Yes. Does the direction change? Yes. Does the direction change? Yes. Does direction change? Yes. So now the question is, this is a 2x2 question again. Constant magnitude and changing direction, or changing magnitude and changing direction? Now this is where you would need to know. If you're going around a circle, let's say you're going around a perfectly circular track, you could hit the gas, you could let go of the gas, you could hit the brakes, you could slam on the gas, or you could keep the gas at a constant rate. Which one is the uniform circular motion? So uniform circular motion. The velocity magnitude is equal to a constant, but the acceleration centripetal is equal to a constant, and it points towards, okay, so actually the acceleration, centripetal acceleration is constant, but the acceleration linear is equal to a constant magnitude, but the acceleration vector changes direction. So how could it be, wait, a centripetal acceleration and acceleration vector? The acceleration in uniform circular motion is a constant. This is what AC is. That constant is the centripetal acceleration. The vector, the linear acceleration, is a vector. So it points towards the center of rotation. No matter where the object is. So if the object is up here, so the velocity will point that way, but the acceleration would point in. But if the object was here, the velocity would be down and the acceleration would point in. Notice that the velocity changed, but the magnitude of the acceleration didn't change, but the velocity's direction definitely changed to the left, down, to the right. And I'm just gonna, not to complete the circle, but I'm gonna put it right over here. Then the velocity is perpendicular or parallel to the circle, but the acceleration is perpendicular and in the direction of the circle, in the direction of the center of the circle. So yeah, the acceleration changes direction, so the velocity changes direction. So the constant magnitude, though, is the incorrect one. The constant magnitude is correct. The only one that has two checkboxes is choice 1. So I crossed out 2 and 3, and now I crossed out 4, and the answer is choice 1. Number 35. I don't know why they didn't put the tuning fork ones together. That would have been nice. After all, they usually do. Number 35, número 35, the tuning fork A starts to vibrate at 320 hertz when it is held. Um, I'm going to put F for frequency. When it's held near tuning fork B, already vibrating at 320 hertz, same frequency, which phenomenon is exemplified by the action of tuning fork A? Doppler effect, resonance, diffraction, refraction. So we've already defined two of these, diffraction and refraction. I would pause and say, what does refraction mean? You tell me, what does refraction mean? If you said that it's a bending of a ray when passing through one medium to another, you'd be right. And if I asked you what diffraction is, if you said that it's a spreading of a wave passing through an opening, you'd also be right there. So it's neither of these. Now the question is it resonance or Doppler effect? And it happens to be that we've also talked about the Doppler effect. Okay, this is equal to the change change. I don't know what language that is. Change in perceived frequency of a sound, of a source sound, due to relative motion of the source and receiver in a medium. The ambulance going by, that's the Doppler effect. Over here, higher pitch because it's going towards you, that's Doppler effect. That's Doppler effect, and then that's Doppler effect. The entire thing is Doppler effect. So why does the frequency go from like to but has this transition in between while it's gotten close to you? So it's constant. It feels constant here, constant as it's moving away from you, but low, and it feels constant here while it's moving towards you, but high. But then in between, it has this smooth transition. The reason for that is actually having to do with the Doppler effect equation that you don't have to know, but if you're a nerd and you want to scroll, if you want to slide back up to where I gave the Doppler effect equation, then you'll see that the Doppler effect is a function of the velocity of the object relative to not just the air around it, but you. And the point in between you and the object is moving as the object is moving. So as it's moving past you, it's moving at a constant speed, say, but there's an angle between its movement and you. And so the velocity of the object relative to you is not its velocity, or rather its speed relative to you is not the magnitude of its velocity, but rather the magnitude of the tangential velocity, which because of the let's see, cos theta, if it makes an angle of theta 0 to 180, then the angle goes from 0 to 180. And as it's doing that, the speed of but it's doing that so smoothly, but as it's doing that, that makes the speed of the source relative to you go from some positive number, some large positive number, to some large negative number, smoothly transitioning to that. As the theta transitions from a zero slowly towards like 1, 2, 3, and then all of a sudden 90, 99, 120, 120, 50, 180, almost 180. And that's why there's a smooth transition. And that's why I go, that's why it makes that sound. So that's what Doppler effect is. So resonance, though, is now something we have to define. Resonance is the tendency of two objects to simultaneously vibrate at the same frequency, at the same resonant frequency. So I know I'm using the word resonance and resonant, but we'll keep it resonant frequency in a medium. Okay. So, fun question. You might wonder, how can we hear if our eardrum doesn't have the same resonant frequency as like the thing that we're hearing, right? Well, it happens to be many objects have, as built, have like this one really very primary resonant frequency. So, like for example, an object that has a length has like one single primary resonant frequency, but it actually has a lot of resonant frequencies. Just that many of the resonant frequencies barely occur because they're too short in some direction. But when you have something like, for example, uh, a sheet tied down in certain ways, that sheet can have many resonant frequencies, and our eardrums can vibrate at many frequencies, so we can detect many frequencies of sounds. That's why we can hear like a singer next to me and me, and then a very deep singer and maybe somebody playing on a guitar, and all the notes from the guitar, you could hear them all simultaneously because they all resonate with your eardrum. But the tuning fork, which is made to vibrate at a really specific frequency, doesn't really pick up other frequencies. It vibrates at the same frequency as another tuning fork when it's hit, because the tuning fork that's vibrating vibrates the air. The vibrations reach the other tuning fork, and because the frequency of that tuning fork happens to match the frequency of the air's vibrations start to vibrate the other tuning fork, and so it actually starts to vibrate. Okay. So, for part B, you'll notice that part B questions are extremely similar to part A questions. So I'm not even going to necessarily address the differences between the two parts, other than you still need your reference table, and you might need a lot more calculations than you did before. Number 36, number 36. A light ray with frequency 5.09 times 10 to the 14th hertz has a wavelength of 2.44 times 10 to the negative 7 meters in a diamond. The wavelength of this light ray in sodium chloride is 1.55 times 10 to the negative 7th meters, or 2.44 times 10 to the negative 7th meters, or 3.83 times 10 to the negative 7th meters, or 5.89 times 10 to the negative 7th meters. Okay, so I can't eliminate any based on not if I don't know anything, but I suspect that this one's going to be wrong. Fake student me suspects that one's going to be wrong, because I remember that when light transitions from one medium into another, the wavelength changes. So we're asking about the wavelength. So let's talk about this. This is F1 and lambda 1, and this is asking about lambda 2. I'm gonna say now. I'm not gonna say F1 and lambda 1. I'm actually gonna say F diamond, so FD and lambda D, and then it's gonna pass through sodium chloride, so SC. And my guess is it's gonna change unless they have the same indices of refraction. But we go to waves, and I'm gonna go back and I'm gonna post the as I did before, and just a couple of them. I'm gonna post the glossary over here, because you do need to know some of these numbers. But what I will say this is this, that these numbers, the reason, do you need all of these details? No, because it turns out that there's another one, not the resistivities, the indices of refraction. You need these. Now, it turns out that even though I personally am not going to use all of the details that this thing gave me, it turns out that there are ways to do this problem using some of those extra details. Okay, so now I look for the diamond. Diamond has an absolute index of refraction. of 2.42. And then the other one was sodium chloride, has an absolute index of refraction of 1.54. Okay? So is it possible to do this problem in multiple ways? I will say this. This is a thing that you do need to know. N2 over N1 equals V1 over V2 equals lambda 1 over lambda 2. It's important that to know that F1 equals F2. That equation is not there. And it doesn't have to be because it can be verified using the equations that are already here. But, like specifically V equals F lambda. But you want to, but it is worthwhile to know that. Like if a red light passes through the air and passes into a diamond, and then passes into sodium chloride, and then passes back into water, and then into air again, if it does all of that, in every single one, if the light ray was red, the light ray is red in all of them. The light ray, the frequency doesn't change. So, yeah, so I'm putting that there. But I noticed that N2 over N1 equals V1 over V2 equals lambda 1 over lambda 2. And I noticed the indices are reversed, N2 over N1 versus V1 over V2 and lambda 1 over lambda 2, which means that N1 and the indices of refraction are inversely proportional to the velocities and the wavelengths. So this is passing from diamond to sodium chloride with a lower index of refraction. Since the index of refraction of sodium chloride is lower, and these are inversely proportional, the wavelength is going to go up, which eliminates for sure choice 2 because the indices of refraction are different, but it also eliminates choice 1 because lambda is going to go up. The wavelength is going to go up. Now, let's actually do the calculation because we still have choice 3 and choice 4. We don't know which one it's going to be. We have N2 over N1 is equal to lambda, and I'm not using n's and or 2's and 1's, I'm using D and SC, N sub diamond over N sub sodium chloride equals inversely proportional lambda sodium chloride over N over lambda diamond. Okay, so I'm going to put these numbers in. N diamond, 2.42, over sodium chloride, and sodium chloride, 1.54, is equal to lambda sodium chloride, lambda, which is unknown, have or need. Remember, have or need. It's okay that I don't have this. Divided by the wavelength in diamond, 2.44 times 10 to the negative 7. Okay? Now, I actually can do a little bit of estimating here. Like, for example, I noticed that 2.42 is not double 1.54. Double 1.54 is 3 and change, 3.08, which means that the wavelength is not going to double, which means that this one is already looking too big, which means I'm gravitating now towards 3. But to calculate the answer, definitely got to do this. And this is definitely not work that you want to skip. You want to see me do this. Lambda SC times 1.54 is equal to 2.42 times 2.44 times 10 to the negative 7 divided by 1.5, so I divide by 1.54, divide by 1.54 to get rid of that 1.54. And I got that lambda SC is equal to, and as I recommended before, I am going to put the entire decimal on paper. Well, actually, this one doesn't require me to put the decimal on paper, but I'm going to show you how I do it on a test so that you see when I do the part 3's and 4's why I do it that way. Okay, let's see. Parentheses, 2.42. Close and open. Open, oh, too many. 2.44 times 10 to the power of negative 7. Close, divided by parentheses, 1.54. And I better not get an answer that's more than double. Choice 3 better be coming out at me. 3.83428571. Okay, so I'm going to put this here. Okay. Again, as I mentioned, I'm going to put this whole decimal, 3.83428571 times 10 to the negative 7th meters. Oh, I should put here meters for the purposes of, the ones where you have to show work. And then I round 3.83 times 10 to the negative 7th meters. Okay? Choice 3. Could I have done this by estimating? Yeah. Well, I just did, didn't I? I knew the answer had to be bigger than 2.44 because I saw the index of refraction shrunk from diamond to sodium chloride, which means the wavelength had to go up, and so that left 2 answers. But since the index of refraction didn't get cut in half, so the wavelength couldn't double, and the 5.89 is just way too close to double. And so the answer had to kind of be 3.83. Okay? Número 37, number 37. The diagram below shows resistors R1, R2, and R3 connected to a 12-volt source. And I see that 12-volt source, 15, 21, and 24, and I see they're connected in series. But I don't take it in more than that right now. Then I see the current flowing through resistor 3 is it 5 amps, 2 amps, 0.5 amps, or 0.2 amps? I love process of elimination here. And I remember the formula V equals IR. Now, if I don't remember that, well, luckily, as we know, we've already been introduced so many times to the fact that this is a heavy formula-centric equation, formula-centric regions. If you don't like V equals IR because the test has R equals, V over I, well, it's the same formula. I was taught V equals IR, so that's what I gravitate towards. But if you want R equals V over I, then fine. But why I'm mentioning this, I notice that if I have a high resistance, given a constant current of voltage, if I have a high resistance, then I have a low current. And these resistors are connected in series. So that means that the resistance adds. And I have a 12-volt source that 15 plus 21 plus 24 is bigger than 12. So the current has to be smaller than 1. I is less than 1, which eliminates choice 1 and choice 2. That's a benefit. You might say there's no benefit because that just eliminated 2 choices, but not 3. Well, I will also say this, that the total resistance is also more than double the number 12, which also does eliminate the number half. So, but if you didn't realize that, I don't like giving the answer before actually doing the calculation because way too many of you just skip the way to do the problem without actually doing it. So, this now, I did mention that most problems are a one equation problem. I don't know how you would do this one in one equation other than just sticking all the equations into one. This is one of the few problems that I actually did use 2 equations. Of course, you kind of need to use 2 equations. You need to know that this is a series circuit. Okay. Why is it a series circuit? Because the resistors are connected in series. So Req is equal to R1 plus R2 plus R3. Now, how do I know that these are connected in series? Because the current cannot split. And how do I know the current cannot split? Because if I start at the voltage source and I go around, there's nowhere that, like, it would literally have to have a second wire going somewhere else. There's nowhere that a second wire appears. Literally going around, there's nowhere to go. but right back to the battery. These are in series. The current cannot split, so these are in series. And so the REQ is equal to, well, 15 ohms plus 21 ohms plus 24 ohms, okay? Which does add up to, according to the calculator that you're gonna use obsessively, 60 ohms, okay? So REQ is equal to 60 ohms. And so now we have 12 volts is equal to some mystery I times 60 ohms. If I divide by 60 ohms, I divide by 60 ohms, I got that I is equal to 12 divided by 60. If I like doing my arithmetic on paper, then I could get that. But we're not in algebra class, so we don't worry about using calculators. Let's just use it. 12 divided by 60 is equal to 0.2. 0.20 amps. Leaving choice 4 as the only viable answer. I added this image over here to show you what current is. Current is literally just the amount of charge flowing through a given part of a wire per unit time. So in this case, if all 4 charges, let's say each charge is 1 coulomb, 1 coulomb, 1 coulomb, 1 coulomb. Let's say that passes through every second. Well, that's 4 coulombs per second. That's equal to 4 amps. That's what an amp is. So 1 coulomb per second is equal to 1 amp. So that's what an amp is. It's equal to a coulomb per second passing through a given region. And so if you have 4 coulombs passing through a given region, then you have a 4 coulomb charge. But if you time it, and it looks like, I can't tell if this charge made it quite through, but this charge and this charge and this charge of 1 coulomb, let's say, pass through that given area in 1 second, then the current would be 3 coulombs. And then this charge, maybe plus another 2 other charges that you aren't labeled, pass through the region, that's another 3 coulombs in a second. Yes, the current would be 3 amps. So the current here, the current is the number of coulombs passing through a given region of a wire every second. Okay? So this one says, number 38, number 38, a charge of 25 coulombs moves past a point in a circuit in 2.5 seconds. What is the current at the point in that circuit? Well, 25 coulombs passing through that point is in 2.5 seconds. That's equal to 10 coulombs per second, which is equal to 10 amps. I would have eliminated this one immediately because that's too few coulomb, that's too small. And this one, there's no way to get 63. Technically, there are ways to get 63 using very incorrect methods, but the 25 and the 2.5, if you divide them, you don't get 63. This is what happens when you multiply the 25 and the 2.5. You get a 63. Okay? I'm not sure how you would get a 50. Now, is there a hint that 63 might be wrong? Well, the hint that 63 might be wrong, if you did 25 times 2.5, the hint that might be wrong is that if you think about it this way, what if you increased the amount of time it takes for the coulombs to pass through? That's a decrease in a current. Like if the current takes way longer to pass through, that's a smaller current. But if you take the time, which is way, way, way longer, and multiply it by the coulombs, you get a bigger number, which means it can't be that the charge times the time is the current. So notice that implies that the current is equal to amount of charge divided by a time. Actually, I should mention that we know, ideally we would know that, right? Except if you notice, right on the formula sheet, that formula does appear there. The amount of charge passing through a given point in a certain amount of time. So the formula is on the sheet. Let me put a delta Q there because that's the way the sheet has it. So it is there. A lot of things, there's ideally a lot of things that you would know, but the test is friendly and allows you to not necessarily know them. Number 39, number 39. Which statement describes an object with constant kinetic energy? Constant kinetic energy. And I remember from my formula sheet that I'm not going to look it up now. Kinetic energy is equal to 1/2 mv squared. So let's see, constant kinetic energy. A car that accelerates along a straight road, constant kinetic energy. A runner decreases her speed along curved path. Or a bicycle travels around a curve at a constant speed. That one's looking a lot better. Or a sled traveled down a frictionless steep straight hill. Now, this is the only one that I think, the choice 4 that I think for some students might be viable. But the thing is that if it's a steep, frictionless straight hill, then there's a gravitational force. There's a gravitational force. And then there's a normal force. And then the FG can be split into F. This is theta, because that's theta. FG cos theta. And then might maybe put a negative sign here. And then I would put maybe here FG sine theta. If down the hill is my positive, okay? Then notice that my F net is equal to FG sine theta. Oh, I should maybe mention this, that Fn is actually equal to Fg cos theta. Since the sled is not flying off, the F normal is equal to the gravitational force perpendicular to the hill. But there is nothing counteracting the gravitational force down the hill. So the sled just slides at an accelerating rate since it's frictionless. So there is not equal to 0, which implies that V is not equal to 0. And A is not equal to 0 down the hill. One-dimensional problem. So implies that V downhill is increasing. So that's not it. And so the only answer remaining is choice 3. Going from there to numero 40, number 40. And let's see, which phrase describes a box in equilibrium? In equilibrium. Is it a box in an elevator slowing down as it rises vertically? Or a box at rest on a stationary table? Or a box sliding down a frictionless ramp? Or a box in free fall? Wow. So this one, I think as a number 40, it's pretty far down the test, but I think it's a little bit of a gift. Because if I didn't know the definition of equilibrium, there are some surprising surprising cases for an object in equilibrium. But if I didn't know what equilibrium is, but I kind of understood that there's a certain stasis when things are in equilibrium from biology, from physics, then the one that makes the most sense by a lot is this one. Stationary on at rest on a stationary table. Normally speaking, I go for eliminating the answers that don't make sense. And when I think of answers not making sense, slowing down as it rises, that one doesn't make sense. And then sliding down a frictionless ramp, both of these have A not equal to 0. This one has A not equal to 0. And it has F net not equal to 0. F net not equal to 0. So those are the ones that don't make sense to me at all. But at the same time, like I might be arguing with myself about a box in free fall versus at rest on a stationary table because like I remember some weird thing that my teacher told me about skydivers, right? But if I had to choose which one is in equilibrium between something in free fall versus something at rest on a stationary table, I think that this Fairlife that's sitting now on my bookshelf is at rest and stationary and looks very much in equilibrium. One of the rare cases where I think going for the one that makes the most sense probably is wise. Now, why do I think that some students even debate choice four? Because they forget the difference between free fall and the fake life where air resistance is zero. In free fall, air resistance equals zero. And then the real life situation where a skydiver is falling through the air. When a skydiver is falling through the air, they are encountering air resistance. Air resistance is a force and it pushes upward. It's a frictional force. The gravitational force for a skydiver changes basically zero because their distance from the center of the earth is so small compared to the actual radius of the earth. The radius of the earth is like 6.3 million meters, whereas they might be a couple thousand meters up max. So we're talking about 6,000 kilometers versus a few kilometers, 10 kilometers, let's say. So that we don't even take into account that gravitational force difference. It's basically constant. And as you know, we actually treat it as being constant, except for when it really, really, really matters. Well, what happens with a skydiver though is they're encountering air resistance. So their acceleration due to gravity is that 9.81 only for that very first instant, but very quickly they encounter a whole lot of wind coming at their faces. So eventually the air resistance resists their acceleration so much that the skydiver reaches terminal velocity. A skydiver reaches terminal velocity. At that point, their acceleration is zero because air resistance is pushing on them. So that's not free fall. Okay, so I want you to remember this: an equilibrium. This means that F net equals zero. You do need to know that. F net equals zero. It doesn't mean the object isn't moving. It doesn't mean the object is moving. It means that F net is equal to zero. And if the object is literally just not accelerating at all because F net is equal to zero, then it's equilibrium. So wait, are we saying that a skydiver at terminal velocity is in equilibrium? Yes. And that's the thing that causes students to mess up with number four because they take the skydiver falling and they call it free fall when the skydiver falling is not in free fall. The skydiver falling is interacting with the air. That makes air resistance non-zero. Why is it that we treat air resistance as equaling zero in so many other situations? Because in most situations that we have to deal with in physics class, air resistance is so small that it just kind of gets in the way of our math. Do we know air resistance matters sometimes? Sure. I mean, when a pitcher pitches a ball, or when a tennis player serves, or if you've seen in the Olympics, which actually is occurring right now, the table tennis players, that the ball is so light, so not dense because it is filled with air, that air resistance is such a big factor, excuse me, in the way they play. But those are not the kind of situations that we deal with in a physics class. Why not? Because that's a more advanced problem. And in a real life situation, we could actually separate the no air resistance question from the air resistance question, treat them separately, and then calculate a final answer. So we could wait until we get to a level where air resistance starts to matter and let that happen in a more advanced physics class. So that's why the answer is choice 2 and not choice 4. Número 41, number 41. Quarks may combine to produce a meson of charge negative 1/3 E or plus 2E or plus 1/3 E or 0 E. A meson of charge what? So now if we go, now this is not going to tell, oh, I went too far. I went looking for the modern physics section. This is not going to tell us too much. Okay. It just unfortunately doesn't give us all the details, you know, but you know, they don't have to because it is a Regents. it's your, you know, your final exam. But let's actually do this. Let's actually talk about this a little bit. Okay. So quarks. There was a long time where we didn't even know that quarks existed. The speculation about whether quarks should exist turned out to start with math, interestingly, and then we just went and looked for them and found out that they're real. So why do quarks have charges that are like fractions of an elementary charge? Well, because we first defined an elementary charge as being a one or a negative one, and then it turns out that quarks have charges of plus 2/3 or minus 1/3, and anti-quarks have charges of plus 1/3 or minus 2/3. Uh, because just that's the fraction that it happens to be by coincidence. And so I want to make sure that we actually know what these types of particles are, right? Um, for the purposes of this test. And so, first off, what are leptons? Leptons are right here. Okay. So the electron, which is you're used to having it have a charge of -1 e. Remember, E is an elementary charge. I know that E is the symbol. This is weird. E is the symbol for an electron, but also E is the symbol for an elementary charge, so that an electron has a charge of -1 e. That also is weirdly historical. When we learned about charge flow, we actually thought that the positive charges flowed. Well, we knew that some charges flowed, right? And we thought so we called the charges that flow positive, right? And then the thing is though that we thought that the charge that flowed was the charge that we kind of like see in like thunder and lightning interactions, but it turns out that it's the opposite. The interaction that we see is with electrons, and so then it turns out that the charge of an electron is -1. So because of that, -1 e. But anyway, so a muon and a tau is also a lepton. Those are also leptons, and then their neutrino counterparts, which have neutral charge and very, very, very tiny masses, have charge 0, and they're leptons. Okay, so what are the hadrons? Well, the hadrons are made of quarks. Okay. Okay. So what is a meson? Actually, the meson, it tells you what a meson is. A meson is a quark plus its antiquark. So if you take a up quark and a antiquark and put them together, then a meson has charge uh, plus 2/3 minus 2/3 0. Notice again, a meson is a quark and an antiquark. Okay, which means that it's always going to have its charge. It's canceled by the anti-quark. Plus 2/3 minus 2/3, the Q is equal to 0. Plus 2/3 minus 2/3, charm plus anti-charm, 0. Top plus 2/3 plus, and then the anti-top minus 2/3, charge 0. A down and an anti-down, minus 1/3 plus 1/3 is 0. The strange and an anti-strange, minus 1/3 plus 1/3 is 0. And a bottom plus an anti-bottom, minus 1/3 plus 1/3 is 0. So a meson is always going to have a quark and anti-quark pair with a charge of 0. Whereas a baryon is always going to be 3 quarks. And it includes, right here it says it, okay? So I don't have to actually write 3 quarks. Let me not confuse it so that you don't think I didn't write it. 3 quarks. And that's, for example, a proton, protons, and neutrons, and other particles that can be created that are actually unstable. But protons and neutrons are examples of baryons. Antiprotons, and then there's other ones that are very unstable. But notice again, a quark, the charges that are made always end up being they do always end up being integers for protons, which eliminates a plus 1/3 and a minus 1/3. But we don't know that. But what about 2e? Well, again, this is about a meson. Meson always guaranteed to be a charge of 0. So if they had a +1, as one of the choices. I could imagine that some kids got it wrong, but if you happen to remember that a quark and an antiquark have a charge, so an antiquark charge is equal to the opposite of a quark charge. Therefore, a meson charge is always going to be equal to 0. Okay? Mesons always have a charge of 0. Whereas a baryon could have different charges. Número 42, number 42. Misspoke. Sorry. The diagram below. Okay. Número 42, number 42. The diagram below shows waves A and B as they travel through the region in the same medium. A goes up and then down and up and down, and B goes down and up and down and up. But I noticed that they have their nodes in the same places. Okay. That's probably going to be helpful. Okay. But I don't process the diagram much more than that. Then it says which wave best represents the superposition of waves A and B. So waves A and B can add together. And if it's weird to you to say that waves can add together, well, then I'll say this. Have you ever heard two people singing? Yes, their waves can add together. Have you ever heard two people singing the same note? Yes, their waves very much add together. Now, and this is an interesting one, have you ever heard two people singing, but one of them is singing slightly off key? If the answer is yes, then you might notice that the waves do this weird beating that because you get this constant constructive and then destructive and then constructive and then destructive interference. Well, the thing is that waves that have peaks in exactly the same places and troughs in exactly the same places interfere constructively and make a bigger amplitude wave, and waves that have a peak and a trough in the same place, they interfere destructively. So in other words, their peaks are in opposite places and their troughs are in opposite places. So these are going to interfere destructively. So you get this number, which is a -1 height, plus this number, which is a +2 of something height. 2 plus -1 is 1, so they're going to add up to a +1 height, a smaller amplitude. Oops. Let's try that again. A smaller amplitude but still an existing wave, which so that eliminates choice 2 because they don't interfere completely destructively because their amplitudes are different, which implies incomplete destruction. Okay, but this one, the amplitudes are they're 180 degrees out of phase. In other words, their amplitude, the crest of one matches the trough of the other, which means that we have destructive interference. And this one actually goes up to 4 and not 3. If they actually made it go up to 3, maybe more students would even accept this one. But because the true constructive interference would go up to 3. Let me actually be clear. Because if they had drawn the wave going up to 3, and down to -3, and then up to 3, and then down to -3, what I mean is to 3, to 3, and to -3. Since A goes up to 2 and down to -2, and B goes down to 1 and up to -1. If they had drawn this one, maybe a smaller fraction of students might have, or a slightly larger fraction of students might have chosen this one. But either way, both of these are incorrect. Going up to 4 and going up to 3 are both incorrect because we have destructive interference. Leaving choice 1 or choice 2, now which one is correct? Well, the blue one is correct. A, the magnitude of A is bigger than the amplitude of B. Therefore, the final wave, the sum, is in phase with A. So that eliminates that. I'm sorry, that does not eliminate this one. It eliminates this one, which is out of phase with A, and it keeps this one. So it's choice 3. From there, we go to número 43, number 43, and we are halfway officially through to a perfect grade on this 85 question region. So I'm really excited. If you're really excited too, just let me know. Click the like button and let me know in the comment if this video is something that is helping you. If there's something that you feel like I could improve, just let me know in the comments. If you have any questions, I actually do respond to my comments. So if you actually have any physics questions, do ask questions in the comments. And of course, if you have really deep questions and you actually need some tutoring, JuanTutors.com, I'm there for you. Número 43, number 43. The diagrams below show the direction of wave travel, and the direction of the medium particle. Oh, and the direction of the medium particle vibration. I deleted the word for, apparently. Four different waves. There we go. That was my mistake. I don't know if it was my mistake because I noticed that the large print test actually had some flaws. Some of the words were missing in one of the tests that I should have actually taken a better look at that. And I will next time. Actually, I'll just look at the regular print one because I noticed that it was not like a computer problem. I did print it and it doesn't print correctly either. So it was a PDF problem. And they should actually, I'm going to wag my finger at the Regents creators for that. I don't know if the actual final Regents as printed for the students had that flaw in it. But if it did, that is a bias against students who have vision problems. Now, if you say, well, no, because the one that's uploaded had the flaw, but the one that's printed didn't, well, that's still a bias towards kids who have vision problems because you know that teachers use these materials. So your PDF online has to be flawless. So go fix that PDF so that students who have vision problems can see the test better. Okay? But that said, rereading this question, number 43, número 43, the diagrams below show the direction of wave travel and the direction of medium particle vibration for different waves. Which diagram best represents the characteristics of a sound wave? Sound wave. We've talked about this a couple of times. Is the direction of travel to the right and direction of medium particle vibrations left and right? Or is the direction of wave travel to the right and the direction of medium particle vibration up and down? Or is the direction of travel to the right and the medium particle vibration in a circle? Or is the direction of travel to the right and the direction of medium vibration up and down as it moves to the right? Okay. So this is the one where we address the thing that we talked about before. Sounds do not cause the particles to translate on average in one direction. Yet another thing that may convince you of that, it might not be too convincing perhaps, but if you think about when you're hitting a drum, if the particles were moving in just one direction and not coming back, then slamming on the drum for an hour would eventually cause all the molecules around the drum to go away until the drummer had a vacuum around them. That's not a thing. You can keep hitting the drum and you still have the same amount of air around you because the air is not going away from the drummer. It's vibrating away and towards the drummer. Okay, so the one that we would eliminate immediately is choice 4 because the particles do not go away from the direction. Now the other one, the direction of the medium particle, do the particles go up and down as the wave travels to the right? No, because the particles are vibrating in the direction of travel. So remember, the particles are vibrating in the direction of travel. So it's not choice 2. They don't go in a circle. That's none of the waves that we ever discuss do that. So the only one that works is actually choice 1. And we do want you to remember, just like the drum in your ear moves back and forth, the eardrum, right, moves back and forth when it receives a sound. The reason it moves back and forth when it receives a sound is that the air around the eardrum is moving back and forth as the sound is being transmitted. So the sound does, as the sound moves to the right, the air moves back and forth. As the sound goes back this way, the air moves back and forth. Okay? So the sound travels in the direction of motion as it does in this one. So the particles, you could literally see them, the particles moving back and forth, the particles moving back and forth, the particles moving back and forth, the particles moving back and forth. Okay. Número 44, number 44. In a sample of gas, many excited hydrogen atoms are in the n equals 4 energy level. What is the maximum number of different proton energies that can be emitted by these atoms as they return to the ground state? 6, 5, 3, or 4? Interestingly, when I was doing this problem, immediately the number 6 popped into my brain. That's just like the math part of my brain. But I mean, do I expect you to know the answer 6 right away? No. I mean, that's not a thing. I don't think it's a thing at all. So how do we do this? Well, it actually is a reference table question because the reference table actually talks about the energy levels of mercury and hydrogen. Why does it do mercury and hydrogen? Because mercury has an immense number of electrons that are in many, many, many different ground states. So it has a lot of possible hops that it can make. Um, Many of them visible. Okay. So I'm going to take the hydrogen. Okay. Now, I do wonder, and maybe if there's anyone who does physics, I do wonder, and I don't know the answer to this question. I'm asking a question to which I don't know the answer. It happens to be that a lot of these ionization energies for hydrogen happen to be in the visible light spectrum. And now you might wonder, why am I talking about happen to be, happen to be? Well, here's the light spectrum of all light. It goes from energies of negative infinity to energies of positive infinity. Now, granted, uh, these ionizations are not, these are ionization energies on an electron volt, but you can convert these into uh, uh, corresponding wavelengths and frequencies of the photons that are absorbed or emitted. And it happens to be that a lot of these photons are right in this tiny, tiny visible light band. So I don't know the answer to this question, but here is the question. Why is it that so many of these uh, energy levels happen to correspond to visible light wavelengths? Is it coincidence or is there a reason? Is it coincidence? Is it a correlation issue or is there a reason? I do have a strong suspicion why the visible light spectrum is exactly this, by the way. And I do strongly believe, I don't know if we'll ever make contact with like actual sentient aliens, maybe millions of years from now, maybe 5 years from now, who knows? We don't know. Or maybe never. But I hope, one day. But that said, uh, I do believe that if we did, that there's a very large chance that their vision will be right around the same as ours. Maybe also a little bit beyond it on one side or the other, due to some interesting evolutionary reasons. But depending on what they happen to evolve from, we happen to evolve from apes, which did not see in the ultraviolet and did not see in the infrared. But there are animals that can see in the ultraviolet. There are animals that can see in the infrared. So and there are reasons for that, by the way. Uh, but that I strongly suspect there are reasons for that. And in fact, if you look at the atmosphere happens to be just about perfectly transparent, right in the visible light spectrum. But the moment you go beyond it in the infrared and beyond it in the ultraviolet, the atmosphere stops being perfectly transparent. If you could see in the ultraviolet, the atmosphere would look a little hazy. And if you could see in the infrared, the atmosphere again would look a little bit hazy. So uh, I strongly suspect that that's why we see exactly what we see. But again, it also happens to be that we evolved from an animal that also only needed to see the visible part, did not care about the infrared or ultraviolet. Had we evolved, for example, from dinosaurs or certain birds, or we might be able to see ultraviolet or infrared, or snakes, for example. Okay, That said, we need to know how many different photon energies can be emitted by the atoms as they return to the ground state. This is the thing that you need to know. The electron, it has to be in a state. It can't be in between, and it has to hop from certain energy levels to others. So it can only hop from, one possibility is that it hops from 4 to something lower to 3. Another possibility is it hops from 4 to 2. And another possibility is it hops from 4 to 1, which is one of the reasons why choice 3 is right there waiting for students. And you might say, well, that's the answer. But it does say as they return to the ground state. It doesn't say that it has to return to the ground state in one step. Because if it did have to return to the ground state in one step, it would actually only be one. Right? And one is not a choice. So the fact that we have 3 jumps here tells us that the answer actually has to be more than 3, because the first 2 jumps that we drew are at either n equals 3 or at n equals 2, which means it has further to go to get to the ground state. So the answer is greater than 3. Greater than 3. So that actually eliminates choice 3 at this point. Then if we go from n equals 3 to n equals 2, we can go to n equals 2, or we can go to n equals 1. That's 2 different photon energies. And if you wanted to know the exact photon energies, you could actually look at the energy with the numbers over here. Subtract these 2 numbers, subtract these 2 numbers, or subtract these 2 numbers, or subtract whatever numbers you need to subtract at the specific energy levels. So, and by the way, if you can't read this, the energy level at n equals 1 is negative 13.6. The energy level at n equals 2 is negative 3.4. The energy level at n equals 3 is negative 1.51. And the energy level at n equals 4 is negative 0.85. So if you want to know the difference between the energy levels, you just subtract those numbers. So now we have 2 more jumps. 3 plus 2 is equal to 5. But that's a hint that actually 5, well, definitely 4 is wrong. But that's a hint that 5 is also wrong, because now in this case, one of the jumps went from n equals 3 to n equals 2, and we still have one more jump to make, because at n equals 2, we're not at the ground state. We can jump down to n equals 1, which gives us one more. 5 plus 1 is equal to 6. So, and that's it. The particle could go from n equals 4 to n equals 1, or it could go from n equals 4 to 3 to 1, or n equals 4 to 3 to 2 to 1, or 4 to 2 to 1. Actually, so I'm miscounting. Those are the ones, I'm saying the wrong thing, because those are the jumps that it can make in a row. But the photons that you could see are n equals 4 to 3, n equals 4 to 2, n equals 4 to 1, n equals 3 to 2, n equals 3 to 1, n equals 2 to 1. All of those jumps are the jumps that we can make. And they all correspond to these arrows, the blue arrows, 3 blue arrows, 2 red arrows, and 1 black arrow. 3 plus 2 plus 1 is equal to 6. Now, this part of the test does give problems that are combined, okay? So multiple choice, multiple questions with the same phrases. So let's look at this. We have to base question 45 to 46 on the information below and the knowledge of physics. 2 students did an experiment to measure the acceleration of a freely falling object. 1 student dropped an object from rest. The other student measured the distance fallen by the object and the corresponding time of fall. The data for the dropped object are shown below. The distance of the fallen object is equal to 2.4 meters. The time of fall is equal to 0.71 seconds. And based on the data for the dropped object, the experimental value calculated for the object's acceleration, which would be like their calculated g, but a, okay? Now, again, so there's some missing information that we have to address. And I want to get you used to looking at these kinds of keywords. That means that VI from rest is equal to 0. And then VF is equal to a question mark. and A is equal to a question mark, and they want to know what what A is. So now I look for what I have or need. I have D, I have 2.4. I have T equals 0.71. I have VI equals 0. I have A is equal to a question mark. I can get this question in many different ways. Can I do it in one equation? Actually, there is an equation that has those have or needs. We have VI, D, T, and A. And I did make an estimate, by the way. I did make a guess, and I want to tell you what my guess is. It is based on trust, literally trust, based on trust. So, like, in other words, how can I eliminate choices from this? I mean, because I'm trying to calculate G. I know that G is 9.81 meters per second squared on the surface of the Earth, and it does say that on the reference table right up there. Uh, so even if you didn't know G somehow at this point of the Regents, it is on the reference table. But if I say trust, my trust, like I didn't know how to do this one, I would say that the answer is going to be close to 9.8, which 4.8 I'm going to guess is a little far, and 6.8 a little far. That's not necessarily good strategy. After all, maybe the apparatus was not very well set up. So it does require me to trust to say choice like 2-ish. But it turns out that I would have guessed right. But why not just look for an equation? Now, I want to point out here, is this equation the only way to do it? No, you could actually calculate VF and then used VF and VI and T to get A. There's multiple ways of doing this question. And I want you to remember that. If you can't find the one equation to do the problem, and as you know, I did a previous problem with two equations. One problem, two equations. So sometimes maybe that's a thing. Can you have done that one with one equation? I think that if you just threw all the numbers in, perhaps, but you'd have to know that it was in series to do that. I don't know. So this one, I'm going to do it with the one equation. But again, I could have gotten VF squared equals VI squared plus 2AD. No. Let's see. V equals D. No, I could have gotten V average equals D over T. Gotten V average. From V average, I could have gotten VF using VI plus VF over 2, because A is constant. Then from VF, I could have gotten VF equals VI plus AT. That's 3 equations. So yes, I could have done it that way, but I'm going to do it this way. So 2.4 D. Now, I called 2.4 downwards positive. So now downward is positive, is equal to VI 0 T 0.71 plus 1 half A T 0.71 squared. That cancels. So then I divide by, I can do this in one step. And actually, I do at this point recommend doing it in one step, but because you could have parentheses. I think it's more important to know that you need the parentheses than to know how to do it in multiple steps, for physics at least. 2.4 equals 1 half A 0.71 squared. To do this in one step, I have to divide by the entire coefficient of A. So divide by 1 half times 0.71 squared. In parentheses, divide by 1 half 0.71 squared, close parentheses. And I get that A equals, let's see in my calculator. By the way, 2.4 times 2 is 4.8. Now I'm dividing by 0.71 squared, which is a number smaller than 1. That confirms now that that confirms now. Okay, sorry, that confirms now that 4.8 is wrong. 4.8 divided by a number smaller than 1 is a number bigger than 1. So 2.4 divided by parentheses 1 half times parentheses 0.71 close parentheses squared close parentheses, enter, 9.52 9.52 9.5219205254. Okay, so now I know meters per second squared. And then I use my muscle memory to correct the correct number of sig figs, 9.5 meters per second squared. And I get a positive number. Leaving choice two, which is what I actually had to guess was going to be the answer if the experiment was well designed. I would just guessed close to 9.81. But again, I did this in one equation. Did you have to use my equation? No. Could you have done it in another way? Yeah, absolutely. Again, you could have used three equations to get it. Is it worth using the three equations to get it? Yeah, I think the three equation method is nice in certain ways. There are a lot of relationships between the physics equations. So many relationships, in fact, that physics allows for many different methods of solving problems, which is a nice thing. Okay. Um, Número 46. Number 46, the ideal value for the acceleration differs from the one obtained experimentally by the students. What is one possible cause of the discrepancy? So now they're talking about flaws in the experiment, right? 9.5 versus 9.81, they're different. So let's see. What did they say? In an experiment to measure the acceleration of a freely falling object, one student dropped an object from rest, and the other student measured the distance fallen by the object and the corresponding time of fall. The data for the dropped object are shown below. So let's see. Choice one. What are the possible flaws of causing the discrepancy? Choice one, the object was given some initial horizontal velocity, or the force of gravity was much stronger outside the building than inside, or the motion formula should not be used in experimental settings, or there may have been errors in measurements of distance and or time. So which ones of these cause errors? First off, the object was given some initial horizontal velocity. This is an important physical fact that you could separate the horizontal direction from the vertical. So this will not change the landing time. So choice one is incorrect. The force of gravity was much stronger outside the building than inside. No, this is very false, okay? The force of gravity is basically the same. Except for extreme changes in distances. How extreme are we talking? First off, a skydiver and us on the surface of the earth and me on the second floor right now experiences basically the same force of gravity. You on a plane and me on right now in my house, basically the same force of gravity. Okay, um, so literally everybody experiences the same force of gravity to the point where, like, satellites, which are between 100 and 150 kilometers up, and then some are 400 kilometers up, that already has a detectable difference in the force of gravity, but it's almost zero. It's almost zero because we're talking about, let's say 100 to 400 kilometers up versus the radius of the Earth, which is 6,300 ish kilometers. Okay, so that's that. This one is very false. The gravitational force outside and inside the building basically the same. Choice three: motion formulas should not be used in experimental settings. Uh, no, right? Because these are the. I mean, you have to get you. I mean, you get the formulas from somewhere, right? These formulas are all derived from experiment, by the way. Literally, all these formulas were derived from experiment. No one assumed them to be true. People suspected all of them to be true, but no one knew till they did the experiment. And in fact, these are so close to being 100% true that it took people like Albert Einstein to discover that the difference between the truth and what they thought is a bunch of decimal place out before you see a discrepancy. So that's how true they are. They may, so choice 4, there may have been errors in the measurement of the distance and or time. That's a source of error. Yeah, timer, you use lasers, the laser takes a small amount of time. Maybe the laser is connected to a voltage source, that the voltage transmission time, I mean, there's a lot of things you could do to cancel out a lot of errors, but there's a limit. So that one's definitely it. We are 46 points into a perfect grade on this region, so I'm really excited at what we've done so far. And we're learning a lot. We're learning a lot going into the regions to get a really super grade. So I'm really actually excited about that. Okay. Número 47, number 47. Which graph represents the motion of an object falling freely from rest near the surface of the moon? Is it choice 1, 2, 3, or 4? And we see choice 1 has an angled line, distance, and these are all distance versus time. You do have to look at the labels of the graphs, because if you're doing distance versus time, velocity versus time, acceleration versus time, those are different graphs. So again, falling freely from rest near the surface of the moon. So the distance, now something that might make a student choose choice 2. So okay, first off, the distance versus time. Choice 1 has a line going right up from the origin. Choice 2 has a line going straight down, from above down to 0 height over time. Choice 3 has a parabola coming in flat from the x-axis and from the time axis going up, and then choice 4 has like a parabola going up from the origin and becoming flat. So again, this object is falling freely from rest. In principle, it could have been choice 4 if it wasn't from rest, but it is from rest. So one reason why students might choose 2, the line going straight down, is because they're saying to themselves, I always call down negative, so this one is the only one that goes down, so like it's got to be choice 2, even though they know that motion, distance, is a parabolic function of time in free fall. So that's the key. The key to know this, to be able to eliminate answers, is that the distance is a parabolic function. Function of time in free fall. It doesn't matter if the object was thrown up in the air, or also, actually, maybe I should say vertical distance. So yeah, vertical distance is a parabolic function of time in free fall. It doesn't matter if you threw up the ball up in the air, or dropped it from rest, or even threw it in the downward direction. All of these, distance is a parabolic function of time, and it could be the upward part and then downward, or it could be just downward if up is positive, or it could be upward then to rest, and then if it's caught up there, or it could be just the downward part. It could be the downward part only a steep part, or upward only the steep part and then suddenly ending if it struck something. Either way, it's a parabolic function, distance versus time, crossing out choice 1 and choice 2, and leaving only choice 3 and choice 4. Now, the key is that you need from rest. From rest implies that VI is equal to 0. And you do have to remember that V is equal to D over T, according to displacement over time, according to the formula sheet. So if velocity is displacement over time and VI is equal to 0, then initially, basically D over T, that D is going to be equal to basically 0. So that's why the parabola from rest starts flat. So you might not like the fact that the parabola points upward in choice 3, but whereas the parabola in choice 4 seems to point downward, which is what you're maybe more accustomed to. But this thing was dropped from rest. It was not thrown up and then let to go arc up and then back down. It was dropped from rest. From rest. It started at a 0 velocity. So what's going on here? For this one, they called down equals the positive direction in this problem. And that's how we got, that's how we confirmed that the answer is 3. And this is not, that might be weird for you, but the truth is, if you remember, I did a problem that way too, right? I'm not going to scroll too far, but there was a problem that I did where I called down positive for the purposes of that problem. It just made it easier, right? So, número 48, number 48, the diagrams below represent the initial velocities for four identical projectiles launched from level ground at various angles above the horizontal. Which projectile, so this is VI, which projectile will have the longest time of flight? Neglect friction. 10 meters per second at 30 degrees from the horizontal, or 10 meters per second at 45 degrees from the horizontal, or 9 meters per second at 45 degrees from the horizontal, or 9 meters per second at 60 degrees from the horizontal. Even if you don't know how to do this question, and I really hope you do, pay attention to how I do it so that you can learn. Some of these answers can be eliminated. We have the longest time of flight, which means it has to stay in the air the longest. So if you compare choice 1 or choice 2, 10 meters per second at 30 degrees versus 10 meters per second at 45 degrees, 10 meters per second at 30 degrees, 10 meters per second at 45 degrees, I don't know which one will go farther. I do know which one will go farther. For a fact, I know that choice 2 will go farther. But because it's 45 degrees, that happens to be the maximizing angle. But point is, at 30 degrees versus 45 degrees at the same speed, 10 meters per second, is going to make the object fly long for a longer amount of time. So choice 1 cannot be the answer. T1, T2, T3, and T4. So T point is that T1 is going to be less than T2. That eliminates choice 1. What about choice 3? Choice 3 now, same angle of attack, but 9 meters per second instead of 10 meters per second relative to choice 2. Slower speed at the same angle of attack, it's not going to stay in the air longer. It's going to stay in the air for less time. So T3 is also less than T2. That crosses out choice 3. And now I have a passing problem, which is great, even if you didn't know how to do this question. Well, what is it? How can we actually do this question? So we know VI and we know VF. And I don't maybe have, I know I did have a little bit of intuition that caused me to choose one of the answers over the other. But I actually, I was not confident enough with the answer that I fully went and calculated the answer just to be 100% sure that I wasn't misleading. And the answers were actually a lot closer to each other than I expected. So here's the thing. You need to know the vertical flight time and the horizontal. Sure, it can help just to give you the intuition, but the thing is that you need the vertical flight time to determine the time. The horizontal flight time and the vertical flight time are literally the same amount of time. How do I know that the horizontal flight time and the vertical flight time are the same? And that breaks intuition for students sometimes, which is an interesting thing. But why is it that those two are the same? Well, they are the same because they because they're a single solid object, right? So I got distracted for a second because I realized I had to pay somebody. They're a single solid object flying through the air, right? So because they're a single solid object flying through the air, they are literally going to land at the same time, right? I mean, the object itself is going to land at a single time, right? You've never seen someone jump and then land horizontally and vertically at different times. No, they're a single solid object. They just land. So we have VI horizontally. Now, this is a part where you could use luckily the reference table does do you a little bit of a solid, even though we've been doing triangles for the whole year. It does you a solid by giving you the right triangle trigonometry. So it does give you this, but I'm going to give you this in the way that I prefer it, not because I think, not for any other reason other than I think it's important to have it this way. So you have sine theta equals A over C, but that implies that A is equal to C sine theta. And cos theta equals B over C, and that implies that B is equal to C cos theta. Okay? So C cos theta, and you have C times sine theta. Okay? And those are more useful in general. So as a result, the left velocity is going to be VI, which is, I can erase that, so 10 cos 45, and the vertical velocity is going to be 10 sine 45. And for choice 4, I could start with a straight line. That's cool. I just found that out. So I don't have to wait for it. Okay. This is going to be 9 cos 60 and 9 sine 60. Now, I remember that sine goes up as the angle goes up. So I have a 9 instead of a 10, but I have a sine 60, which is higher than a sine 45. So I can't just by comparing coefficients eliminate any of these answers. But I could do that to eliminate choice 3 and choice 1. That's good. If I didn't have the intuition that I just gave you. But the thing is that only the vertical velocity is going to matter for which one lands, which one takes the longest flight. So what do I have? I have, this is going to be my VIY. Okay. So, and I know my A is equal to negative G. My time is equal to be some mystery number. My displacement vertical, now this is the one that's important. My displacement vertical, so it's launched from a level ground, and which projectile will have the longest flight, which means that it's going to land on the level ground. So if it starts from the level ground and lands on the level ground, the vertical went up and then back down to the same height. So dy is equal to 0. So I know dy, okay? Now, are there some helpful things to know that can reduce the amount of work that you have for this problem? It is helpful to know what the final vertical velocity is going to be, but what if you don't know how to calculate it? So I have, if you didn't know the Fy, I know this one. So I know the formula from the formula sheet, which I've copied so many times, I'm just going to write it here. VFy squared equals VIY squared plus 2AD. So VFy squared is equal to VIY squared for choice 2. I have 10 cos 45. Nope, 10 sine 45. Squared minus 2 or plus 2 times negative 9.81 times vertical displacement, which is 0. That's equal to 0. Therefore, VFy squared is equal to 10 sine 45 squared. If I take the square root now, remember that I could just, okay, so let me actually rewrite it. VFy squared is equal to 10 sine 45, close parentheses, squared. If I take the square root, and remember to bring in the plus or minus, now I have that VFy squared is equal to either plus or minus 10 sine 45, but VFy is in the downward direction. So it's equal to negative 10 sine 45 in the downward direction. So I have that number. Okay? Now, you might wonder, why am I doing it this way? Because I said, let me go back to the formula sheet, because I said that there's often just one, you could do these problems with just one formula, right? But the problem is, the one that has everything you have or need is d equals VIT plus 1/2 AT squared. And this is a quadratic equation in terms of time. Yes, it is true, since dy is equal to 0, you could do this by factorization. So it is a viable way to do it without going into crazy algebra, but you'd need algebra. And that's my concern. I'm actually trying to avoid the algebra. I can avoid the algebra by just solving one equation at a time. So I have VFY is that. So now then I have VF is equal to VIY plus A minus plus G plus AT. If I subtract VIY, now this is for the nerds because I actually do often recommend, I have VFY, VIY, I have A, and I need T. I actually do generally recommend solving the equation with the variables first and then plugging it in. It helps students a lot. VFY minus VIY is equal to A, negative G, negative GT, divide by negative G, divide by negative G, and I get that T is equal to this number. And if you're wondering why I recommend it, well, it happens to be in higher level physics problems. This is a really helpful strategy. But in other problems, why it's helpful in higher level physics, it happens to be helpful in this problem. In this problem, if you notice, I've already solved for T for the choice 2, but I have it also done for choice 4. I don't have to do the algebra a second time because the algebra is already done with the variables. So I have 10, negative 10 actually, negative 10 sine 45 minus 10 sine 45, and I've missed my parenthesis there, close parentheses, divided by negative 9.81, and I get a 1.44 for this for choice 2. And for choice 4, I've done the algebra already, so I actually can say that VFY for choice 4 is going to be equal to negative 9 sine 60. So I have negative 9 sine 60. You might have already noticed that I could just multiply the negative 9 times 60 by 2. If you notice that, you could do that. 9 sine 60 divided by the same negative 9.81. You get 1.58. So T is around 1.44 seconds. And here, T is around 1.59 seconds. Could I have done that by intuition methods? I don't think so. Could I have done that using some basic properties of physics that I know? Like, I just calculated the time. Is there a faster way of doing it? There is a faster way of doing it. If you recognize that the time flying, before we go to number 49, if you recognize that the time flying is strictly a function of the vertical velocity, increasing the vertical velocity increases the time flying, decreasing the vertical velocity decreases the time flying, all you would have to do is get VIY, found that number, get VIY for the for choice 2 and choice 4, found out that the VIY for the choice 4 was bigger, and therefore choice 4 is the answer. But that requires you to know the physics. I need to be able to explain it to students who don't necessarily know that, so you could calculate it, okay? Had I just done that in the beginning, then too many students would skip that process of solving for it without actually knowing how to do the problem. But now you know how to do the problem in 2 different ways. three different ways, because I said d equals bit plus 1/2 at squared could have done it for you in just one equation had you, but it requires algebra, including factoring. All right, number 49. Four forces act on a crate on a level floor, as shown in the diagram below. I see F is 50. I see F rope is 100. I see Fn is 150, and I see Fg is 150, negative 150. I'm gonna put some signs here. I'm gonna put negative and negative because I prefer these to be vectors. I prefer my labels to be vectors. Now, at the instant shown, yes, at the instant shown, yeah, I'm gonna do it that way. At the instant shown, the crate is accelerating to the right, or accelerating to the left, or moving at a constant velocity to the right, or remaining at rest. Four forces acting on a crate on a level floor, and we know the friction is 50, but the force of the rope is 100. The force of the rope is dominating the frictional force. So it's definitely not remaining at rest. In fact, it doesn't matter what our personal opinions are about the way we think the problem should work. The fact is that the F net is equal to, well, the upward forces and the downward forces cancel, but F net is equal to 100 minus 50, which is equal to 50 newtons. Okay? And that's equal to MA. So F net equals MA. So there's an acceleration. So is it moving at a constant velocity to the right? No, that would imply that A is 0, but A is not equal to 0. And here, A is not equal to 0. Both of these are eliminated by that fact. So now we're saying accelerating to the right or accelerating to the left. And I think this requires understanding the physics. I mean, but there's no reason to expect that the object is going to accelerate to the left if the forces add up to a force to the right. So, is the force to the right? Absolutely. So is the acceleration to the right? Absolutely. Number 50, number 50. The graph below represents the relationship between the potential energy stored in a spring, PES, and the elongation of the spring, X. And I look at the graph real quick. I see elastic potential energy versus elongation, 0.2.1, PEJ, X, 0.2 and 0.4. And then it says the value of the spring constant is 5 newtons per meter, 10 newtons per meter, or 125 newtons per meter, or 250 newtons per meter. So if I'm looking at this problem, what would I do if I wanted to do just some process of elimination? If I remember, first off, I look at PE and I look at X, and I have to kind of remember that I need to go to a formula sheet, right? Now, if I wanted to do some process of elimination for the purposes of, maximizing my grade, then I might say something like this. 0.2 versus 0.02 and 0.04. These are very small displacements relative to the size of the energy. And so what that tells me is that the value of the spring constant is going to be a large number. So it takes a lot of energy to displace the spring, a very small amount. And you might say 0.2 joules, that's not a lot of energy, but 0.04 meters, 4 centimeters, that much takes 0.2 joules. It's more about the magnitude of the number being squared, which means that it's gonna be, and that's the other point, that it's gonna be squared, which means that the spring constant is probably going to be a very large number because this is a really hard string to stretch. So I suspect that this one and this one aren't right. That's my estimate. That choice 1 and choice 2 are not correct. But to get the answer, I definitely want to actually go through the algebra. And I could choose either one of these. And in fact, doing both of them will just confirm the answer, won't it? So I would say choose one point to get the answer. And if you want to be the nerd is a compliment, do both points. Confirm answer. Okay, so I get PES. So I'm going to use the top point, 0.2. 0.2 joules is equal to 1/2 K, parentheses, 0.04 squared. And now I could divide by parentheses 1/2 times 0.04 squared, close parentheses, divide by parentheses 1/2 times 0.04 squared, close parentheses. And I got to go to my calculator for this. Now that this does confirm to me, by the way, since I'm dividing by a half, that the 0.2 divided by a half is 0.4, and then divide by 0.04 squared. If I divide by 0.04 squared, if I divide by 0.04 by 0.04, 0.4 divided by 0.04, that's 10. So the answer is definitely going to be greater than 10, confirming that this is wrong and this is wrong. And now some quick knowledge of arithmetic is actually confirms that the answer has to end in a 0. That's again the benefit in having a little bit of arithmetic intuition. Having a 10 in the numerator divided by 0.04, that's equivalent to multiplying by some larger integer. So 0.2 divided by 1/2 times parentheses 0.04 close parentheses squared close parentheses. Notice my use of parentheses in the denominator. Absolutely algebraically required. Optional? Well, you know that you have the option to use them, except that if you don't use them, then it's wrong. Then it's absolutely required. How can you decide between when something is absolutely required versus something is optional, whether you should do it? If using the thing is optional, but you don't know if it's required, or if you have the option to use the parentheses, but you don't know if you are required to use the parentheses, well, if you know that using the parentheses gives you the correct answer, then use the parentheses. Now, part B2 looks just like part B1, except now basically the multiple choices are gone. Okay? So that's the big difference. And we are, by the way, we've done 50 problems. We are 35 problems away from a perfect grade on this test. So if you've made it through this point, I'm absolutely proud of you. And I told you, I mean it. I believe that you have the capacity to ace this test. If you are approaching a 65, but you want to pass, and that's your goal, the strategies that I've been showing you are going to get you the passing grade. Now, if you are knowing you're passing, but you're trying to get an 80, or if you know you're going to get an 80, but you're going for a 90, or if you have a 90, but you're going for 100, all of the strategies put together are going to get you closer to the 100. Now, again, as I noted, when I was doing this, I made occasional mistakes. Now, no, my mistakes were not content lack of knowledge. My mistakes were just genuine mistakes. And sometimes it's a reading. I read the problem incorrectly. And sometimes I plugged in the number. And it was I always did the problem given the way given the way I read it correctly. So I used the correct formulas, but sometimes I just read the thing like it told me to get one thing, like compare A to B, compare B to A. I might have compared the wrong thing to the wrong thing and I got it wrong, which means that if I am able to make those errors, you are also able to make the error. So make sure that, especially from 51 to 85, this is where it's most important, but also of course important from 1 to 50 because that's most of the test. Make sure that when you're done with the problem that you check that you answered the question that they asked. And that's a common error for a lot of students. Answering a question, but then not checking to see if they answered the question that the question itself asked. You get some value of little g, and they didn't ask for g, or you get a value for m, but they didn't ask for m. Now, about points. Some of these questions, as you can see, are like quiz 51-52. How could it be 51-52 in a single question? Well, this is the hint. These problems, generally speaking, can be done with either two equations, which is actually almost always the case. More than 99% of the time, that's the case. But the other thing is that you have to use units and all that good stuff when you're solving the problem. That's what gets you all the points. So often, many of these are two equation problems, Like if you see a 51-52 or 53-54, 55-56, that's three problems, three sets of problems that are probably going to be two equation problems. Yes, some of them have a way to do it with just one equation, but don't look for in these cases the one equation that will give you the answer. And that's actually the really important thing to know. Don't look for the one equation that's going to give you the answer. Look for an equation that gives you something relevant, because it's almost guaranteed that you actually can't do the problem in one equation. Although, like I said, sometimes I did find just one equation, sometimes, but don't look for that because that's a waste of your time. Look, it's almost always the case, and that it's almost always the case that every question that is a two-parter actually requires two equations. This test had one maybe that I only used one equation. Most of them require two. So just assume that they're going to require two equations. On that note, número 51 a 52, number 51 to 52, planet Need has a mass of 6.50 times 10 to the 23rd kilograms and a radius of 2.96 times 10 to the 6th meters. The magnitude of the gravitational force of attraction exerted on a 5 kilogram object. Now I'm going to do M2 and M1 by Need is 7.15 newtons when the object is located at a position. 5.50 times 10 to the 6 meters from the center of Need. So this is R Need, and this is R, just the distance. Calculate the gravitational field strength of planet Need at the position of the object. At the position of the object. So this is one of those situations where as I mentioned it to you, this has a piece of information that we can actually avoid using. It's this one right here. We could actually avoid using it. But does that mean that that's irrelevant information? You should, as I told you, you should not treat any piece of information as irrelevant, nor should you, especially, you should not look for any information that's irrelevant, because it's almost guaranteed that every numerical, mathematical piece of information is actually relevant, including information that implies numbers, even if it's not written as a number. You know, to rest, from rest, v equals 0, that kind of thing. Free fall, you know, g is the acceleration due to gravity. But in this case, could you have done it by getting the gravitational field strength on the surface and then using that to get the gravitational field strength at 5.50 times 10 to the 6? Yes. But you could actually just go right to the 5.50 times 10 to the 6. So this is, and by the way, I put these here because of Pluto, Earth, Moon, and Pluto and Charon, because there's some details about the Earth that if you look, it does have some details about the Earth. Like, for example, the mass of the Earth, 5.98 times 10 to the 24th kilograms, and the mass of Need is 6.50 times 10 to the 23rd, which is smaller than the mass of the Earth. And then the radius, or the distance rather, since we don't need the radius of the actual planet, but the distance, 5.50 times 10 to the 6th, and then the radius of the Earth is 6.67 times 10 to the 6th. So that's ever so slightly bigger. The radius of the Earth, which reduces g on Earth relative to Need ever so slightly, but the mass increases g on Earth a lot compared to Need. But then we look at the yes, so that's enough information to actually give us a hint that in fact we should expect g on Need at this height to be strictly smaller, and actually by a good chunk, by a good multiple of less than about 10, but a good chunk less than g, which is 9.81. Why do I do that? A test taking strategy that I've used many times actually on this test so far to eliminate some choices. Make an estimate. And so why am I showing Earth and Moon and Pluto and Charon? Because on the Moon, despite the fact that, you know, the Moon is smaller, well, we care about density too. But it does turn out that rocky planets that are smaller tend to have lesser gravity than rocky planets that are bigger. And this is a rocky planet that's smaller. So unless the density is super duper high, we expect a smaller g. We'll see. So FG, and of course we said that the formula sheet is king. or queen is Rex, let's say, we look for the gravitational force. And expand that. So we have Fg equals G M1 M2 over R squared. And yeah, and they want the that's the gravitational force of but they actually wanted the gravitational field strength. So I actually have to look for a different formula. Um, this one. So it is a two equation problem. Let's actually put that in. So this G is the gravitational field strength. And this capital FG is the gravitational force. Okay? And the clever among you might be able to do this in one step. And there is a way to do this in one step. Okay? But let's do this in the two steps and I'll tell you the clever way after I get to the second part, because you don't want, I know you think you want the clever way and just the clever way. No, you don't, because if you don't remember the clever way, then what are you going to do on the not and the problem? Like nothing. But if you remember this a way to get it in the right direction, then you do it right. And if I just give you the clever way, a lot of you will just skip this way, which is a problem. Now, again, formula sheet. I'm not going to screenshot this constant, but it's there. Gravitational constant. Oh, yes, I'm gonna. How many times do I say that? I'm not going to screenshot this, and then I do it. But the big emphasis here, of course, is that it is on the reference table, right? Basically everything you need is on the reference table. Really rarely do you get a problem that's just not there. So 6.67 times 10 to the negative 11th. 6.6. Now I want to point this out. Show all work, including the equation and substitution. Okay. Well, I didn't do that one straight. I literally did it the way that it makes it straight from moment one. Oh, well. Okay, 6.67 times 10 to the negative 11th. And what are the units there? I almost don't even think of the units so often. Instead of, I could just break it down, but instead I'm just going to look. Newtons, meter squared per kilogram squared. Do you have to carry your units all the way across to the beginning and end? No. And then M1, 6.50 times 10 to the 23rd kilograms. And then M2 is 5 kilograms over the radius, the distance at that position. Calculate the gravitational field strength the planet need at the position of the object. Okay, so the position, 5.50 times 10 to the 6th meters squared. Do you have to carry your numbers all the way to the end? You do not. In fact, not only do you not have to carry it all the way, but once you put the equation, if it doesn't require any more algebra to solve it, you could just plug into the calculator, which is exactly what I'm going to do. Okay, 6.67 times 10 to the power of negative 11 times M1, 6.50 times 10 to the power of 23, close open, M2, 5, divided by R, the distance, 5.50 times 10 to the 6th, close parentheses, squared. Notice I had to use parentheses in the denominator especially, but I do that, I press enter, 7.166115702. Newtons. And you could round, all of these numbers are to 3 decimal places. So, or 3 digits of accuracy, so 7.17 newtons. Did I get that right? 166. Okay. So now I have FG, and now I need to get little g, which again, little g is the gravitational field strength. And if you're wondering, here it is. If you're looking for gravitational field strength, G is acceleration due to gravity or gravitational field strength. And you might be saying, wait, I've never talked about it that way. But it is on the reference table. And if you look for gravitational field strength, you would find it. So little g is equal to Fg over m. And at this point, I want to point out that notice that this is Fg divided by m, which is 5. So 7.17 newtons divided by 5 kilograms. And what's the point? You could have figured out the gravitational field strength. I said that there's a clever way by replacing the 5 kilogram by a 1 kilogram object, because the gravitational field strength multiplied by 1 mass, mg, is equal to 1g. So you could have replaced the 5 kilogram object with a 1 kilogram object. But do I expect you to remember that on the test? I don't. So that's why I don't want to just show you the clever way on step 1 and then have you end up not knowing how to do it during the test. So 1.433222314. Meters per second squared, or 1.43 meters per second squared. Notice that I used units in every step. Do you have to use units? Oh yeah, you have to. I know so many kids who are like, well, I don't want to use units, and my teacher said to use units, but I don't want them. And then they get to the test and don't know why they got an 80. Like, the thing is, I wish that the test makers would break down how your score was determined, because then they would just show you that for those of you who are like, I don't want to use units, so I'm not gonna, and I won't, how your score is just like 15 points lower than it could have been, despite the fact that you knew how to do the problem. Use units. You're actually required. It tells you you're required, therefore obey. You know? Números 53 a 54, number 53 to 54. As shown in the diagram below, a toy car initially traveling at 1.0 meters per second uniformly accelerates to a speed of 4.0 meters per second as it travels down a 5.0 meter long slope. Calculate the time required for the toy car to travel the 5.0 meters from the top of the slope to the bottom of the slope. Show all work, including the equations and substitutions of units. Now, do I write down my estimate? Not on this test. I don't write down my estimate. But if I look at 1 to 4 in 5 seconds, now I might say if it was going at 1 second, 5 to go 5 meters, 5 seconds to down to 5 over 4, the final velocity, seconds. And if I average that, like 2.5 average, 5 over 2.5, maybe around 2 seconds. So that's, in other words, I just picked an average velocity somewhere between the 1 and the 4, and 2 seconds. Yeah, 2 seconds. Okay, but how do I do this problem? Okay, that's my estimate. Okay. But yeah, I recommend doing an estimate on every single problem. I do. It helps with your intuition. It fixes intuition. And that's why I recommend it. Okay, so we have VI, we have VF, we have D, and they want to know the time. Is there an equation that gives us the time? Yeah, in one step? Yeah. Do I recommend it? No. Remember the other one, the D equals VIT plus 1/2 AT squared, that you could have done it that way, but it requires algebra? I actually do teach my students to do it that way because I teach them the algebra, because the algebra is just a fundamental skill. I want them to know the algebra. But in this case, D is a positive number, VI is a positive number, T is an unknown. This would be a quadratic equation with some crazy roots. If Yeah, I don't recommend doing it that way in this case. I recommend going for a different equation. So if you look for the have or needs, VI, VF, and D, this one's missing A. And you might say, well, that doesn't have the thing that I need because A is not even on the list of things that I need. But if you go for the one equation that has your have or needs, your D, your VI, I'm sorry, it's actually, no, I lied because this one also has A. So this one doesn't have your have or needs, and if you go for this one doesn't have your have or needs. If you go for this one, well, if you have V average, this one has your have or needs, but we have to talk about V average. So how do we go about doing this problem? And there are a lot of ways. There are a lot of ways. Um, there is an equation that is not on this test that I recommend the nerds to know. Where if A is constant, that means that V average is equal to VI plus VF over 2. I am not going to do it that way, even though I did do it that way on my own paper, only because I actually want to teach. This is one time I get to teach the video, right? If you were my student, I would teach you this equation. But since you're watching this video and I want to maximize score, I have to go for ways that'll get you the answer using the formula sheets and the formulas that are there. So this is missing one of my have or needs, my T, but it has A. And I know that if I get A, then other equations have my have or needs and T, right? Because then I'll have A will be a have and T will be a need. So another equation will give me T in an easier way. So I'm going to do this. I have VF squared equals VI squared plus 2AD. And I have, so VF is 4 squared equals 1 squared plus 2A times 5. And I have 16 is equal to 1 plus 10A. Subtract 1, subtract 1. I get, let's scroll down a little bit here. 15 equals 10A. Divide by 10, divide by 10. And I get that A is equal to, and I've got my units, right? Meters per second. Meters per second. You see how easy it is to miss units? 5 meters. A equals 1.5 meters per second. You do not need your units in the intermediate steps, but you do need your units in the initial formula and in your final answer, squared. 1.5 meters per second squared. Okay, so now that I have A, now A is in my have or needs. Now I can go for an equation that has have or needs including A and T, and it happens to be that this is a much easier equation to deal with. Let's expand that a little bit. VF equals VI plus AT. Let's go for red now. VF equals VI plus AT. So I have 4 equals 1. Now the acceleration is down the hill. So let's just make sure I understand my signs is down the hill and is a positive number because it's in the same, the acceleration is in the same direction as the velocity. So I have 4 meters per second equals 1 meter per second plus 10 meters per second squared times T. I don't know if you saw that flying by. That was a ladybug. Subtract 1, subtract 1. Nope, I lied. Where'd the 10 come from? The ladybug flew by, and I got distracted. 1.5 meters per second squared times T. So I got 3 equals 1.5 T. Divide by 1.5. Divide by 1.5. And I'm only doing this to simulate. If you don't know what 3 divided by 1.5 is, I'm going to simulate the fact that I'm bothering to plug it into my calculator. It is going to be 2 because 3 is double 1.5, and I get 2. So T equals 2 seconds. 0.0. Let's put 2.0 seconds. You don't need the 0.0. 2 is good enough. Okay? There's no requirement that you have exactly the number of sig figs that they have. So 2.0 is good enough. Número 55 a 56, number 55 to 56. Calculate the resistance of an incandescent light bulb that operates at 20 watts of power when connected to a 12-volt battery. Show all work, including the equation and substitution with units. Of course we will. So we have the resistance unknown. We have to calculate it. Incandescent light bulb operates at 20 watts. That's a power. And connected to a 12-volt battery. As far as I know, the only unit that I know where the variable and the unit is the same letter is volts. Like power is in watts, resistance is in ohms, current is I is in amperes. Uh, you know, displacement is in meters. I don't really know in my mind of any other unit where the unit and the variable are the same letter, but it's weird. So V equals 12 volts. The first V is the variable voltage, and V is volts, the unit of the actual voltage of the battery. Okay. So I need a power equation that has or need resistance. A power, resistance, and V. So I go to my I have my power equation here. And it happens to be this one equation has all my Haver needs. So I think this was the one that I said. I think in this test there was one that turned out that I didn't need more than one equation. So I have my Haver needs is contained in this last one. V squared over R equals P. So P equals V squared over R. And now I could plug into this, or I could solve for R. So for my nerds watching this, I'm going to solve for R. Oops, that was silly. For my nerds, I'm going to solve for R. That's what I get. Sometimes, by the way, when I speak or think, and this is actually a source of error for a lot of students. So this is actually worth telling you, both for the students who struggle and students who are nerds, but somehow just for some reason know how to do every problem, but still get the question wrong. One of the sources of errors happens to be if you think of something while simultaneously writing something else, the thing that you think sometimes seamlessly replaces the thing that you were thinking smoothly and seamlessly replaces the thing that you were writing. So I was thinking about the number one while I said R, and my one turned into an R. Okay, you think that that's just a thing, but actually across the board, I've discovered it that a lot of my students I notice when I'm tutoring them because they're almost failing, they're like at 65 or 60, or maybe they're actually failing, and I get them to a 70, then an 80 to a 90, and do you know what they get after a 90? Like a 70, not a 95. Then I have to train them past the 70. And what causes them to go from a 90 back to a 70? That exact thing. When they're struggling, their thinking is slower than their writing. So they think. They have a thought, write it down. Have a thought, write it down. Then their thinking gets faster. Then their thinking gets faster. And the writing, of course, because writing speed doesn't change. Their thinking speed gets faster and faster. And all of a sudden, at one moment, their thinking speed exactly matches their writing speed, and they're great jobs. And then what happens? Why their grade goes back up? Well, because now their thinking speed goes beyond their writing speed, and now there's no smooth uh, and seamless switching of the thought with the writing thing. So yeah, that was what caused me to get the R down there, and so look for that. So I get PR is equal to V squared, and if I divide by P, I get that R is equal to V squared over P. Now, R equals V squared over P might break your intuition because you're not used to seeing it that way. But understand, this is not a formula I want you to memorize. I don't want you to memorize R equals V squared over P. I want you to get P equals V squared over R from the formula sheet, and then you could do algebra to solve for R. The other option, if you didn't want to do it that way, you could plug in immediately and then start solving for R. You could plug in the numbers into the red equation and start solving for R. But I decided to solve for R. So why is this suddenly, maybe it makes sense that it's a 2-point question? Because it requires you to solve for a variable that's in the denominator, maybe. So I get R is equal to V squared, 12 volts. Remember the units, over P, which is 20 watts. Now, how do I convert like volts squared over watts into ohms? I'll be honest right now. I don't. If you had said resistance is equal to that number with volts squared over watts, you wouldn't lose points. However, I just remember that resistance is in ohms. So I literally just write it down. Sometimes if my intuition breaks a little bit, I might do some quick notation, my some quick unit checking for myself, but that's not what's going on here. So 12 over 20, no, 12 squared over 20, 7.2. So I get R equals 7.2, and I just immediately write ohms. I don't do the unit conversion. I just know resistance is in ohms, so I put it in. Now, is there a benefit to making sure you got the right units? Actually, yes. If you are not a struggling student around the 60s to the 70s, yeah, then there is. It is worth confirming that your units are correct. But if that's not you, then no. Base your answers to 57 to 59 on the information in the graph below and on your knowledge of physics. The motion of a car traveling in a straight road is represented by the graph below. Speed, meters per second, time, seconds. And I do look at the numbers real quick. 0 to 12 and time 0 to 10. Speed 0 to 12, time 0 to 10. And I see a line, a straight line going from 0.4 up to 10 and then like 11 point something, 5-ish, ish. Determine the average speed of the car from time t equals 0 to time t equals 8 seconds. So the average speed of the car from t equals 0 to time t equals 8 seconds. So I'm sitting there debating because I'll tell you how I did the problem. In the previous problem, I said that I didn't use this equation on purpose because it's not in your formula sheet. But then, too many things minimized there. But then that's actually exactly the way I did it for this problem. And I'm just wondering if it's worth it to ignore myself and do it that way. Okay. So well, I did it out. Okay, so that's the way I did it on my paper. I think I'm not going to do it this way, though. I think I'm not going to do it this way because there is a lesson in physics. Yeah, actually, this is very wise because you're watching this video trying to learn something, and there is a lesson in physics that um, you need to know. So this first off, the slope of the displacement curve is the velocity curve. Is the velocity. So if you're wondering what the velocity is when you have the distance versus time curve, that is the slope. That's the velocity, and then the slope of the velocity time curve is the acceleration. But then there's a second lesson. The area under the acceleration. Wait, I thought I changed colors. I want to make sure I changed the colors. So, and calculus students will recognize this. Area under the acceleration time curve is the average velocity. No. Did I get that right? The average velocity? No, it's not the average velocity. Sorry. I misspoke. I don't know why I blanked for a second. So hey, I get things wrong. Is not average velocity. So the area under the acceleration time curve is actually delta v. Okay, there we go. The area under the acceleration time curve is delta v, and then the area under the velocity time curve is d, displacement. So weirdly, now you might not do calculus, so I'm just gonna just say this for my calc heads. But weirdly, it seems like if you think of like slope calculation and area under curve calculation, it seems like calculating the slope and calculating the area under the curve are like inverse operations of each other. And then if you're a calculus head, you know that that's actually true. That's saying that the derivative and the integral are inverse operations of each other. Now, if you're not a calc head, then just accept that. Accept these 4 points. The slope of the distance time curve is velocity. Slope of velocity time curve is acceleration. Area under acceleration time curve is delta v, and area under the velocity time curve is d. So I never, not in one problem, got to calculate the area under a curve, but that is an important piece of this Regents. So I'm going to do it that way. I'm going to get the displacement from here to here. They said t equals 0 to t equals 8, right? Let's make sure ti and tf. So I'm going to get this area. And how do I get this area? This is a trapezoid. It is a trapezoid. If you look at the top, the red lines that I just drew as being the parallel bases, this length is 4. This length is 10. And then the height is horizontal. So the area, which is equal to the displacement, as we said, is equal to 1/2 b1 plus b2 times h. That's from geometry class. So 1/2 4 plus 10. Now I have to do units. 1/2 b1 plus b2. This is 4 meters per second plus 10 meters per second times the height of the trapezoid, which is in time, as weird as it is, 8 seconds. The height of the trapezoid on the graph. That's why the height is in time. It's because it's a trapezoid on a graph paper, right? And so then this is equal to, on the calculator, 1/2 times 4 plus 10 times 8, and that's equal to 56 meters. Okay? And now the second piece is the average speed. V average equals d over t, which is equal to 56 meters over 8 seconds, which is equal to 7 meters per second. On the calculator, 56 divided by 8 is 7 meters per second. And that's the answer. Did I do it that way on in my paper? No, I actually used this formula, V average equals VI plus VF over 2. But again, it's not on your formula sheet. So, what do you do in that case? But then neither is this, the area under the curve fact. But it is one of the things in physics that you're expected to know. It is on the Regents. And I haven't seen a Regents where that didn't appear. So do remember that the area under the acceleration time graph is the delta V, and the area under the velocity time graph is displacement. Okay? Displacement, which is change in position, displacement, right? Okay. Number 58 to 59, 58, 59. Calculate the magnitude of the acceleration of the car from t equals 0 to t equals 8 seconds. And that's where it is. Look at the slope. So we really care about this, don't we? So we use this one, and we use this one to get the information, right? The second one is the slope of the velocity time curve, okay? So the acceleration, A, is equal to delta V over t, which is equal to V final minus V initial over time, which is equal to, and by the way, that is on the formula sheet. I'm not going to screenshot every formula, but you want to know that these formulas are on the formula sheet. A equals delta V over t. So equals 10 meters per second minus 4 meters per second over time, 8 seconds. And that's equal to 6 over 8, which is equal to 0.75 meters per second squared. And so even though it is a 58 to 59 problem, we just did that one in one equation. Which other one did we do in one equation? This one we did in one equation, but it required a lot of algebra. So I think when I said one problem, I really was thinking about this one, but then this one really required only one equation too. But as you see, the 2-point problems usually require two equations. Okay. Número 60, number 60. A light ray is traveling through a transparent medium at a speed of 1.75 times 10 to the 8th meters per second. Determine the absolute index of refraction of this medium for this light ray. So we need an equation that relates the speed, v, that number 1.75 times 10 to the 8th meters per second, and we need n, okay? So one known and one unknown. Well, how could we possibly do it? Then it is possible in one equation, but you do have to know some stuff. Let's see. The one that relates index of refraction and velocity is right here. So we actually need a comparison. And what can we possibly compare it to? Speed of light in a vacuum. So this is v in the medium. How about v in a vacuum, which is equal to c, and n in a vacuum is equal to 1. There we go. And we have the equation n2 over n1 equals v1 over v2, so they're inversely proportional. So now we have n unknown over v is equal, n over v, n over n vacuum is equal to, flip these, make sure you flip these, v in a vacuum over v in this medium. I'm going to say v medium and n medium, m. That we have a way to track what we're writing. Okay, so we plug in some numbers. N in the medium is over n in a vacuum, 1 is equal to velocity in a vacuum, 3 times 10 to the 8th meters per second, over v in a medium, 1.75 times 10 to the 8th meters per second. Now, if you didn't know that you can cancel the times 10 to the 8th, then just plug them into your calculator. In fact, the units cancel too. So again, if you didn't know, then use parentheses. 3 times 10 to the 8th, parentheses 3 times 10 to the 8th, close the parentheses, divided by, open parentheses, 1.75 times 10 to the 8th, close that parenthesis, and then you get this answer, 1.714285714. Divided by 1, so nm is equal to 1.714285714. So n, and now I need decimal places. I know the speed of light in the reference table. If you didn't remember it, it is in the reference table. That's the beautiful thing about the reference table. Like, I forgot the speed of light, great. 3 times 10 to the 8th meter per second, but it's in 3 decimal places. And 1.75 is in 3 decimal places. And in the medium is equal to, now I rounded to 1.7. Now after the 1 is a 4, that keeps the 1 the same. And I've done 60 problems, 60 fully correct, full credit problems. I am, 60 problems towards a perfect grade. I need 25 more problems to get a perfect grade on this Regents. Drop the mic at the end. I'm really excited about this. Número 61, number 61, as shown in the diagram below, a ray of light traveling through a medium X is incident upon the surface of medium Y. The absolute index of refraction of medium Y is greater than the absolute index of refraction of medium X. On the diagram below in your answer booklet, which is exactly this diagram, which is why I didn't paste it here, use a straight edge to draw a ray that could represent the path of the light and medium in the medium. Look, straight edge. Your school is required to provide you a straight edge. However, your school is also required to provide you a centimeter ruler. So if there's any problems that actually required a measurement, which I don't even know if there is, uh, then your school is actually absolutely required to just give that to you. But in this case, the edge of your calculator will work, the edge of the slide of your calculator, whatever will work as a straight edge. Um, so how do we do this? Um, well, I know that if the index of refraction was the same, the light would follow this continued path. And so now I have to know when a light ray passes through from one medium to another, it bends. Now notice my fingers conveniently bend more than 90 degrees, right? So the question is, does it bend? So here's the horizontal. Does the light bend towards the horizontal, or does it bend away from the horizontal as it passes through from the medium X to medium Y? And that's when you have to know. We have n sub x. I don't want this pen. I like that pen, but it's hard to read. N sub x, and you have n sub y. Okay, and then they said the absolute index of refraction in medium y is greater than the absolute index of refraction in medium x. So nx is less than ny. So what I remember is the water situation. What is the water situation? The water situation is that light going from outside to the water actually bends towards the perpendicular line. From air to water, it actually bends towards that perpendicular. And when light is coming out from the water to outside air, it bends away from that perpendicular. That's the reason why, for example, a fish tank will have, like, if you look at it at just the right angle to the side, you might actually see that there's total internal reflection inside of the tank somehow. Well, it's not just somehow, it's because of that total internal reflection. And so but if you actually were a fish in a fish tank, you could see in all directions from the fish tank. But funny enough, it would actually be all contained within this finite region instead of being like 180 degrees. So what does that mean? I have to know that the light ray is going to bend away from the direction of the light outside and towards the perpendicular. The path of the light in medium Y. That's the answer. Do you need an arrow? Actually, no. I did see in the book it didn't say that you needed the arrow, you just needed to draw the path. Okay. Nice. 52 a 50, oh, 62 a 63. 62 to 63. A tungsten wire has a cross-sectional area of 5.03 times 10 to the negative 7th meter squared and has a resistance of 1.21 times 10 to the negative 2 ohms when operated at 20 degrees Celsius. That's the temperature. Calculate the length of the wire. And there is an equation. And show all work, including the equation substitution in units. And I will say, I kept saying that there's one problem that I did with just one equation. But I mean, this one also just requires one equation. So I guess, but it does require two pieces of information. So perhaps that's why. But there's plenty of multiple choice questions that you needed like two pieces of information, right? Let's see. And then what's the other piece? The equation, resistivity equation. You see that ladybug. Ladybug is flying and enjoying this room. Keep enjoying the room. I have plenty of plants here. So R is equal to resistivity times L over A. And now I have the tungsten resistivity also. So I'm going to write that down. R is equal to resistivity L over A. Now in this one, the other one, I actually solved for the variable that I was looking for. And this one, just so that you get experience with both, I'm not going to solve for the variable that I'm looking for. I'm going to keep it there. So I have the resistance is 1.21 times 10 to the negative 2 ohms. If you didn't know that symbol for ohms, you could just write OHM, okay, equals the resistivity, 5.60 times 10 to the negative 8th ohms meters. L, the length, is an unknown, but we're looking for it, right? L divided by the A, 5.03 times 10 to the negative 7th meters squared. Okay? So if I had to make an estimate, there's not much information here to make an estimate, is there? But if I had to think about um, for the length of the wire, I would say that lengths wires tend to be of reasonable lengths, but they can vary from centimeters to kilometers. Do I think that the answer is going to be nanometers for a wire? I don't think so. So you know, I just but they could be a 100-meter wire. It can be a multi-kilometer wire. So I don't have an estimate just based on intuition, but I do notice that the denominator here is bigger than the numerator here, which shrinks the coefficient of L. Then I'm gonna divide by that number, and so that gives me a number bigger than this. And in fact, the numerator is about 10 times smaller than the denominator. So if I just change this to 1/10, then multiply by 10 on both sides, I get 1.21 times 10 to the negative 2. That's my estimate. And then I say 1.21 times 10 to the negative 1 is my estimate. And then if I say, well, the numerator is 5.60 compared to 5.03, slightly bigger, then that means I'm going to divide by a number that's slightly, I'm going to multiply by a number that's slightly less than 10, or equivalently divide by a number that's slightly more than 1/10. So I'm going to get a number slightly less than, ever so slightly less than 1.21 times 10 to the negative 1. So slightly less than 1.21 times 10 to the negative 1 meters. And that's a great estimate. That's a phenomenal estimate because now I will know almost immediately if my answer is right. 5.03 times 10 to the negative 7th meters squared. 5.03 times 10 to the negative 7th meter squared. Then I have to divide by 5.60 times 10 to the negative 8th ohm meter. Divide by 5.60 times 10 to the negative 8th ohm meter, and I got that L is equal to, I put these numbers in the calculator, okay? Now I think I'm gonna have to move this a little bit because, so the calculator's small, but the screen is gonna be big, so it's okay. So parentheses, 5.03 times 10 to the power of negative 7, close parentheses, open parentheses, 1.21 times 10 to the power of negative 2, divided by parentheses are required, 5.60 times 10 to the power of negative 8. Oops. Close parentheses, enter, I got 0.108. Now let me bring this number to the calculator, to the screen here. Okay. Okay. So I got L is 0.1086839.286 meters, or L is approximately, and now I look for the decimals. All of these numbers were 3 significant digits, so I could do 0.10 and then 8, and then followed by a 6, 9 meters. Not bad. And I said slightly less than 1.21 times 10 to the negative 1. Remember, 10 to the negative 1 is divided by 10, so that's slightly less than 0.121, and 0.109 is slightly less than 0.121. So my estimate checked my answer. You see the benefit of doing an estimate? The estimate itself checks your answer. Número 64 65, number 64 to 65. As shown in the diagram below, a block is hanging motionless from a vertical spring, having caused the spring to elongate from its unstretched length of 0.200 meters to a length of 0.500 meters. So this is L rest. This is L stretched. So delta X is, I could calculate it now, might as well, 0.300 meters, right? 0.500 minus 0.20 meters. Okay. Point. Okay. The spring has a spring constant K of 250 newtons per meter. Calculate the magnitude of the force. So they want the force exerted by the block on the spring. They want the magnitude. So let's go to the formula sheet. It does help to know these formulas, but I mean, I hope that simulating me constantly going to the formula sheet to get the formula is helping you to realize that that's the way to do the best as possible on this test. Now, if you know the formulas, not like 99%, but like 100%. If you know the formula 100%, do you need to go to the formula sheet for every single formula that you know? No. That's if you know the formula 100%. If you don't know the formula 100%, go to the formula sheet. And many of you, if you're at a 65, chances are you don't know the formula 100%. So I would go to the formula sheet. So that said, Fs is equal to 250 newtons per meter times X is 0.300 meters. And then you get an answer of 75.0 newtons. Checking my calculator. Okay. Checking my notes rather. Just making sure I did that one right. Did I do that on the calculator? Let's say I did. I have a calculator installed in the brain. Should you do that on the calculator? Yeah. Should you trust your arithmetic? I think not. If you appreciate the advice I've given you so far, I appreciate that. If you feel like I don't deserve to subscribe, then don't subscribe. But if you feel like I do, if you feel like this video has been helpful, then I do appreciate the help that you've given me by subscribing. And I think I started at whatever number I started at, and I was at one more a couple hours ago. But I'm going to keep going. This video is a whole lot of work. And I don't know if you noticed the outfit change. I had to go. I have a kid. Shout outs to Javier, by the way, who probably will see this shout out because he is the one doing my shorts. So I really do appreciate the work that Javier is doing, and hope that continues. That said, base your answer to 66 through 70. It's 5 different problems on the information and data in the table below and your knowledge of physics. In an experiment, a resistor is connected to a source of varying potential difference. A voltmeter and an ammeter are included in the circuit so that the current can be measured at different potential difference settings. The data table below shows the potential differences and currents measured. And I do look at the table, but I don't absorb it all. That's not a thing. I look at it and then I move on and then go back to the table when needed. Data table, potential difference 0, 2, 3, 5, and 8, and current 0.26, 0.35, 0.63, 0.98. Not surprising that's going up. Okay? Then using the information, and I like vaguely have some formulas in mind, but vaguely. I go back to it when I need it. Using the information in the data table, construct a graph on the grid in your answer booklet following the directions below. Plot the data points for current versus potential difference. Okay? Current versus potential difference. Okay? Now, I do have to do a little scrolling. Let me see if I have the graph created here just so that I can be confident that I don't make a mistake. Yes. Okay? Current versus potential difference. Not surprisingly, the graph goes exactly through 0. 0, 0. And then the next one, potential difference in current in that order, 2 and 0.26, 2 and 0.26. So clearly I have to estimate where 0.26 is, right? So how do I estimate? I go 0 0.1, 0 0.2, 0 0.3, 0 0.4. So 0.26, 0.25 is halfway between 0.2 and 0.25. I'm sorry, 0.25 is halfway between 0.2 and 0.3. So 0.26 is slightly above half. Are you expected to be so obsessively accurate like that? No, but it helps to know slightly above half. But these are dots that have finite size. So make the dot as big as you need to make it work. Then the next one, 3 and 0.35. 3.0 and 0.35. Again, that's exactly half between 0.3 and 0.4. And if you can't remember 0.30, label it 0.10, 0.50, 0.60, 0.70 if it helps you. Then the next one is 5 and 0.63. 5 and 0.63. 5 and 0.63. Oops, I messed this one up. That's a silly thing to do. 0.70 and 0.90. And the good thing about that is that if I had messed that up, I could literally just erase it and go back and fix it, which is what I just did. 5 and 0.63, closer to the 6 than to the 0.6 than to the 0.7, and then 0.8 and 0.98, which is almost exactly at the 1, just slightly a hair below the 1. Okay, that's the data points. I got a point there, and then draw the line of best fit. Let's draw that in red now. Line of best fit. There's a trick. Usually, if you just connect that bottom point and the top point, you've done a great job at it. But you do have to check that you have some points below and some points above. I've seen students get this question wrong by connecting the first and last point, but then they have points above the line but none below, or vice versa, have only points below and not above. You have to have like an equal spacing of points above and below the line. Otherwise, it's not right. Okay, so that's my line of best fit. And that's a full credit graph. And then number 68 to 69, calculate the slope of the line. Show all work, including the equation and substitution with units. Let's check if this graph, if there's any slope equation here. I thought there was, but so this might be the first equation that's not on the reference table. So slope, I did not see it, is not on the reference table. Okay? So it says calculate the slope of the graph. So slope is equal to the change in y over the change in x. So in this case, the slope is equal to, now I'm going to use the 0.00, which is exactly expected to be correct. And this point is 8.0 volts and 0.98 amps. Okay? And I should actually label this as 0 volts and 0 amps. Okay? So the slope is, the change in y is 0.98 amps minus 0 amps divided by the change in x, which is the volts, 8.0 volts minus 0 volts. Okay? And so then I get to my calculator. You can do, if you choose, 0.98 minus 0. But that's 0.98. And you could also do 8 minus 0, which is 8. Or you're allowed to know that minus 0 doesn't change the number. So 0.98 minus 0 divided by 8 minus 0, and you got 0.1225. 0.1225. Now, do I have to get the right sig figs? That's not a requirement on the test, but it's around 0.12. And that's amps over volts, amps over volts. Okay. Now, then the second is to determine the resistance of the resistor, the resistance of the resistor. So how can I get the resistance of the resistor over this? I have a current I and I have a voltage V in that order. I over V, if I go to my equation sheet, I over V doesn't appear as is on the sheet, but V over I does, and that's the reciprocal of resistance equals 0.12. So V over I, okay, okay, sorry, this is acting up here. Okay, stop acting up. I need to write something. There you go. V over I is equal to 1 over 0.12, which is equal to R. So R, amps over volts. So I can remember that this is the resistance, and I don't have to like convert amps over volts or volts over amps to uh, ohms in any special way. I could do 1 divided by 0.12 is 8.33. So 8.33 repeating ohms, or R is equal to 8.3 ohms. Okay. That said, let's go to, we've done 70 problems. We are 15 points away from a perfect grade on this test, and I'm really excited. Base your answers to 71 through 75, another 5-question problem, on the information and diagram below and your knowledge of physics. An alpha particle with a charge of plus 2 elementary charges, so they were nice to tell you that that's true. An alpha particle with a charge of plus 2 elementary charges is moving towards 2 oppositely charged parallel plates, as shown in the diagram below. The magnitude of the electric field strength between the plates is 5.0 times 10 to the 4th newtons per coulomb. So this is the charge. This is the electric field strength. Okay, and determine the magnitude of the charge of an alpha particle in coulombs. Well, Q is definitely equal to two elementary charges. No, how do you convert elementary charges to coulombs? That is not a formula on the formula sheet per se. What it is a page 1 reference table. How many elementary charges are in a coulomb, and how many coulombs are how many elementary charges. So there's two numbers here. Either one could be relevant here. So I'm generally speaking, since either one could be relevant here, I'm going to give both. But the one that we want to convert elementary charges to coulombs. So remember, E is this. These are equal to each other. So we have Q equals 2E is equal to 2, parentheses 1.60 times 10 to the negative 19th coulombs, which is equal to 2, no, not 2, 3.2 times 10, 3.20. I'm going to give the sig figs. Why is it erasing that when I wrote this first? Okay, that's weird. And now it's not erasing those decimals. That's weird. Okay, equals 3.20 times 10 to the negative 19 coulombs. Okay, that's a full point right there. Now, the next one on the diagram in your answer booklet, draw at least 3 field lines showing the direction, okay, of the electric field in the space between the charged plates. So I know that the electric field between charged plates, this is something that you need to know. The electric field, bent just last minute, between the charged plates is a straight line. So if your lines aren't like, they just barely bend, they would be for a little bit forgiving, but you know, they are straight. My computer is acting up, this software is acting up a little bit. So I'm hoping that it'll let me finish this problem. But if I drew 3 lines, notice that they go straight from the positive to the negative. The grading did say they didn't have to perfectly touch the plate, but that is a full credit answer of the line. Now, the thing did say put the answer on the answer booklet. Just for space purposes, I didn't put this on the answer booklet, but it's exactly this diagram. Okay. The next question, that was 72. The third question, 73, so 73. What is the direction of the electrostatic force exerted on the alpha particle as it passes between the plates? Now you need to know that F is equal to EQ, which means that it's in the direction of the electric field. So, which means that the force is to the left between the plates. Okay? Between the plates. Outside the plates, different story. 74, 75, 74 to 75. Calculate the magnitude of the electrostatic force exerted on the alpha particle by the electric field as the alpha particle passes through the electric field. Show all work, including the equation substitutions in field with units. So that's actually our equation. And that did come from, by the way, I closed that, had a little bit of a faux pas with the software breaking. That did come from the formula sheet, okay? F equals EQ or E equals F over Q did come from the formula sheet. So if you want to use this formula, great. Okay. So notice that the electric field and the force point in the same direction if Q is a positive number. That's why the force points to the left. So how do I get the magnitude of the electrostatic force? Well, if I multiply both sides by Q now, multiply both sides by Q, I got that FE equals EQ. Okay, so equals, now the electric field, I believe they said was 5 times 10 to the fourth. Okay, 5.0 times 10 to the fourth newtons per coulomb. Make sure I got that right. Yes, and I got two elementary charges, which is 3.20. 3.20 times 10 to the negative 19 coulomb. And I get whatever the calculator says, times 10 divided by 2. Okay, that's my estimate. My estimate is, of course, a small decimal, but with a 10 to a power that's less than, somewhere around 15, maybe 14 or 16, based on the numbers in front. How did I get that? Negative 19 plus 4 is negative 15. And then the numbers multiplied in front might bring it up or down. So 5 times 10 to the fourth, parentheses, 3.2 times 10 to the negative 19 newtons per coulomb. And I get 1.6 times 10 to the negative 14 newtons. Okay. Confirm my answer just because I want to make sure that you guys get 100 on this test. And yep, I confirmed that the answer is correct. 75 questions, 75 points. We are 10 points away from a perfect grade on this Regents, and I'm really excited about that. Base your answers to 76 through 80, another 5-point question, on 5-problem question on the information below and your knowledge of physics. 2 students investigate transverse waves using a long, stretched spring, like a slinky. One student holds one end of the spring stationary, while the other student produces 12 waves every 4 seconds. The waves have a uniform amplitude of 0.20 meters and a distance between 2 adjacent crests is 0.4 meters. Excuse me. 76 to 77, 76 to 77. On your diagram in your answer booklet, draw at least one complete wave produced by the string. I actually recommend, drawing exactly one. So you are, and you're allowed to draw as many as you want, but this says that 12 waves every 4.0 seconds. So this is number of waves, and this is time. And then, so the frequency or the frequency is equal to number of waves divided by time. In this case, it's 12 waves over 4 seconds, which is equal to 3 hertz. Okay, so I got the frequency, which it's asking for, but I'm realizing that it doesn't actually need that. They have the amplitude of the waves 0.20 meters, and the distance between two adjacent crests is 0.40 meters. So this is the wavelength. Since this graph is position versus particle displacement, I'm going to have a crest at 0. I'm going to put a crest at 0. I'm going to put another crest at 0.4 meters. How high do they go? The amplitude is 0.20. So another 0.4 meters. I'm going to draw another one. Halfway through, we're at a trough. And in a quarter of the way through, we're on the x-axis. And 3/4 of the way through, we're on the x-axis, or the position axis. And so how do I draw this and make sure that I get full credit? If I try to draw straight lines, I'm not going to get full credit. I know that this is a sinusoidal wave. If I happen to have drawn many sinusoidal waves, then that's great. Draw a sinusoidal wave. If you've never drawn a sinusoidal wave, but you've drawn parabolas, you definitely have done that. You could draw 4 parts of parabolas. Parabola, parabola, parabola. Let's draw that one again, and it doesn't have to be perfect. Parabola and parabola. And that's it. I could draw a whole nother one after that, but I've already gotten full credit on this question. Okay? Now, I wrote this part again, just so I have, excuse me, just so I have the word there. Número 78, number 78, determine the frequency of the waves. Actually, I've done that. But let me just check if that equation is there. So they have V equals F lambda. They also have T equals 1 over F. Both of these equations could actually be used to find the frequency. So if I didn't know that frequency was defined as number of crests over amount of time, I could have done it this way. So, but how do I get the velocity? I know that there's 3 waves, 3 crests. So there's 12 crests every 3 seconds, every 4 seconds. That means that there's 1 crest every 1/3 seconds. So no, I don't want to do it that way. I don't want to do it that way. I know that the lambda is 0.4, and I know that there's let me see, 12 crests every 12 waves every 4 seconds. 12 waves every 4 seconds. So I know that the wave traveled 12 waves over 4 seconds. Now I know that this is the frequency, but maybe fake student me might not know that. But I know that the wavelength is 0.4 meters. So 12 times 0.4 meters every 4 seconds. And that's equal to 1.2 meters per second. So now I know the V. So that's the V. And then I put that into the equation for V equals F lambda. I have the V, I have the lambda. And then I get the frequency. 1.2 divided by 0.4 is equal to, so I have 1.2 meters per second is equal to F times 0.4 meters, divide by 0.4 meters, divide by 0.4 meters, and I get that the frequency is equal to 3 hertz, as I expected. So I have 2 different ways of getting the frequency. One using using the definition of frequency, but I had done that earlier. But this one used the formula sheet as given. So whichever way you choose to do it, that's full credit. The frequency is equal to 3.0 hertz. That Z shouldn't be lower. HZ. Okay. 79 to 80, 79 a 80, calculate the speed of the waves. I actually also did that. So that work is already here. This is exactly how to calculate the speed. But if you found the frequency, you could find the velocity. But now, so we've done all this work. So the velocity is equal to 1.2 meters per second. And now you know how to calculate the speed. But you could have also calculated the speed with the frequency by using the v equals f lambda. Okay, many ways of doing this problem. I notice that what I've said many times. Like there's a lot of ways to access the answers. Now, I wanted to show this picture of an alpha particle leaving a nucleus. This is an example of nuclear decay or alpha decay or alpha, the word ALPHA decay. Many heavy nuclei emit an alpha particle with a certain amount of frequency, and they decay this way. Base your answer 81 to 85 on the information below and on your knowledge of physics. Alpha particles are stable decay products of many nuclear disintegrations. An alpha particle consists of 2 protons and 2 neutrons and has a mass of 6.644 times 10 to the negative 27 kilograms. When the individual masses of 2 protons and 2 neutrons are added, the sum is 6.695 times 10 to the negative 27 kilograms. The difference between the mass of the alpha particle and the total mass of its 4 individual component particles is called the mass defect. 81, number 81. Now, I'm really excited at this point. We are 5 points away from a perfect grade on this Regents. I'm super stoked. So if you're super stoked, let me know. 81 and 81, determine the mass defect in kilograms when 2 protons and 2 neutrons combine to form an alpha particle. So let's talk about this answer. And this is something that I think the Regents graders would have to clarify, because they did give the answer. They gave the formula, the difference between the mass of the alpha particle and the mass of its 4 individual components is equal to the mass defect. So I'm going to calculate it in that order, in the order that they gave it to me. But it's important to know. I mean, I did notice in the grading that they had the a positive answer, but that said, the mass defect, according to this, they said that the alpha particle has a mass of 6.644 times 10 to the negative 27 kilograms, and that subtracting from that, the mass of the components is 6.695 times 10 to the negative 27 kilograms. And notice that this is actually a negative number. Let's get that as a number. And now I might not know how to convert that into a number in scientific notation, which I think, there's a limit to how much we can know on any given test. The way to convert it is by, moving the decimal place over a certain amount. If you shrunk the number, then you have to increase the exponent on the 10. But I'm going to let the calculator handle that for me. 6.644 times 10 to the power of negative 27 minus, parentheses, 6.695 times 10 to the power of negative 27, close parentheses, and I get a negative number, negative 5.1 times 10 to the negative 29. Negative 5.1 times 10 to the negative 29 kilograms. Now, I do have like a minor complaint to the graders, so I'm just going to do a little finger wag again, because in the grading, they have a positive 5.1 times 10 to the negative 29 kilograms, but the order in which you, the writer of the test, gave it, you said the difference between the mass of the alpha particle and the total mass of its 4 individual component particles is that mass defect, in that order. That is the order in which we subtract in math class. The difference between blank and blank, the difference between P and Q is P minus Q. And I'll tell you the truth, like I blanked to the point where like I even had to look up the words to make sure that I wasn't blanking on the way we in writing define subtraction. We define subtraction. The difference between P and Q is P minus Q. So I literally Googled it, checked my math. I literally went into Math Regents and checked how they do it just to make sure that I wasn't teaching it wrong. The way we define the subtraction does give us a negative answer, but in your grading you have a positive answer. The last thing we want is for a grader to see a negative 5.1 times 10 to the negative 29 kilograms and mark that as wrong, right? So, especially if you defined it the way you defined it. And so, definitely note that in your grading. That said, 82 a 83, 82 to 83, calculate the total amount of energy in joules that would result from the complete conversion of this mass defect to energy. Okay, so I'm going to use the positive number for this conversion because of the fact that the E equals MC squared does have a positive number in it, but it doesn't actually require a positive number. I'm going to use a positive number for this one, but now where's this formula in the formula sheet? E equals MC squared. That is a classic Einstein formula. Okay, E equals MC squared. So we use that formula. E is equal to the mass 5.1 times 10 to the negative 29th kilograms times C is 3.00 times 10 to the 8th meters per second squared. And now this number is going to be in joules. So let's get this. Now, it's going to be a small number, but also worth noting, a small number, relatively speaking, but also just a huge number relative to what you could get from a chemical reaction. So parentheses, 5.1 times 10 to the power of negative 29, parentheses, 3 times 10 to the power of 8 squared, and that's 4.59 times 10 to the negative 12th joule. Or if you wanted to use two significant digits, 4.6 times 10 to the negative 12 joules. They would have accepted either one of those two answers. All right, and we're 2 problems away from a perfect grade on this region, so I'm really excited about this. Determine the total amount of energy that would result from the complete conversion of this mass defect to energy in mega electron volts. So I'm going to do this with some nice chemistry methods, but it really is just a mathematical method. In chemistry, you call it stoichiometry. In math, you just call it unit conversion. 4.6 times 10 to the negative 12th joules. Now, you have to convert joules to electron volts. Now, how many joules is in an electron volt? That's when you have to go to the formula, the physical constants. Joules to electron volts. 1 electron volt is this many joules. And that's the one I'm going to use. Okay. I'm going to put that right there. Okay. So I have 1 electron volt divided by 1.60 times 10 to the negative 19th joules. Now, a common question is, how do I know which one to put in the numerator and which one to put in the denominator? And the answer is that the unit in a numerator, some unit in the numerator and some unit in the denominator have to cancel. So that cancels, that joule cancels with that joules. And so I know I put it in the correct place, electron volts. Okay, and then, but I have to convert electron volts to mega electron volt. So how do I know? I need to know that mega equals 10 to the 6th. Okay. So mega electron volts is 10 to the 6 volts, electron volts. So 10 to the, so I need to cancel electron volts. So I know that 10 to the 6th electron volts is 1 mega electron volt. And now electron volts cancels. That's how I know I did it right. And now I go to my calculator. And you know that like chemical reactions with single atoms and molecules, their energies are measured in electron volts, and but often nuclear reactions are measured in mega electron volts. In other words, they're actually in the order of about 1,000,000 times the amount of energy of chemical reactions. So 4.6 times 10 to the power of 12, negative 12, okay, close, times 1 divided by, parentheses, 1.6 times 10 to the negative 19, close the parentheses, times 1 divided by, again, 10 to the 6th. And I get 28.75 mega electron volts, which is around 29 mega electron volts. If you gave the answer as 28.75, you would get full credit on that, so you don't have to worry about that. And this note, we're about to end 85. I want to just finish 85, drop the mic, say we're done, and say bye. So before I even go on to 85, I just want to thank you for even making it all the way through this video. I really believe in your ability to do as good as possible on this Regents. If you actually stuck to me in this video as long as you did, then you did a very big service for yourself. And I want to just applaud you for that. I believe in your ability to do well. All that it takes is getting as much of that information in your brain as possible. If you do have time to rewatch this video, what I do recommend is go over the ones that you got wrong. Now, if you didn't do the problems, like you only watched me do it, then I would recommend going through the problems again and actually choosing an answer and actually doing the algebra that is required to get the problem right, and then see if you got it right relative to the way I did it. On that note, we are going to go to 85. I would appreciate if this video has helped you, that you click the subscribe button. I want to move on to number 85. Let's just go. Let's do this. 85, number 85. What fundamental interaction is primarily responsible for holding protons and neutrons together in an alpha particle? Well, it's a fundamental interaction, so they did give us a hint there. It's one of the 4 fundamental forces. It's the gravity, the electric force, or the weak nuclear force, or the strong nuclear force. The one that's responsible, and it's, by the way, it's massive. The fundamental force, it's extremely strong. Hint. The fundamental force that's responsible for holding protons and neutrons together in an alpha particle or in any nucleus at all is the strong nuclear force. And with that, we put that period, we pick up the mic, drop the mic, and we're done. Good luck.